Good evening, my friends. Today we want to talk about important skill sets you're supposed to have for your successful May examination. Without further ado, let's get started. What we're going to do is to read through some of the May 2021 questions and thinking about the mindset you're supposed to have. I'm going to put myself in the shoes of a student and how we're going to spend that essential first 5-10 minutes of the reading the paper. And then we're going to go over each topic and talk about the essential skills for those problems and apply them accordingly for the November paper. Let's get to it. So now I'm a student. I'm in the exam room and I'm reading this question and I'm thinking, okay, it is something about the, let me use a highlighter, arithmetic sequence. Okay, so I'm talking about the arithmetic sequence in series. Okay, very likely that it's going to be some sort of a simultaneous equation. And voila, we have a sequence in series. Okay, that's great. And as soon as I see that, I say, oh, okay, it's a present, it's a Christmas present. I just have to work simultaneously by using the formula that we know of, right? For the, the arithmetic sequence. Okay, it's gonna be the first term plus 7d is equal to 8. Okay, I have a two unknown parameter, the first term and the common difference. Well, I can get the secondary equation from the series. So let me use it. S8 is going to be 8 over 2, and what is it? 2u1 plus 7d. So all I gotta do is just solve it simultaneously by either substitution or cancellation, whatever suits you, is what we gotta do, right? So that's the sort of a mindset you need to have. I'm not gonna solve it, right? When I'm reading the paper, as soon as I got the paper in the exam room, I will be just reading through all the questions and mark them. Okay, so this is a topic 1 sequence, simultaneous, boom, then move on to the next question. It's sort of a tactics that I want you to have, right? Okay, I'm looking at this problem without blinking an eye. I know that this is something about the whisker plot, so I'm aware it might be something with the interquartile range or outlier, and luckily we have something with the outlier here, right? That is great. So I know that I'm going to be using some of the formula that we already have learned from the topic 4, right? So, I'll be thinking then, oh, okay, for this one, I just know that the bound for the outlier is going to start, okay, from Q third quartile plus 1.5 interquartile range. So, that your job is to get the interquartile range, which is, difference between the third and first. I think this one gives you, yeah, there you go. And that's all I'm gonna check, right? So, the essence of this video is to get the first 50% of your understanding, okay? The secondary 50% to achieve the full marks of this problem is computation. It is your algebra, how fast and how correctly you solve the problem. But for the 50% is what you've been accumulated for the past 2 years, isn't it? Right? So, and that's what I want to check throughout the video. Okay? All right, let's go. All right, as soon as you read this question, you should be thinking, oh, examiner has been cute. Okay, examiner has been cute. Minyoung, why? Because I'm pairing the double angle of a cosine with 1. As you know, there are three forms of a double angle of a cosine, isn't it? So cosine square minus sine square, 1 minus 2, blah, 2 minus cosine, 2 cosine square minus 1, etc. But your job, okay, of double angle of a cosine, if there exists 1, is to cancel it out. I want you to get rid of it. What I mean by that is, among many terms of a double angle of a cosine, what I'm going to use is the 1 minus 2 sine squared x is what I'm going to use. Why? Because it cancels out. That should be the thinking that you have, okay? I'm not going to solve this problem, but I just want to talk about what sort of skill sets we need to have. As soon as I see 1 with cosine, boom, I'm confident that I can solve this problem without hesitation. Okay, that's great. So I'm going to move on. That's the only skills that I want to talk about. When I'm in the exam, I read this question. Okay, examiner is being cute again, right? Why? Why? Because 2 of the roots are given as a complex number. Okay. Then what do you know? Sure, by the fundamental theorem of algebra, I know their conjugates are roots as well. Kumbaya. That is great. And also, what would you like to use? Would you like to make a factor here and expand them? No, I don't want to. You're absolutely right. I want to talk about sum and product of roots, right? So, if you add all that, what do you get? The imaginary parts, boom, cancels out, right? No problem. Very good. And then, then you're going to make, okay, then negative 4s are going to be, what is it? 2a plus 2b. And then what are you going to use? Product of roots, aren't you? And yes, please make sure product of roots are alternating. So what I mean by that is because I've got degree 4, it's going to be positive, right? So then you're going to multiply them and you're good to go. You can solve them simultaneously. Done, right? So I don't want to talk about the details of this problem, but just the skill sets you need to have, okay? And how it is beneficial for you to gain the confidence and accuracy of the solving problem. Right, when I look at this, which part should I have a look? Okay, so for this one, why I have pointed out is because, for this one, you'll be thinking, oh, okay, this is a Cartesian equation of a line. I got to be very careful with who? The direction vector. Aha, you know what? As soon as you read this, I want you to chuckle. Okay, I want you to smile. Examiner is trying to have a trap on you, right? Because if I have a negative coefficient on z, I got to be careful with the z component of the direction vector. Remember that? I want you to always have the positive coefficient. So meaning, for that one, I want you to slightly change into who? Z minus 3 over negative 1. Aha, you should be able to spot that. When you read through the paper, you realize, okay, where's the trap? And this is the trap, right? So therefore, the direction vector is going to be, what is it? 2, 1, negative 1 is what I'm going to use. Okay? That's great. So, for the details, I'll leave it to you. You do your job. My job is to tell you what sort of skills that we need and what sort of keywords we try to find. Okay? That really comes from the practice you already have made throughout the years. Okay? And today, it's just to consolidate. Okay? Good. When I'm reading this problem, when I got the paper and then go through the the section B problem and realize, okay, this is a long question, right? And then we realize, okay, I look at the induction with the derivative, and what should you then be reminded? Okay, when I'm trying to prove the the result to prove case for the derivative, I'm aware that I have to be very careful with the derivative, okay, of the induction hypothesis. I'm going to differentiate only once more of my hypothesis. Okay, so that's the one thing that I want you to remember. Okay, so that's what we're gonna do. And sure, for the product, I'm going to talk about that when I later talk about the topic 5 skill sets, and for those details things that I'm gonna talk about later. But for this one, I just wanted to point out, okay, induction, derivative, I just have to be careful with just differentiating once more from the hypothesis, right? Very good. Okay, so what I'm going to do is this. All the answers are within the syllabus, okay? And they give you a great guideline. I think the PDF is 100 pages long, and talking about what you should know and what you should be expecting. And you know what? They even throw out some great ideas for the extended essay and internal assessment. What a great document that is. And among them, it talks about the syllabus of AA. And I would go through one of those subcategory of those topics and talk about, okay, what sort of exam questions you're expected to have, and talk about the skill sets that we're going to do, okay? Before we continue, let me just quickly check on my microphone. Yeah, it's running, so great. Okay, let's move on to the next slide. So yes, this SL 1.2, it's core, so H students are supposed to have that class as well, as you have seen from the first example on the May 2021. Let's say what sort of a potential skill sets they're going to ask. Okay, arithmetic sequence, okay, are very popular with the logarithms, right? Logarithms in general are very popular with these sequence and series. Why? Because when you add them, right? If you combine the exponent, if you combine the domain, it becomes geometric, or sometimes it can be arithmetic as well. So things like that, log with the arithmetic or geometric, I need to remind you they're very popular to come along. And for this one, what I want to make sure you to try to find is common difference, right? For the arithmetic, common difference is very important. And for this one, what you should be aware is I don't like that I have a different base, right? So then we can use a change of base, right? Remember, well, it's supposed to be topic 1. I wasn't going to talk about the log a lot, but then because it's a very nice problem for the arithmetic, I'm going to talk about it. What is log BA is the same as 1 over log AB. You should be able to prove it, okay, using the change of base. I will leave that as an exercise, but that's what it is. And for that, we can do the difference, right? So it's going to be equivalent to what is a log base x 2 log base x 8. Okay, then voila, we have we were given that this is arithmetic. All I gotta do is just to find the common difference, and you just subtract them, and you realize, aha, the common difference is just log x 4. That's it. I'm not gonna solve this problem. I just want to remind you what is log is popular with arithmetic and geometric as well. Okay, that's good. Oh yes, and for this is a very, very nice problem. Very, very nice. All you gotta remember is this. Okay. What is arithmetic sequence is really just checking with the linear relation. In arithmetic series is talking about the quadratic relation. So if I see the series with something of a square and linear, no constant. Okay, if you have a constant, that's something else. Okay, so don't worry about that. But as soon as I see that, even if I wasn't given that this is arithmetic series, I should know that this is arithmetic series. And then what the question often asks you is to derive the sequence from the series. Okay, so that formula I want you to remember. Okay, so to get the sequence from the series is the following. What we're going to do is Sn, we know it's a general formula. So A1, A2, A3 goes all the way to AN, right? And then the AN minus 1 plus AN, let me write that far. And then the N minus 1 is A1, A2 goes all the way to AN minus 1, right? And then what we can do is simply subtract, right? So what happens, they all cancel out, isn't it? So I'm just left with the sequence AN, very good. So therefore, AN is going to be Sn minus Sn minus 1, okay? And it applies for the arithmetic and geometric. It tends to be popular with the arithmetic, so I wanted to talk about that, okay? So, and also, just to give a preview, I'm going to talk about this later also. Consecutive terms, it is always talking about either arithmetic mean or geometric mean, okay? So these are given as a consecutive of a geometric sequence, so you should be using the geometric mean, but I will be talking about that a bit later, okay? Right, the SL 1.3 suggests that it's a geometric. Then let's talk about what sort of questions we are expecting for the geometric sequence and series. Right. What I want you to remember is that for the sequence and series, you can have either the explicit form, which is just in terms of n, and recursive form, very, very popular for paper 3. Okay. But again, here I have a recursive form. My present term depends on the previous term by multiplying some constant. So even if you don't have the geometric definition, I should be expecting that this is a geometric, right? Is my point. Okay? So, because I've got the first term 3, I can convert this into the explicit form. Let me change the color into red. Okay? And then the explicit form, therefore, should be, using the formula, the first term 3, and then the common ratio 1 plus I to the power of n minus 1 is what I'm going to be writing. Okay? And blah, blah, blah. I'll leave that as an exercise. But here's the thing. Yes, you should be aware that, I don't like Cartesian form of a complex number to the higher power. Right? I want to apply some DMT on it. You know what I mean? So I want to make into the polar form maybe. Right? I don't want to deal with, Cartesian form to the something power of n. So I would probably change this into, the polar form as such as root 2 cis pi over 4. And then you would be good to go. But here, why I was making this example to explain about the geometric sequence and series is because I want you to be aware. I want you to be able to distinguish between the recursive and an explicit. Okay, that's great. Oh yes, this is the example that I wanted to talk about. Why? Because every time you have something three consecutive terms, it is either the arithmetic mean and geometric mean. If I look at the first case, that's the arithmetic sequence, and arithmetic mean was what? Can you tell me? Pause the video. Talk to yourself. What is arithmetic mean? Very good. It is a 2 beta is equal to alpha plus gamma. Right? Great answer. And the geometric mean was a beta square is equal to alpha gamma. Okay, so that's the thing. I'm not going to talk about anything in this question in details. I want to just talk about what sort of skills you're supposed to have. When you read the question, okay, 3 roots, 3 terms of arithmetic sequence. Examiner is being cute again, right? Zeus. Why? Because we are using the arithmetic mean or the geometric mean. Okay, very good. Oh yes, this is a very nice problem. Why? Because talk about the series of what? Geometric series, and I'm trying to convert that into the arithmetic sequence. Okay, so either arithmetic or geometric. So either arithmetic or geometric doesn't matter. If you want to convert from series to sequence, what are you expected to do? Yes, you're right. I want to do the Sn minus Sn minus 1 is equal to who? An. Okay. I want you to try this yourself. But here's the thing, just give you a little bit of taste, is that you want to simplify before you continue any algebra, you know what I mean? So for this one, I wouldn't put the n minus 1 right away. I want to simplify this one because it's a sort of I can do some long division there, right? So it's actually same as a 1 minus a over 7 to the power of n, right? So it's a lot easier for you to perform the algebra than plugging in n minus 1, all that, you know what I mean? That is great, okay? And this question is also very nice. I want you to try this at home, okay? I'm not going to solve it, but that part is very nice, and what I want to highlight is this, okay? But I'm going to move on. Right, then yes, the superstar, compound annual depreciation, anything with the financial sequences series can come up for you either paper 1 or paper 2, okay? And so I think this problem, I don't remember the year exactly, but this problem is beautiful. If you can solve this problem alone, you're good to go, okay? I want you to take your time reading this paper. Let me just get out of the screen for a while. Just pause the video, read through. Okay, I'm assuming that you already read through. For the financial sequences series, I want you to know the names, right? What does it mean by a simple interest? That's just the arithmetic sequence. What is a compound interest? That's just the geometric sequence. But for this problem, lucky her, lucky Mary, grandpa is putting all the money for her. Good for her, okay? So this scheme here is the superannuation, right? So what I want you to do is to be able to read the passage and realize what sort of a financial plan they have. And this is actually superannuation. Why? Because it's really just about what? Geometric series. Okay? That's great. And this is a very nice problem. It's potentially some paper 3 or so because it's really just about the recurrence relation. Okay? So I want you to take a look at this example also. How you can derive the general formula using iteration. So the whole point of doing this is to you repeat the process. Okay? And then get the actual general term. But whole point of me bringing up this paper is, the question is that, in the sequence of series, there's application with the finance, and among many, superannuation is also a very nice problem. But first half of this problem in that year was about superannuation. And then the second half was even better. It was about the repayment, okay? It was about the repayment. Okay, so for the, as soon as you read this question, let me just get out of the screen so that you can pause the video and read through. Good. I want you to realize that this was about the repayment. Why? There's some money going up, or my loan, and there's some money that is going out. Birthday present, or my repayment. Okay, so this is repayment. And as soon as I see repayment, I want you to be able to come up with the formula. Superannuation was about the geometric series, and repayment is just the battle between the geometric sequence minus, what is it? The repayment times the geometric series. And that should go flat out to be 0 to pay back my entire amount, or waste all the juice that I had in my bank. Okay, so if you just vaguely write down the formula, the geometric sequence usually goes by, okay, whatever the initial amount that I have with the r to the power of n, and that common ratio is very important for you to define according to the compounding method. Minus x times r to the power of n minus 1 over r minus 1 equal to 0 is the typical formula that we have. Okay? That's great. Okay, let's talk about some of the other I just combined them together for the exponential equation because, those part, it talks about some property of exponent and log and then applying for the equation. Okay? You can do it. So I did, blah, blah, it's fine. But yes, this is a very, very typical one, right? When you have, let's say, A times B, then maybe it's worthwhile to apply the log, right? Because we can apply the property of log, right? Ln A plus ln B. You know what I mean? But when you have addition, there isn't much you can do when you composite with log, okay? Because a lot of people sometimes get confused and even apply this to claim that this to be ln A times ln B, but it ain't, right? So you got to be very careful. And I wouldn't composite the log here, but realizing that, okay, you know what? Our enemy is any variable in the bottom. We don't like it. We don't like it. So what we are expected to do is get rid of it, right? How do we get rid of it? Well, by multiplying the reciprocal. So let's go with 5 to the power of x. Boom, 5 to the power of x, okay? So if I did here, let me quickly write that for you, and then it's a laws of exponent, right? That the plus 1 can come to the front, and the coefficient is going to be 10. We have a 10 times 5 to the power of 2x. And if I quickly rearrange after the distribution, I have a 5 to the power of x. A minus 3 is equal to 0, and what is your, let me just write it more carefully, you know what I mean? 2x, okay? Bear with me with my handwriting. It reminds me of a quadratic. Good to go, okay? Then I will use a substitution and blah, blah. But the whole point of me is that, in this part, many properties of exponent or logarithms to apply, and here I'm going to use that quadratic form, okay? That's great. Oh, same thing here. Whenever you're trying to solve the log, the best kind is to have a same base. I don't have a same base here, okay? What do we do? Well, it's actually interchangeable, right? It almost looks like the same base. All you gotta do is just to change the base that we saw in the very beginning, right? So what I want to remind you here also is that log BA is 1 over, what was it? Log AB. Okay, so I will use that there, So then we can have what is it? It's the same as a 4 over log xy. Okay, then I have a log xy. Okay, and what we can do is just rearrange to the left because it becomes a perfect square, doesn't it? Then I have a log xy square is equal to 4. I'm very happy. We can use the property of log again, right? This 2 is going to come down, isn't it? So it becomes 2 times log xy equal to 4, right? Oh, no, it's not. Okay, please be careful. Okay, the power of entire function is nothing I can do, only like substitution, etc. But if it was, if it had been the exponent in the inside of a function, then you can take him to the front, but not in the entire ones. Do not do this. It's a very common mistake as well. I gotta warn you about. But here, it's going to be what is it, log xy is equal to who? Plus minus 2. Okay, don't forget log can be negative, okay, but cannot have a negative domain, but can be negative in range, okay. So from here, I'm gonna say what is it? Y is equal to x to the power plus minus 2. So that means square or 1 over x squared. Here's the one thing. In the mark scheme of this problem, it didn't really specify the possible values of x and y, but you should be aware of it. Okay, and even if you wrote that in the exam, it's absolutely fine. Okay, what I mean by that is remember, sure, the domain of log, they are positive, but do you remember the condition for the base of log? For example, here, log xy, what do you remember about the base? Yes, not only positive, but also cannot be 1. You need to specify it, okay? Got to be very, very careful. Same thing for the y here, right? It's a good example to not only talk about the property, but the fundamentals of his domain and the base, okay? Sure, for this one, what I would encourage you to do is another property here. What is another property that I want to mention about? Log a to the power of n, b to the power of m. Sure, this m is an exponent, will come to the front, but this, what you have in the base, will go reciprocal, right? So it's going to be m, oops, let me go back, change into pen, m over n log AB is what I want you to remember, okay? I'm writing down the essential skills. But you know what? You should question yourself. And question yourself, can I prove it? And yes, it's examinable, okay? And it came up in the very recent paper. I can't remember the year, but examinable, okay? Is it how you spell it? Whatever, okay? So you should know how to prove it. And why I'm saying that, maybe I can take that, 2 square is going to come to the front being what? Half. And that half will go to the square root of it. And you remember that log is a one-to-one function. Range same implies the domain same. So I can simply just change that into x minus 2 is equal to, what is it, square root whatever, and then you're good to solve, okay? And the second example, as I've said before, I prefer having the same base of a log, and I will try my best if I can change. So, same thing for the exponential. I want to go with what is it, same base of a exponent, right? So if you don't have it, no problem. If it's an exponential equation, maybe you use log because they're inverse to each other. So what I would probably do is to compose it with ln and see what we can do, right? The thing is going to come out, it's going to be a perfect square. And remember, ln e is simply just to 1, right? It's good to go. So here, why this problem? Because I wanted to talk about that skills, okay? I actually should talk about what skills we're aiming to achieve in here. And for this slide here is the algebra. Yes, you know what? As soon as you read this paper, you read this question, and you'll be thinking, okay, you know what? It's all different base. So maybe I would just compose it with log. You could do that, but I don't want you to rush. Every time you're trying to compute things, it's not only within topic 1, later on topic 5, such as differentiation or finding the limit or integration, I really want you to simplify as much as you can, okay? What I mean by the simplifying on this one is that some parts are actually divisible, right? What I mean by that is maybe 3 is a prime number. I can't do anything about it. But for this one, 2 to the power 4x plus 2. You're absolutely right. And for 6 is a product of 2 and 3. So, this can be 2 to the power x plus 2, 3 to the power x plus 2. And then you can cancel things out, right? Whole purpose of me bringing up this problem is what matters? Algebra matters, okay? Especially who? Yes, simplification. You know what? I'm cool, so I'm going to write in cursive. Okay, Almost, no? Simplification. Good. Okay, so please try to simplify as much as you can, okay, before attempting anything. And then, yeah, and after cancel things out, then you can take the learn and things are going to be way quicker, okay, way better. Hey, please fasten your seatbelt, okay? I'm going to fasten seatbelt on my fat belly too. Superstar. Not easy, okay, not easy. So now it's talking about that part is talking about the proof by deduction. So you should be very comfortable with the 5 different methods: proof by definition, proof by, I'm not saying in order, exhaustion, counterexample to disprove things, and contrapositive and contradiction. 5. What have I said? Definition, exhaustion, counterexample, contrapositive, contradiction. 5. You should be comfortable with the deduction. Okay? Yes. Great. So this will be a typical definition problem. I really wish, you know what? It hasn't appeared yet, definition. It hasn't appeared yet in the exam, but I'm really hoping that this will come on paper 3, okay? One day. I have a dream one day. So, you know, the typical definition you're going to apply here is the first principle, isn't it? So, in order to find the derivative, I'm going to use the first principle of sine x plus h minus sine x over h and things like that, right? I'm not making an example here to solve this, but I'm saying definition matters, okay? If someone asks you to prove it, you should be thinking that I'll be using first principle, all right? And the many examples that are associating with the by definition, such as a vector theorem. Use the vector theorem to prove this, or use Pythagoras theorem to prove this, prove that, you know, for example, if it's a shortest distance, that will make the perpendicular to a point from a line, things like that. You know, you're applying something that you already know to solve another theorem, and that I would say that is that would be the hardest kind of my proof by induction, and I really hope that this will come one day. But what's the purpose of this question, this slide? Definition, such as first principle, vector theorem, sine rule, cosine rule, you name. Okay, you name it. It's really examinable throughout the topics. Okay, so this will be the proof by contrapositive. Right? So A implies B is equivalent. Remember, equivalent, not B implies not A. Okay. So when do we use it? You know, they are logically the same statement. Okay. So either you take this direction, that direction to prove things. It doesn't matter. But, you know, whenever you're dealing with this type of question, what I don't like here is that what I'm trying to start with, my hypothesis, is just very complicated, right? For me, I prefer starting something simple like odd, okay? So what I would equivalently change this statement is that, what would that be? You're right. And even implies whatever that statement is odd, okay? So I will slightly change it so that it is a lot easier for you to start with that information. Then I'm gonna say, okay, let the n equal to 2k, where k is an integer, then on and on, right? It's fine. Okay? So the point of this slide is because to talk about what contrapositive. Okay? That's great. Okay. Oh yes, love this problem. Okay, solving inequality involves a lot of contradiction. I mean, you know, there are many things that are popular with the contradiction, such as a finite versus infinite, prime, non-prime, rational, irrational, you name it. There are so many different kinds. But what I think is also popular is with inequality. Okay. What is a contradiction? Yeah, you're right. Oh, Very good. Well read. Reduction to who? Absurdity. We love absurdity. Okay, so things like that, what would you do, especially for inequality? You're gonna assume the opposite to be true, and then come down to something strange, right? Strange things. And for me, then you're gonna say, suppose, what is it? Left hand side. I don't want to write all that, but let's do it for the May examiners. Okay, let's just write everything. Cosine alpha minus beta is bigger than cosine square alpha. And of course, you want to play around here, right? What should remind you? What should the left-hand side remind you, my friend? Oops, sorry. That's the one I'm supposed to find. Yeah. What does the left-hand side remind you? Very good. You're absolutely right. It reminds you product to who? Some formula. You're absolutely right. By now, it should be obvious. By now, you should know it. Okay? If you don't know it, don't worry about it. This video is going to confirm and verify why knowing this formula is important in the topic 3 later. Okay? But product to sum, very important, right? And what is it? What was it? So, if I have a 2 cosine A, cosine B is going to be same as who? Cosine A minus B plus cosine A plus B. You can check yourself by using compound angle and whatnot, okay? And this is very, very popular for trig equation and induction, so please make yourself clear that you know them, okay? So I'm not going to solve it, and you should solve it. So here I would suggest that you use the product to sum formula. For this one, I want you to use the half angle, right? You will realize why I need to use half angle here. And if I did, it's going to be, 1 plus, what is it? A cosine 2 alpha over 2. And you'll be getting into some contradiction that you can solve later, okay? That's great. Okay, so, purpose of me of bringing this table is why? Because I wanted to talk about the contradiction with inequality. But it's not just limited to the inequality. Remember, there is a debate with the prime, non-prime, finite, infinite, rational, irrational, so many examples, to name a few, okay? Let's talk about who? Infinite series. Okay, let's talk about the infinite series. Very important. 2 things I want you to remember. 2 things. What is it? The formula, sure. But also who? Even more important, I think they mentioned it here. Yeah, there you go. The interval of convergence, it brings a lot of inequality. Okay, this one doesn't matter much. You already know it. But that one is way more popular to be assessed. Okay, so let's have a look. Okay, what I want you to realize here is that you realize that this is the geometric series, infinite geometric series. Why? Because we have something to the power of n. So he represents like what? Common ratio. Okay. So, for finding the set values of x, what you need to do is to solve inequality of who? Very good. Absolute value of 2x over x plus 1 less than 1. Okay. Then you solve the inequality, right? So interval of convergence is very, very important. And you know what? I really want to talk about it, but I have a great set of questions in topic 2 to involve with inequality and absolute value. But I would say a few things here. Please, you could, in this time, but I don't like squaring things, okay? I don't want you to square too often when you have absolute value. I get it. I get the absolute value of x squared is an x squared, but sometimes it creates some problem, okay? So what I would encourage you to do is when you're dealing with the, the absolute value with inequality, I want you to try your best to solve the inequality by sketching. Okay, I want you to sketch. Okay, try with sketching is what I gotta say. Okay. Next, let's move on to next. Okay, what I have mentioned here is the importance of what defining the values of x so that the series would converge for the geometric sequence. and series. Okay, there you go. Again, for part B says what? Find the set values of x for which the geometric series is going to converge. Then you got to find the common ratio, isn't it? So here, the common ratio comes as a 2 cosine x. Okay, and for this to converge, you already know. So the absolute value of 2 cosine x has to be less than 1. You're right. But here's my point. You really need to start practicing solving the inequality by sketching. I don't want you to square things a lot. For this one, I think it will overcomplicate if you square. Okay, so you just graph it. Graphing is fine. So, and yes, it's a periodic function. So what matters a lot? The domain matters a lot. So it says it's defined from negative pi over 2 pi over 2. So I'm going to just graph it. I'm just going to graph it for you. Okay. Then you're comparing with the y equal to 1, and then what do we want between these two? Then voila, you can just find the intersection and describe those intervals. Leave that as an exercise. But the importance of this slide is to discuss. It matters a lot for finding the values of x or r to make the infinite series converge, and that involves a lot of solving inequality. And for solving inequality, I want you to make sure graph it. Okay, you don't have to graph it later because you'll be talking about sign diagram, but you gotta sometimes practice it. Okay. Oh, sure. Also, a lot of simultaneous equation for the arithmetic geometric sequence and series, right? So you should just have two things: first term and common differential ratio. Okay. Same thing for the infinite series. What do we have here? For the first one, it says first term. Oops. Let me change in red. I have a first term here, and then the common ratio, then voila, we have a over 1 minus r being just 76. That is great. I don't know why. And for the second series, that's going to be who? A over 1 minus r cubed being 36. And yes, you should be comfortable being able to solve this simultaneously. I would just divide, and then good to go. And I cannot put emphasis on the importance of algebra. You should definitely be able to see what 1 minus r cubic, 1 minus r cubic is factorized as what? 1 minus r, 1 plus r squared. Okay? Then, cancels out, then you're solving a quadratic equation, and make sure, okay, even if you found the solutions in the quadratic equation, sometimes the absolute value of r may not be 1. May not be less than 1. You got to double check that, okay? Do not rely too much on the equation. Please double check with the condition that it's within that interval, okay? So why I was talking about that one? Because to emphasize the importance of the simultaneous equations, you should be able to describe every sequence and series of arithmetic and geometry by two things, two terms. First term, common differential ratio, okay? Sure. Superstar, well, not yet, because I was going to say about the rational power, but natural power, easy peasy, lemon squeezy, okay? Now let's move into the next slide. So we're talking about the binomial theorem. Binomial expansion, superstar with rational power, but we're going to talk about the natural power first, okay? General form, right? So make sure we are aware of the a plus b to the power of n. We're able to simplify things, So sigma k is equal to 0 to n choose k, a to the power of n minus k, b to the power of k is the form I'm going to use. And I will try to simplify as much as I can. So what I mean by that is, when I'm looking at things like that, I will instantly just go simplifying, such as, what is it? Sigma k is equal to 0 to 12. Then it's going to be 12. Choose k. My a is going to be 4x squared to the power of 12 minus k. And then I have a, negative 3 over, let's go with the k, negative 3 over 2x to the power of k is what I have. But after having applied the formula, what you need to do is to also simplify, right? I want you to simplify as much as you can. So what I mean by that is, I'm gonna expand it using the exponent rule. So 4 to the power of 12 minus k, x to the power of 24 minus 2k, negative 1 to the power of k, 3 to the power of k, 2 to the power of negative k, x to the power of negative k. Okay, then I will group them together. But before doing that, maybe I can change that as 2 to the power of 24 minus 2k, right? That's great. Then what do we have? Maybe I will combine that together, 2 to the power of 24 minus 3k, boom. Alternating term, I'm going to put it in the form, in the front, negative 1 to the power of k, 3 to the power of k, voila. X to the power of how much? 24 minus 3k is what I've got, okay? Sure. And simplifying that gives you a lot of a chance to find a desired term, such as a constant term, meaning the exponent has to be 0, so degree has to be 0. So here you can choose your desired index. So the index that you're going to work with here is k being 8. Okay, then you can plug all the k here with the binomial coefficient, and you can find the terms. The whole point of this problem is to encourage you to use the formula and then try to simplify as much as you can. Again, algebra matters. Okay, let's have a look at the next problem. So here, what skill I want you to have here is that you realize that this is talking about the product of a two binomial expansion. And here then you're gonna play some distribution, is that so? There will be some of the term here, a1, a0, a1x, a2x squared, plus on and on and on. Multiply by who? Maybe I will use different color for you. Let's go with b0, b1x, b1x, b2x squared, plus on and on. Of course, you may not have the coefficient for a certain degree. Doesn't matter. So point here is, if you're looking for the constant term, right, the distribution will be only limited, right? You are only looking at the product that's gonna yield into the constant term. So things needs to cancel out, or it's a product of a constant term, right? So by inspection, if I look at from here, maybe it's possible to have 1 over x, for example, right? Then I'm going to only find the term that could possibly give here being x, right? Who knows, right? We don't know. But what I'm trying to verify here is that for the product, I want you to be very careful. I don't want you to expand out everything, but only find the desired term that's going to give you the desired term, such as a constant term. Okay, that's great. Let's move on to the next one. For this problem, it brings us the sense of ascending form and descending form, right? Descending order or ascending order. What I want you to be always careful here is, if you put the constant term in the front, that yields into ascending form, if we follow the formula that we used in the previous slide. So what I mean by that is, if I had put a plus x to the power of n, right? So that's going to, if I put in the constant term in the front, so that's going to be k is equal to 0 to n, and choose k, right? A to the power of n minus k, and then x to the power of k. So as you can see, this is pretty nice because I don't need to worry too much on the degree of the x, where I can play around with the binomial coefficient and then the constant coefficient. This is going to be ascending form. And then it's good for unknown degree. Okay, if you have a unknown degree, such as in this problem, maybe it's better for you to work with the ascending form. So try to put the constant in the front. So for this type of problem, question already puts the constant in the front, but you should be aware, it's because they want to talk about how we can find the n, okay? And for this problem, what I would probably do is just use the simple fact that the 1 plus x to the power of n is the same as 1 plus nx plus n minus 1 over 2 x squared. And then, if I go for the cubic, I need to go n minus 1, n minus 2 over 3 factorial x cubic, right? Then I would probably use that, right? But make sure this one was x. However, for the expansion in this problem was an x over 2, so you might as well change this as an x cubic over 8 by replacing the x with x over 2. Okay, the rest I will leave it as an exercise. But why am I talking about this one? If you have unknown degree that you need to find, ascending power, put the constant in the front. Usually it's a given, but if it's not, make sure that yourself does the putting the constant in the front. Okay, that's good. Very, very popular for paper 1, paper 2, depends on. There are many rules, it's worthy. Anything with worthy problem, we don't like it. And let's have a look at some of the skills that we need. How to translate that sentence into something combinatorics. Is it going to be with order, without order, etc., etc. Let's talk about that. Right, love this problem. Right, so here we are selecting. Every time you have something of a selecting or choosing, doesn't matter if you chose A person or B person first. Just depending on how many numbers you choose. So for that involves with combination, right? That's important. So here it's going to be something with the combination. I think that A, B, C are pretty straightforward. So I will leave that as an exercise. But maybe I'll have a look at something with part D, right? Why? Because in this problem, given that, we're going to talk about that more later in topic 5. If it's something with the given that, I want you to use conditional probability. Right, and also here, blah, blah, given that Fred is selected, then you go for it. But here, it says, what about the case that I include Tim or Anna, but not both, okay? So for example, imagine, let's have a look at this one. We have 6 boys and 5 girls in a tennis club. A team of 2 boys and 2 girls will be selected to represent the school in a team competition. Okay, so I need to choose people, right? I need to choose them. And for example, if I have to choose or not choose a certain person, I will use the following. So imagine that I want to choose Fred, but no Anna. Okay? In that case, what I'm going to do is I will call one as Fred, and I choose him. Okay? Now, I need to still think about the boys, right? So how many boys? 6 boys. And I need to choose 2 boys. I already chose Fred. Oh, sorry. Are we talking about the team? Doesn't matter. Let's just say that we're talking about Fred or Anna, okay? Fred, I chose Fred. And 1, I chose Fred. But I'm not going to choose Anna. But before talking about Anna, let's finish the boys. So 6 boys. I'm going to go by 5 boys. Out of them, I need to complete the 2 sets. So I'm going to go by 1 more boy, okay? And it's a product principle. If you have a language of n, it is all about the multiplication. Anna, I'm going to think of it as a 1 person Anna. I don't choose her, so 0. And then, out of how many left? 4. I need to choose how many? 2. So that will be the case that I choose Fred but no Anna. Okay, so the rule that I'm trying to use here is I'm going to use this one choose something as a selecting person or not selecting person. Okay? Sure. Very, very good. Here, how many different ways can be seated? Seated or allocated or order. It is always about, what is it? Permutation. It is always about who? Permutation. In this case, what I want you to read is that we have 10 seats in the room. There are 6 people. So what you're doing is you're allocating those seats to people. Okay? So simply, for the first one, without any restriction, I'm going to just go 10 permutate 6. Okay? I'm allocating those seats to 6 people. So that's going to be the way. But in part B, there's a restriction. I want you to pause the video and take your time reading it. Let me just get away from the screen so that you can read. Very good. In a group of 6 people, right? There are 3 sisters who must sit next to each other, so they work as a group, right? This type of sense of a group is also very popular, right? So what I'm going to do is maybe I will create 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then I probably will consider 3 together as a sister, as a one group, and I want to probably talk about how many ways it can move around. But if you think about, there aren't that many. How many is it? 1, 2, 3, 4, 5, 6, 7, 8. Many of those group can move around those seats. Okay, so that's my first event happened, right? So okay, 8 many of them. Okay, well, you know what? Let me not get the multiplication sign here, but let me go to the second phase. What is it? In the group, they can permutate. The sisters can permutate within the group. So what do we do for the order? We use a factorial. So 3 factorial is what I have, right? We got to think about who also. You're absolutely right. The remaining people, right? So what you want to do is, how many seats left after having set the 3 sisters? 7. So I'm going to, what is it? Allocation. It's a permutation. So for the remaining people, I'm going to go by, what is it? 7 permutate 3 is what I'm going to do. And it's happening at the same time, so it's the language of n, product principle. So we're going to multiply all that. Okay? My favorite question. This is a beautiful, beautiful question. I want to get away from the screen. I want you to take your time reading this, okay? Very good. What is this problem about? The previous one was about grouping, right? It's grouping 3 sisters and consider it as a one group, one object, and permutate within the group, right? That was what was about. But for this type of separation problem, right? I need to separate who? Biology, chemistry, physics. I need to separate them. You may attempt, okay? You may attempt with exclusion principle. What was exclusion principle? It was total, right, minus specific. Right, that was the exclusion principle. I would probably do so if it's a separating 2 objects, okay? If it's a 2 object, I will probably use the exclusion principle. But if it's more than 2, such as 3 papers here, I will not use it. I will not use it. Let me briefly talk about why I wouldn't use such. Why not? Because if I look at the, talking about the exclusion principle with 3, what I can do is, okay, from total, how many paper was it? It was 18 papers. So, I'm going to go with 18 factorial. Maybe I'm going to get rid of 2 together and 3 together, right? Because I want to get rid of every single case then they're together, right? So to separate them. But it's not that simple, right? Because if you think about 2 together, suppose, I'm talking about biology and chemistry together. Why I'm talking about that permutation, accidentally, what can come next? Physics can come next. So accidentally, this involves with 3 together as well, right? And then you might say, how many cases are redundant? I don't know, you got to think a bit more. Also, not that I have to also, not to mention that I have to think about 3 together. So it's repeating, okay? So I don't like it. So every time I have more than 2 objects to separate, I will use the different method. What is? Attack on the gap, not on the tight end, okay? Attack on gaps. That's what we should do, isn't it? Okay, so what I want you to do is permutate the remaining papers. It was how many paper was it? It was 15 papers, so I'm going to permutate them. So let's suppose that we have arranged them, okay? What you then get is the gaps between them and on the corner. So what I have here is, those are the gaps that I have created, all right? And how many gaps do we have? 1, 2, 3, 4. Yes, you're right. There are 16 gaps, okay? And think about it. If I want to guarantee these papers separated, physics, biochemistry, what do we have to do? We need to allocate those papers in these gaps, right? In that case, there is going to be always 1 or 2 papers that are not relevant to the science. That's great. Allocation, what do you remember? You're right, permutation. So it's going to be 16 permutate 3. And it needs to happen at the same time. That's going to be what it is. So if it's a separation, please try to use, what is it? Attack on the gap. So permutate the remaining and allocate the relevant into the gaps. Okay. Very good. All right. Wow. Let's talk about who? Rational power. You're going to have it. It's a new chapter, new topic. It used to be only discussed in the Maclaurin series, but now it's also a discussion a bit further. Okay? Two things to remember. Two things. The formula and interval of convergence is very important. Does it mention? Doesn't mention. Interval of convergence. Oh, wow. Let us talk about that. Okay? Sure, let's talk about the method of expanding. Let's talk about the method of expanding. There are two ways of doing it. Two ways. The first is if the problem doesn't ask you to find the general term, but only expand up to up to 3 non-zero terms or up to degree 3, etc., then you can use the following. What is? Remember this. 1 plus x to the power of n is it would be a finite series if n was a natural number, and we wrote it as a 1 plus nx plus n minus 1 over 2 x squared, on and on and on, and goes up to x to the power of n, right? That was it. But with the rational power, it becomes an infinite series, right? So if n had been a rational number, would have been 1 plus x to the power of n will be same thing. You know what? It is the same thing. So let me use technology to paste it. Yes, I know. It is pretty cool. I will paste that. Then there you go. But I ain't going to stop. For the rational power, it is going to be infinite series. So you got to leave it like that. But when was your first time dealing with the infinite series? You're absolutely right. The geometric series, and we said that for the geometric series, two things are very important: the formula and interval of convergence. Same thing for the binomial expansion. Not only the formula, you also always have to mention about the interval of convergence. How do you find it? Think about any value of x that makes the inside of a bracket 0. In this case, it's going to be -1, isn't it? And it's going to be always x between that absolute value of that and negative absolute value of that. So in this case, it's going to be between -1 and 1. Remember that, right? We already know. We've been practicing a lot, but just specifying that, knowing the formula and the condition of convergence, very, very important. So for this one, maybe I would do, what is it? 1 plus x to the power of half, and your n is going to be half here, x is going to be x, then good to go, okay? For this one, no problem. What do we have? It's going to be a 1 minus x squared to the power of -half. So what is going to be your n? It's going to be -half, and substitution is going to be with a negative x squared. Remember, I got to put the positive x there. So substitution would have been 1 plus, let me write in red, negative x squared to the power of -half is what we see. Okay? That's great. Let's move on. Oh, well, of course, you should explain yourself. I'm not going to do it. But just talking about the technique. And yes, what is a strange here? And think about it. You're absolutely right, too. Don't forget, if you don't have a constant being 1, try to factorize it and then apply the formula. So here, what I would do is probably do this as 2 plus x to the power of -half. All right? Factorize by 2. So it's going to be 2 to the power of -half. 1 plus x over 2 to the power of -half is what I've got. Very good. Okay? And then, yeah, you can just expand it. I think I have it. It's okay. Let me just use that. Oh, sure, you know what? Just like the natural power, you have also a case with the binomial expansion with the product with the rational power. So what I mean by that is that for this one, I would describe this as a 1 plus x to the power of half times, what is it? Let me write in red. Yeah, you're absolutely right. 1 minus x to the power of -half. So you were going to expand both of them and to the distribution. You don't have to distribute all that because they're only interested up to the degree 2, so only multiply with them, okay? Sure. Also another new chapter, right? It wasn't in the syllabus before, but since the new syllabus we have it, so of course it's gonna come up, isn't it? And then very, very likely to associate with either the function sketching or integration, isn't it? So make sure you're able to do the partial fraction well, okay? And I think I brought a beautiful slide here. So yes, if it's a linear vector, I'm gonna separate it. You write the utmost degree of a remainder is gonna be 0. So make sure you put the constant part there, okay? The next one was what is it? If it's a perfect square, it's a repeating, okay? So it's gonna be linear, constant, quadratic, constant. Even though it's a quadratic, it's a perfect square, so I'm not gonna put my remainder as a linear term, but only the constant. Make sure you remember this. For cubic, same thing. If this is a cubic power, repeating with linear, quadratic, cubic with just the constant remainder is what I'm gonna write. Okay. Boom. But if I've got a quadratic term is not perfect square or not factorizable, the remainder must be, yes, the linear term. Okay, that is great. Okay, for cubic linear, it says linear factorization, no problem. Constant over linear, constant over linear, constant over linear, right? Good to go. So if I quickly give you an example, it is factorizable with the x minus 2 and x plus 3. What do? We simply just put the constant and just solve the simultaneous equation. Remember that? No problem, you can find it. I am not going to spend much time on solving it, but only discuss the techniques that you need for a partial fraction. Okay? You know how to do it. Okay, it's fine. Okay, for this one, what do you need to remember? You're absolutely right. I've got a perfect square, isn't it? So it's going to be constant of a linear plus constant of a perfect square. Boom, there you go. You can find the ABC using the simultaneous equation by putting them back together, okay? Which I will leave it as an exercise for you to find the ABC. Okay, superstar. Complex number analysis. Okay, great. So let's talk about what sort of a skill set I need to have. This chapter 1.12. Let's have a look. Sure, so now what I want you to do is be comfortable with the Argand diagrams, because Argand diagram is really just talking about the complex number in vector. Okay, that's what really is about with the Argand diagram. So if I have for example, a form of a negative 3 plus 0i, so that's just same as a negative 3 comma 0 here. Okay, then what would you do to find another coordinates? You're absolutely right. I would probably use some of the geometry here, using something of a congruence, isn't it? Thank you. Then you can accordingly find all the coordinates because they're congruent, right? And then what are the other values that we were given? A was a negative 1, 4. So then the rise of a run is going to be the same. Then you can use the same distance on the other part. So why I'm making this example for this chapter here? Yes, work complex number like a vector. Cartesian plane, a Cartesian form is really just talking about the coordinates, okay? Very good. Another one, try to simplify as much as you can, okay? What I mean by that is whenever I see this exam, I would say, oh, okay, I've got a complex number in the bottom. I don't like it. Rationalize it. And for that, the formula was 1 over z is the same as 1 over z. Maybe I'll write better. In with z times z conjugate. And what was the product of complex and conjugate? Very good. It was a modulus of z squared and then z conjugate. Okay. So I would try to simplify before solving it, right? So for example, here I know 1 over 3 plus 4i using that formula. And what's the modulus? It was a 5 and square it, so 25, 3 minus 4i. Okay, I will always simplify first before doing any rearrangement, especially if I have a complex number in the bottom. Okay? Then the rest I will leave it as an exercise. But please make sure you simplify. Okay? Sure, you know, there are many proof questions. With who? Complex number in Cartesian form. Well, I don't like it. You know, the Cartesian form would be the least form I would use for proving things. Okay, but sometimes the question insists you use it, you use it. But when you do so, again, what do you have to be very careful about? Do not put complex number in the bottom. Okay, don't put the complex number in the bottom, and also grow the habit of what? So, 1 over z conjugate over modulus of z squared. And what was number 2? You're right. Always try to distinguish between the real part and then the imaginary part. Okay, make sure you always separate them. Okay, this problem I think is a very nice example. Also, there's an extensive algebra, but at the end of the day, things cancel out a lot, and separating the real part and imaginary part helps you a lot. Okay? But way more important of this part of contents, because it talks about way more popular form of a polar and the Euler form. Let's talk about what sort of applications we can come up with them. Okay? Sure. You know what? I would just get rid of the 2 here because I would talk about them more in Timecodes theorem. But yeah, you're right. You know, whenever I'm given things like that, I like to put them in the polar form as a modulus times c is the argument. So here, you know, complex number is really just strong revision. With who? Trigonometry, isn't it? It is really just strong revision with trigonometry. So make sure that you are able to find the argument and identity a lot quicker than, I don't know what I'm saying here. Let's have a look at the modulus here. So modulus is going to be square root of, what is it? Sine square. Can't be bothered to write all that, so okay. And then if I expand the square of that, it's going to be 1 minus 2 cosine plus cosine square. And voila. And, you know, I can use the Pythagorean identity on them, isn't it? So if I did, it's going to be 2 factorize 1 minus cosine theta. Okay? And here you might say, oh, I'm comfortable with this. I'm fine with that. I'm going to move into the argument. I don't want you to. Okay? From now on, every time you see the 1 pair with cosine, I want you to be very happy because I can use the double angle of cosine to cancel things out, isn't it? Right? Very good. So what am I going to do? It is going to be, what is it? Square root of who? 2. Boom. Yes, double angle of cosine. Who are you going to take out to cancel things out? 1 minus who? 1 minus 2 sine square. Yeah, you're right. Theta over 2. Right? To use the double angle, we had to express the theta as a 2 times the theta over 2. You know what I mean? Then I'm very happy. So things are going to be, what is it? Cancels out. Positive 2 squared, so it's going to come out as a 2. Modulus sine theta over 2 is going to be my, what is it? Modulus. Okay, very good. And also, let's talk about the arguments. If I call the argument of that complex number as a phi, then tangent phi is who? The imaginary part over the real part. Remember that? Very good. And what does this remind you? Do you know? You should know, right? Very good. It reminds me of the half angle of tangent. Okay? If you ask me, oh, how do you know it? Well, you should know it. And I'll leave it as an exercise for you to solve it. But very popular with the half angle of a tangent and cotangent to work with the, you know, converting this Cartesian form into the polar form with the complex number. So it is very important for you to memorize it. Okay, what are the other popular form of a tangent half angle? Is also another one is a sine theta, I think, yeah, over 1 plus cosine theta is another one. Okay, and another one is a square root of a 1 minus, I believe, something with the cosine. You can look up. Okay, but yes, therefore I know that the argument is simply theta over 2. So this sine theta plus 1 minus cosine theta is going to be 2. modulus sine theta over 2. What is it? Cis. The argument was who? Theta over 2. We'll be good to go. Okay. And obviously there's a benefit of that because for the higher power 2 later on, you can do the DMT, right? So the whole purpose of this is be comfortable being able to convert things around between the Cartesian, polar, and Euler. Okay? And that really, really goes with who? Trigonometry. You must be master of it. Master of trig. Anyways, let's move on. Oh yeah, so same argument here. I will leave that as an exercise for you to do modulus and argument form, but what I want to just briefly talk about is just the argument. Okay, let me just talk about the argument here. So, modulus, I'll leave it as an exercise, but for the argument, if I call the argument of a, oops, why is it so? If I call the argument of this complex number as a phi, okay, then a tangent phi, what was it? Imaginary part over the real part. So what I have is a negative sine to theta over 1 minus cosine theta. Okay, it's a little different from the previous one. It was a, sine over 1 plus cosine for the half angle of a tangent. For this one, my friend, it is half angle of a cotangent. Okay, so this becomes negative cotangent theta right away. But I don't like it. Why not? Because it's not something of a tangent I want to associate with tangent equal to something equal to tangent, so that I can take out the argument together. But it's okay, right? You can convert the cotangent into who? Absolutely right. Cofunction identity. Complementary angle. This is a negative tangent pi over 2 minus theta. You should know it, right? And then tangent is odd function, so I can take the negative inside because it's an odd function. Tangent theta minus pi over 2 is what I have. So why I'm making this example from the exam question? Because I want you to be aware, nasty. So I might use a lot of trigonometry, and among them, half angle of a tangent or cotangent, very popular example to come up with. Okay, so the argument here is going to be theta minus pi over 2. Easy peasy, lemon squeezy. Okay, so we talked about the Cartesian form and how we have to be always aware, not having the complex number in the bottom, or distinguish between the real and imaginary. Number 2, polar form was all about the trigonometry. Number 3, the Euler form. Okay, Euler form tends to be a lot algebraic. Okay, so that means you use a lot of algebra, something like the exponential equation, or like this, the geometric sequence and series. So the only thing that I really want to talk about is maybe talk about the expression of the infinite series. Okay, maybe I would talk about that. So how we can talk about that is the following. Let me just copy the image. Oops, no, not this one. There you go. I'm going to copy that page. And I'm going to say yeah. And then it's going to pop up. How? If I unclick that, I'm going to make a new slide. Using the geometric series, it's going to give you who? The first term over 1 minus 1 over 3 e to the power of I theta is what I've got. But what do I want? I don't like having fraction in the bottom, so I'll multiply by 3 top and bottom. I have a 3 over 3 minus e to the power of I theta. Okay, that's great. But also, I don't like having complex number in the bottom. We mentioned that already in the Cartesian form. I want to multiply the conjugate, and when you multiply by the conjugate, I don't want you to make silly mistake. The conjugate of that complex number ain't 3 plus ei theta. It's not the conjugate of the bottom, right? The multiplying the negative in between is only working for who? A Cartesian form. But if I take the, 3 minus e to the power theta conjugate, you really want to just take the conjugate of the complex number, right? 3 wouldn't be affected. So this is going to be 3 minus e to the power of negative I theta. Remember that I'm only multiplying the negative on the argument for the polar form and then the Euler form for the conjugate. So I'm going to multiply by who? 3 minus e to the power of negative I theta over 3 minus e to the power of negative I theta. That's what we have, right? And then you can expand and blah, blah, blah. But I would probably expand only the denominator with you, okay? How? It's going to be 3. Oops. It's going to be 9 minus 3 e I theta plus e negative I theta. And then, multiplying that will be e to the power of 0 plus 1. So I've got 10 minus 3 e I theta, e negative I theta. But here's the thing, I want you to remember this. What do I want you to remember? Complex number times conjugate was modulus of z squared. Okay. Another thing that I want you to remember is complex number plus conjugate must be the real part. Okay. And what would be the real part of that? You're absolutely right. It would be twice of the cosine theta. So that is going to come out as a 10 minus 6 cosine 2 theta. The rest, I will leave it as an exercise. Okay, let me go back to the slide. Gone with the wind. Okay, then let's talk about the application. Very, very important. Right? 3 major applications with the complex number. What is it? DMT, roots of unity, and fundamental theorem of algebra. We must be very comfortable with the applications, okay? Sure, one of the applications of the DMT is to convert something of a linear power into higher power of trig form. Sounds very fancy, doesn't it? Let's talk about what I mean by that, okay? Let's talk about what I mean by that. So I'm not going to solve the entire question because it's pretty lengthy, but I will talk about only the techniques that you should remember. Okay, what I mean by that is the following. Let me just copy that. Boom. Very good. Okay. So on this one, every time you want to somewhat make the sine 6 theta with higher power of trig, what you want to do is to use the DMT. Okay, so how do we use the DMT? Is the following. In complex number questions, you see a lot of cosine somehow, or something of a sine that really is asking you to involve either the real parts or imaginary parts. So here, for the sine 6 theta is probably to associate with who? Imaginary part is likely to work with. Okay, let me talk about it. Let me tell you what it is. So what I want you to do is start with just conventional. You know what? Let me quickly write in here. So let's go with cosine theta plus I sine theta to the power of something. Okay, but that depends on the coefficient. Here I have a 6 theta. So I would take what power? Oops. I would take a 6 power. Let's go with that. And I'm going to expand it. Okay? I'm going to expand using 2 different methods. First, our typical method with the complex number, the DMT. So let me go with the cosine 6 theta plus I sine 6 theta. Okay, that's what I have. But what you can also do is to use the binomial expansion. Let's do that. So if I use the binomial expansion here, k is equal to 0 to 6, 6 choose k, cosine theta to the power of, let me write in red and erase all this rubbish. Okay, so 6 minus k times I to the power of k sine k theta. Okay, that's great. And I'm going to compare. And yes, you're right. What we wanted to get was a sine 6 theta. So very likely that I'm going to involve the imaginary part. Okay, I want the imaginary part to be the same between these two, even though it's a different method. The output must be the same. And to discuss the imaginary part for the binomial expansion, I don't need to expand all that. But I'm going to only expand with who? When the I survives. And how do we make the I survive? When the k is odd. So 1, 3, 5 is going to be the only one that I'm going to associate because that's going to be the imaginary part. And make it as a sine 6 theta is going to be the answer for that one. So here we have, what is it? The sine 6 theta is the imaginary part from the DMT. And I'm going to take out the 1, 3, 5 from the binomial expansion and make them equal to, because the same imaginary part. So it's going to be 6 choose 1 cosine 5 theta sine theta. What is it? Minus 6 choose 3. What is it? Cosine 3 theta sine 3 theta plus 6 choose 5 a sine 5 theta. Okay. If you ask me, oh, where did the I go? Well, you know, they're the imaginary parts, so I just got rid of it, right? Because it's the same parts. Okay? And then you can plug it in. You can divide by the sine theta and then work with more trig identity. I'll leave that as an exercise, but I wanted to show you what is lower to higher. If you want, you know, it applies for the cosine as well. You know, something of a cosine m theta or sine n theta. Okay, for that one, just, you know, for the first one, I will do cis theta to the power of m. Okay, and compare what real parts of the one from the DMT, which is going to give you the cosine m theta, and one from the binomial expansion. Okay, same thing for him. For that one, I'm going to use cis theta to the power of n. Okay, very good. So that was lower to higher. Something of a degree 1 in the multiple of higher power is that. But of course, we can work conversely from higher to lower. So let's check that. Sure, a very beautiful problem here. So, you know, let me copy that also. Sure. Yes. Boom. Very good. Okay. So as you can notice, you know, it's the higher power. It's now the power of 4. And what I want to do is to make into something of a linear term like the cosine 4 theta, cosine 2 theta, and the constant 3. So what do we do? So every time you do the higher to lower, I want you to use the following identity. It's a very, very popular identity. What is z to the power of n plus 1 over z to the power of n is the same as 2 cosine n theta. Okay, I will leave the proof as an exercise. I mean, you know, the question usually asked starts with prove this, and of course you should practice it. Okay. So if I had that identity, what I want you to do is to start with the n equal to 1. Okay, start with the n equal to 1. If you did, then you're going to have a z plus 1 over z is equal to 2 cosine theta. Okay? And what you see here, you know, I wanted to get the cosine to the power of 4. So now what I'm going to do is to raise this to the power of what? 4. Okay? That's what I would do. All right. Then what do we do? On the left-hand side, I can do the binomial expansion. You're absolutely right. Let's do that. So if I use the left-hand side and expand with the binomial expansion, that's going to be sigma k is equal to 0 to 4. 4 choose k. Boom. Z to the power of 4 minus k times z to the power of negative 1 to the power of k. Okay? That's great. So let's simplify further. Sigma, blah, blah, the same thing. But z to the power of 4 minus 2k is what I have. And what I like to do in this time is actually expand them through. Okay, let me try to expand them through. Okay. If I did, it's going to be 4 chooses 0. Z to the power of 4. Beautiful. 4 choose 1. Z2. 4 choose 2. That's it. 4 choose 3, z negative 2. 4 choose 4, z negative 4. Okay, so that's what I've got. Okay, so now what do we do? I can actually associate with this identity or even this identity for the rest of them, right? That's great. So I can make a symmetric comparison. Okay. Then I have, what is it? Z to the power 4 plus 1 over z to the power 4. Right, that's great. Plus 4 choose 1 is the same as 4 choose 3. Remember, n choose k is the same as n choose n minus k. Do you remember the another identity that I want you to memorize? The Pascal's identity. It's not relevant to this problem. I'm just saying it because it's an exam prep, isn't it? So n minus 1, k minus 1, n minus 1, k, same as n choose k. Okay, another identity that I want you to memorize is addition. But anyways, it's not relevant to this, but good thing to remember, memorize. So 4 and then z squared, 1 over z squared, and then 4 choose 2. What is it? 4, 3 over 2. And what can you do? These guys, I can use this identity to substitute. What's going to happen? It's going to be 2 cosine 4 theta plus 8 cosine 2 theta plus boom, 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 6. Okay, that's great. Then, that was the left-hand side. What was the right-hand side? The right-hand side was, boom, it was 16 cosine 4 theta. And they should be equal to each other, isn't it? Let me quickly select that. That we should be equal to each other. Then you can convert, right? By dividing this by 16, you can have that identity. And this method is a good combination with integration. The question can ask, hence, integrate, let's say, from 0 to pi over 2 cosine 4 theta d theta. Then obviously you can substitute that and integrate now. We'll leave that as an exercise. But here, the point of this problem is, what is it? This question, to remind you, is if you want to do the higher to lower, use that identity. Okay, use that identity. And very good question. I'm glad that you're asking me that. What if it was a sine to the power 4 theta that I wanted to figure out? Very, very good question. Then you got to use this identity. What is z to the power n minus 1 over z to the power n is a 2i sine theta. Okay, use that. Okay, and then the rest is very similar logic. Okay, let's go to the slide. So yes, have a look at this problem. Very, very nice, but it goes with the higher to lower. Okay. All right. Let's have a look at the next slide here. So the next application that I want to talk about is the fundamental theorem of algebra. Okay. So this isn't really like a polynomial solution here, but it uses the identity that we talked about today. What is, if omega is a cis theta, then omega to the power of n plus omega to the negative n will be the twice of the real part, which is just the 2 cosine n theta, right? So you can then make a relevant substitution here, right, using the symmetry, right? So here, then I see that it's going to be, what is it, 6 cosine 2 theta minus 2 cosine theta plus 2 is equal to 0. Then you can work with the trigonometric equation here. And what I would probably suggest is to use the doubling of a cosine to make it into the quadratic form, right? So, before doing that, I would simplify first, get rid of 1, 1, 3. Then use the double angle here. It is a 2 cosine square to theta minus 1. Then you can replace that again. So that's going to be, 6 cosine square theta. Oh, my bad. It's supposed to be theta there. Let me just get rid of it. There you go. Then yeah, it would just become a quadratic form. You can solve it, right? Okay, let's have a look at the next one. So yes, the point of this slide is to talk about the fundamental theorem of algebra. And what is, if I have a complex root, I know what is. Conjugate must be a root, right? So we know that solution here is given as a negative 1 minus I, right? The conjugate is what? Minus 1 plus I. And furthermore, right, if you have a complex root, then you have a quadratic factor. From the factor theorem in real number, we've been saying if I have a root, then I have a linear factor. But for complex number, you have more than one. You actually have a quadratic. So what was it? It was a z square. It was x squared minus twice of the real part of the complex root times x plus modulus of z squared. So you should be able to come up with the quadratic factor right away, right? So for this one, what I like to do is, in fact, to use the sum of roots. So what we have here is that the sum of roots is going to be negative m. That's going to be, if you add them together, that's going to be negative 2 plus the remaining roots that I don't know, right? And then with that complex root, I can come up with a quadratic vector. It's going to be, what is it? Z squared. What was his real part? Negative 1. So plus 2z. And then what's the modulus? Is root 2. So plus 2 is going to be the complex root. And from here, we know the constant part would be negative 8. It must be a factor. So what I recognize is that times z minus 4 would be a good case. And the remaining root must be 4. And you can find m and z right away. Okay? So here, what I want to remind you is that the fundamental theorem of algebra, if I'm given a complex root, I can come up with a quadratic vector. Okay? That's great. Another application is roots of unity. Okay, if you want to work with the roots of unity, remember the formula, right? So z pop n is equal to cis theta implies z cis theta plus 2k pi over n. K is from 0 to n minus 1 integers. Okay, so we have exactly n many roots. So in order to do so, you always have to specify the complex number in polar form so that we can apply it to the formula at ease. So 216i is the same as a 216 cis pi over 2, and then you can plug it in, right, for the formula. So make sure, what I'm saying here is if it's a roots of unity problem, it's going to be using the formula. But to do so, make sure plug it into the polar form, right? And not only I think there are several things that you got to memorize. Negative 1 is a cis pi, right? Negative I will be cis negative pi over 2, right? Please memorize. Okay, so roots of unity. And then for the roots of unity, there are 3 things to memorize. Formula, sum of roots of unity, product of roots of unity. Okay, I want you to make sure you to memorize that the sum of roots of unity is always a 0. Okay, it's always a 0. And then the product of roots of unity is plus minus 1. And if you ask me how do we prove it, oh, it's pretty bad handwriting, my bad. How do we prove it actually? There are many ways of proving it. This one, I want you to maybe, this one uses the polynomial factorization, but also you should be able to prove it by using the geometric series. And the first one, I would ask you to prove this by arithmetic series. But yes, I'm just trying to point out that sum of roots of unity being 0 is a very, very popular example. And this is also a nice example I want you to take I want you to try. As I've mentioned before, I was talking about complex number. But all of a sudden it talks about the cosine. It really just associating with Associating with the real part, okay? So make sure to realize this question is going to involve some study with the real part and try them, please. But point of that slide was to indicate that, for the roots of unity, not only the formula, but also sum and product of roots, very, very popular. Okay, and then induction, right? There are many, many questions with induction. Divisibility, right? Series and sequence, differentiation, integration, composition, so many. But only a few comments that I want to make with the induction is that please be comfortable with induction because you already know the answer, right? So do not forget to describe by the basic step. The first step, it might be 1, it might be 2, it depends on the question. So for the series starting from 1, then I can find the basic step at n equal to 1, right? We can do that. But also, I want you to, go for the second step, assuming k true implies n equal to k plus 1 true. So that is, induction, hypothesis, and this is the result of proof. And it's good to know the answer, okay? We already know the answer, but of course we can't use the answer, but at least we know how to get there, isn't it? So what I mean by that is for this problem, for the induction hypothesis, is going to be sigma r is equal to 1 to k, and then we have R3R will be 3 over 4 to k minus 1 times 3 to the power of k plus 1. That's the induction hypothesis, okay? And then the result to prove, write that too. You already know where you are heading. That means r is equal to 1, k plus 1, r, 3 to the power of r, 3 over 4, and make sure if you have some multiple there that it's going to be raised by 2. So it's going to be 2k plus 1, 3 to the power of k plus 1, plus 1. So we already know the answer. This is the answer that we need to get. But of course, you cannot use it. And for this one, what I can do is, if I quickly maybe erase this, is that we realize that using the sigma notation, it is going to be sigma 1 to k plus 1, ak is the same as Is the same as a sigma 1 to k, oops, my bad, I probably use r, ar plus a k plus 1, the next term of the sequence, so that I can use the induction hypothesis there. Sure, so whatever the series that we had on the left is in fact going to be same as, I will copy this, and move it there. Okay, so that plus, the next term of the sequence? Okay, it's going to be, k plus 1 times 3 to the power of k plus 1. But you realize it doesn't look that obvious, right? However, I know that it must look like that. So what it gives you a clue here is probably factorize it, whatever. I don't know whether it's going to work or not, but I do know my answer says that the common factor must be 3 over 4. So arbitrarily, Okay, even though it doesn't look so obvious, because of the induction hypothesis and result to prove, I'm going to factorize this by 3 over 4. That's what I'm going to do. Then, you get the same term here. Only term that I got to be worried about is here. But, the 3 to the power of k plus 1 is the same as 3 times 3 to the power of k. So I just want to have 3. Okay? So that means I would probably add this by 4, right? And then k plus 1 times 3 to the power of k is going to give you a good substitution, okay? And then you can work inside the bracket and then continue to prove it. But whole point of this practice is to show for the induction, it's good to write down the answer. Why? Because it gives me a clue where I'm heading. Even though I used the induction hypothesis with the next term of this proof here, it didn't look so obvious to link them. But now I realize, I can actually factorize by 3 over 4 and work more beautifully there. Okay? That's good. So, and also another comment that I want to make for the induction is that we got to be a little careful of those problems that involves more than one clue. So what I mean by that is the following. So far, applying the induction hypothesis gave you an answer. But some problem like this, such as inequality, okay? Or integration, or sometimes divisibility, might involve more than one step, more than applying just induction hypothesis actually to get the answer. Okay, so I will leave this one as an exercise. Very nice problem, but be aware applying the induction hypothesis doesn't get you the answer right away. But the actual example that I want to show you is this one, right? Divisibility question with the polynomial term, and show you why just using the induction hypothesis is not enough to prove things. So let me quickly show you that. So let me quickly copy that. Sure. So on this one, what we notice is that divisible question is always something with the multiple. So I'm going to go with it's equivalent to say n times n squared plus 5 is equal to who? 6m, where m is the integer. Okay. So that's the statement. So what I can do is you can show the basic step is trivial, so I'll leave that as an exercise. But let's go with the induction hypothesis implies the result to prove. So what I'm going to do is writing down two things, the hypothesis and then the result. Okay? So if I maybe copy, suppose n equal to k true. So k times k squared was let's say 6p1. Okay? So now it says it's divisible by 6. The aim here is n equal to k plus 1. So I'm going to go k plus 1 here, k plus 1 there, okay? And then maybe show you some sort of a integer, positive integer they say. Okay, let's try to solve that problem. Sure. So maybe I'm going to expand on the left-hand side and show that eventually that will be multiple of 6. So if I expand that one, I have a k plus 1, and then what is it? It's going to be k squared plus 2k plus 6. So that's great. And let's do the distribution. So it's going to be k cubic 2k squared plus 6k. Okay, that's great. And I'm going to multiply by 1, so it's going to be k squared 2k plus 6. So if we add them together, that's going to be k cubic 3k squared 8k plus 6. Okay, but what we should initially start is the induction hypothesis. So if I use the induction hypothesis there, which was k cubic plus 5k is divisible by 6. So That's great. So I'm going to maybe use that information here. So I can use that information here. Oops. Here and here. Well, not entire 8k, but it's okay. So if I did, it's going to be k cubic plus 5k, and then the rest is going to be 3k squared, 3k plus 6. Well, I'm going to put the 6 there. Why? Because I can now entirely factorize this by 6, because by the induction hypothesis, that was a 6p1. So I can do 6p1 plus 1. Okay. Now the only problem I have is the last two terms, 3k squared plus 3k. What can I do? Well, what you can do is to factorize by 3k. So let's do that. So it's going to be k plus 1. All right? But it's not that obvious that it's divisible by 6. And here's my point, right? Applying induction hypothesis does not solve the problem right away. It might require a few more steps, okay? And then you shouldn't be afraid of doing so, right? Sometimes it might be with inequality, sometimes it might be with divisibility, whatever. What I recognize here is that, think about this. K were in the family of positive integer, okay? And positive integer really can be categorized by two. What is it? Even and odd. And in fact, if you actually apply this case of even and odd case by case, you realize if this had been even, then case closed, because even times 3 will be a multiple of 6. If this has been odd, no problem. K plus 1 would have been even, right? So that even times 3 makes it multiple of 6. So either way, it's good to go. Yeah, right? It is divisible by 6. So therefore, you can say, aha, by since we show that the basic step works and induction hypothesis implies the result of proof true, therefore by the principle of mathematical induction, the statement is true for all positive integer. You always need to mention the conclusion, okay? Don't forget to write down the conclusion. It's very, very important. But it's a good example to show you why induction hypothesis applying alone might not solve the problem, hence requiring further information. Okay? Sure. Let's move on to the next slide. Okay, linear system. It's in the topic 1, but it's more to associate with who? Vector. It is to more associate with vector. Okay, let's have a look. All right, so what I'm going to have a look is the following. So yeah, I mean, it is a simultaneous equation with 3 variables and looks like a vector, but really it is going to work with the vector a lot more. And what I also want to remind you is this. When you have 3 variables with 3 equations, it is working what? Intersection between 3 planes, wasn't it? And the typical method you learned in school was a row reduction, right? Use the row reduction. Sure, we can use a row reduction to verify the nature of intersection, right? The unique as a point, infinite and many as a line, and no solution. So if we perform the row reduction here, what we have is a 2, 1, negative 1, a plus 1, 3, negative 2, 1, a plus 2, given 3, 1, k. And you know what? This matrix actually is hard to apply the row operation. Why? Because, you know, you got to make the a as a 1, so you're going to multiply by 1 over 8 on each. Then, you know, for example, this is going to be 2 over a, and then, you know, adding or subtracting with these is actually going to make some weird rational form. And it's actually hard to work with the algebra. But what I want you to do, what I want you to remember is whenever we try to work with the intersection between three planes or solving the three linear system of three variables is to work with the determinant. Okay? And I know it's not in syllabus. It's okay. The more the merrier, right? If I have a certain more efficient method, I'm going to always tell you to use it. You can use your row reduction here, no problem. But what I would encourage you to learn is a determinant, which is essentially the same as a cross product. You know how to do the cross product, why not on here, okay? And what I want to also remind you is that if the determinant of the matrix isn't zero, if it's non-zero, then you have a unique solution, okay? But if the determinant of the matrix is a zero, then it's a non-unique. Remember that? So for that, it can be either no solution or infinite many, which is going to be a line equation. It depends on the case. Okay? So instead of working with the raw reduction, what I want you to do is to apply the determinant, which is going to be a lot quicker for you to verify what values of A makes this non-unique. Okay? So now, if I just get the 3 by 3 identity here, and work on the determinant just like a cross product. It is a cross product. Let's see what we get. What was the identity? It was A plus 1, wasn't it? Determinant. And let's see what we get. It is cross product. So instead of I, J, K, I'm just going to use A to 1. So it's going to be A determinant. A plus 1, 3, 1. A plus 2. Minus 2, remember it needs to alternate, sign needs to alternate. Minus 2, what do we have? Minus A plus 2, plus 6. Okay, oh, sorry. I didn't mean to compute right away because I wanted to show the process. So it's going to be the determinant of negative 1, 3, negative 2, A plus 2. Okay, that's great. And for the third one, it's going to be plus 1. And then negative 1, A plus 1, negative 2, 1 is what we have, okay? That's great. So from this, what we're going to do is apply the determinant of 2 by 2, which you've been doing for the cross product, no problem. So I have A plus 1, A plus 2, minus 3, okay? That's great. Minus 2, and what is it? Minus A minus 2 plus 6. And then plus 2, negative 1 plus 2A plus 2 is what I've got. Okay, that's great. Then let's expand. So what is it going to happen? It's going to happen with the A. And if I expand, it's going to be A squared plus 3A minus 1. That's great. Minus 2, negative A plus 4 plus 2A plus 1 is what we have got, okay? And then simplifying this, trust me, better than row reduction. It is A cubic plus 3A squared minus A plus 2A minus 8 plus 2A plus 1 is equal to 0. So I have A cubic, boom, 3A squared, boom, A, 3A, boom, minus 7 is equal to 0. Voila. Okay. Now I want to find the 0. It's a cubic polynomial. And if you ask me how do I solve it, well, it's not that bad. We can do the, what is it, rational root test. Remember from the polynomial, we discussed that the solution must come out as who? Actually, I'm not sure if we have discussed, but I'll tell you now. It's going to be, if it had been a rational root, we don't know it, it then must come out as a plus minus factor of the constant term, which is 1 and 7, over the leading coefficient, simply 1. So what I'm going to do is just to plug in the 1 and see if it, plug in plus minus 1, plus minus 7, and see if it becomes a 0. And the obvious answer is obviously 1, right? So 1, 3, 3, 7 makes it 0, okay? So why is it good? Why? Because then we can factorize. Right, let's do the synthetic division because I already have the root. So it's going to be 1, 3, 3, negative 7. What do we do? 1, 1. We multiply outside, isn't it? So 1, 4, 4, 7, 7, 0 is a great answer. So we have a minus 1, a squared plus 4a plus 7 is equal to 0. So yeah, for this quadratic term, if you look at the discriminant, it is simply 4 minus 7. It's negative, so I'm not going to bother finding the solution there. Only who is possible? A equal to 1 is possible. Okay? And if A had been, what is it? 1, then determinant was who? 0. That means it's not a unique solution. I don't know if it's going to be line or no solution. I just know it is not unique. Who is going to determine whether it's going to be a line or no solution? You need to also discuss K. How do we do that? We're going to discuss it a lot later in vector. You can use now the row reduction. And if you ask me, oh, okay, now all of a sudden now we're using the row reduction. Yes, now it's a lot better because you have A. Okay, if I didn't have A, using the row reduction was nasty. But now, because I've got the A being 1, things are a lot better. Okay, then applying the row reduction to discuss the K is going to be the next step that we're going to do in vector. Okay. Sure, now we're going to move on to function. Next time. All right, now let's have a look at the domain of a function. All right, so now topic 2 is functions and equations. The most important part is the function domain. Okay, make sure you're impeccable finding the domain of functions. So let's have a look. So let's have a look what sort of skills we can have from the topic 2. All right, so 2.2, 2.5 is all about the domain and range. What I want you to always be able to do is to be able to derive with the parent function. You know, there are many different types of parent functions, square root of x and whatnot, logarithmic function, exponential function. We should be aware what their domains are, right? So if I look at this and I want to find the domain, largest possible domain for the square root of whatever the composite function, you now know that you are supposed to solve the inequality of a pi over 4 minus arc, is it cosine or sine? Okay, arc cosine x bigger than or equal to 0. You know, that's what I want to solve. And when I'm solving it, some of the questions I wouldn't go too much in details because the point of this video is to help you to be reminded what skills we need, such as solving inequality, right? Oh, okay, so square root of blah, so I know inside has to be bigger than or equal to 0. And for this one, I will briefly talk about, for solving inequality, it's usually sign diagram or sketching. And for this one, I would encourage you to sketch. Do not composite or change the form of a function easily. So what I mean by is the following. So you may, you might try this by, okay, so by after the rearrangement, I have a pi over 4 bigger than or equal to arc cosine x. And then you might say, okay, I'm not so familiar with the arc cosine, so I might as well just composite by the cosine, you know? And then realizing, okay, that gives me root 2 over 2 bigger than or equal to x. Oh, voila, then I've solved it. Well, it's incorrect answer, right? So I want you to be very careful when you square things or composite with the cosine. I don't want you to do it unless you're maybe working with equation, not with inequality. And especially compositing with the cosine is very dodgy. Why? Because cosine is a decreasing function from 0 to pi, right? It's a decreasing function. So I don't like working with the, compositing by the cosine. But instead, what I like to do is just sketch the inverse cosine. So if we were solving, what was it? Pi over 4 bigger than or equal to arc cosine x, okay? And for that one, I'll just sketch this. And if you ask me, do I have to memorize the shape of arc cosine x? Yes, you have to, right? We have to. Very good. So we know that it looks like that. And domain was defined from, where is it? -1 to 1. Make sure you memorize that too. and understand that, right? The range is also is going to be from 0 to pi. And then the y-intercept would have been pi over 2. Right, that's great. And now I'm comparing with who? Pi over 4. Okay, so I'm going to then sketch the pi over 4, the horizontal line like that, right, indicating that is a pi over 4. So only this this interval is the one that I'm going to solve it for my inequality. And intersection was, as we have done, it was root 2 over 2. So that interval is going to be, what is it? Root 2 over 2 and 1. Okay, so why I'm talking about this? Because yes, composite function. Remember the parent function, such as the square root of x, domain has to be bigger than or equal to 0, so that induces the inequality of inside function. Solving inequality sometimes involves a sign diagram or sketching. Okay, that's great. Let's move on to the next one. Oh, I love this problem. Find the inverse stating its domain. So maybe finding the inverse, I will discuss that a bit later. But I'd like to talk about when you have to find the, what is it, the domain of the inverse function. Because, you know, you can directly find the, what is it, inverse function and find its domain, or use the original function, right? So we realize that this is in fact the same as who? Range of who? Of the original function. So, you know, if, all right, so this question asks you to find the inverse of it, but let me just get rid of it, right? What if it asks you just to find the domain of the inverse? Then I wouldn't necessarily find the inverse form, but just work on the range of the original function. And if you ask me, how do I find the range? Oh, well, it's from this graphing, okay? So I would just quickly graph this and get the sense of the range is going to be. And if you ask me how to sketch this, well, you know, this is our typical sigmoid shape, but, you know, if I may maybe start with the 1 plus e to the power of negative x, where you know that it's a exponential decay with the horizontal asymptote of who? 1, right? Very good. So I'm going to go with the horizontal asymptote of a 1, right? Very good. And it's going to be decay. Brilliant. Now, what are we going to do? We're going to flip it, right? We're going to flip it. How is going to look like then if we flip it? If we do the reciprocate, it is going to look like this shape with the same horizontal asymptote, right? And it's kind of expected, you know, this is something that you learn in differential equation, right? The logistic growth. And if I send x to, what is it, positive infinite, y goes to 1. So we attain the horizontal asymptote here. If I send x to negative infinity, y goes to 0. So we have a horizontal asymptote of y equal to 0. So from this, I know my range was who? Between 0 and 1. Aha! And therefore, that's going to be the domain of the inverse. So inverse function will be defined from where? 0 to 1 open interval. Okay, so the reason I put this example for that chapter is because when I talk about finding the range of inverse, I will do the domain of function, vice versa. Okay. Before I move on, yes. Also, one comment here: if you want to find the intersection between function and inverse function, you might try to see their intersection directly, or you can just simply do, what is it, function f(x) equal to x. Okay, you don't necessarily have to put the inverse because of the stereosymmetry. By what is it, y equal to x, they must intersect, you know, at the y equal to x is another comment that I want to make. Okie dokie. Anyways, I will discuss that more when we talk about the inverse function. Let's move on to the next slide. Great. Why I came up with this one? Because not only talking about the domain, but also the range of a composite function. Very, very important. What is range of composite function? Okay. What I want you to do is the following. If you want to find the range of a composite function, I want you to draw the composite function diagram. And what is a composite function diagram? I'm going to go with the domain of G extending to range of G. Okay. And then what am I going to do? Domain of F extending to range of F is what I have. And for the composite function to exist, you already know the range of G must be subset of domain of F. Right? Very good. I want that. Okay. So that was to find the domain. Okay. But now I want to do the range. And the range is going to be, what I want you to do is to sketch the outside. I want you to sketch the outside function. So what I mean by the outside in this case is the one is given on the left, the f function. So here, if I consider this is a composite function, this is a square root of x composite by the rational function, isn't it? And for me, the outside function will be the square root of x. Okay, I don't know why it's not in yellow. Let me put it in yellow. Okay, so that is what I have, and I want to graph that. Right? Let's try to graph that square root of x. That's brilliant. Right? So that's what I have. And now what I want you to do is use the range of inside as input is what I'm going to do. Okay, what do I mean by that? Well, let's have a look at the inside function. On this case, it was a rational function, isn't it? His range is, what is it? All real, except, what is it? Horizontal asymptote is -1. But of course, I'm not going to use that, right? Because the domain was restricted for this composite function to exist. The domain of that was 1 minus x over 1 plus x bigger than or equal to 0, right? And if I do the sign diagram with the -1 and 1, and then -1 being the vertical asymptote, right? And let's try to plug the intervals, right? If I plug in 0, I get positive, minus, minus, right? So I get the bigger than or equal to 0 only within who? Within -1 and 1. So in that domain for the rational function, it's a bit tricky. Let me quickly sketch that for you. For the range, for the restriction, I will show you more clearly by graphing it. And vertical asymptote was -1. And the horizontal asymptote was -1 too. Okay, and x-intercept and y-intercept are 1 and 1. Right, that is brilliant. So we have a function like that. And now, remember, we restricted from -1 to 1 only. So I'm going to only indicate the function from here to here. Right, so that is from the vertical asymptote to the x-intercept. And then if you look at the range, it looks like what? Only bigger than or equal to 0. That is brilliant. Okay? So the range of that g on the composite function was bigger than or equal to 0, except, remember, there's a horizontal asymptote that I can't have. Right? What was it? It was sorry, it was -1. I don't have any restriction for that. No problem. So bigger than or equal to 0. Right? Just bigger than or equal to 0 is fine. Okay? Right. So then, as you can see, what I would do is just going from 0 to infinity all the way is what I'm going to do. Okay? So for that one, everything is defined there. So for my range of a composite function is also going to be, what is it? From 0 to infinity. Okay, so that's going to be the range of the composite function. And you know what? It's less interesting. It's a little bit boring there. I would have liked it if it had a positive horizontal asymptote. Okay. Well, in fact, you know what? Let me quickly show you. Let me quickly show you one more example to this. Okay. Let me quickly show you one more example to this. So what I mean by that is, Sure, let me copy that function there. Sure, so for that one, what I wanted to talk about was, what if we had a positive horizontal asymptote? So let's say I had a square root of what? X plus 1 over x minus 1. I want to talk about his range. Okay, let's say that I want to find the range of this. Okay, and first of all, if you want to find the range, you need to come up with the domain first. So I'm going to go what? x plus 1 over x minus 1 bigger than or equal to 0. So that's what I'm going to do. Let me do it quickly. So it's a negative 1 and 1. 1 is a vertical asymptote. If I plug in 0, minus, plus, plus. So the domain is going to be, what is it? Less than or equal to negative 1 or x bigger than 1. Okay? And for the range of that x plus 1, the range, therefore, is going to be, what is it? From 0 to infinity, except, now the horizontal asymptote is 1. Okay? So that is the range of the inside function in this composition. This is a composite of what? Square root of x, composite x plus 1 over x minus 1. Okay. Why have I brought this example comparing to this one? Is because this now, horizontal asymptote actually matters. Okay, this matters now. How? Well, we said now if I want to talk about the range of the composite function, you're going to sketch the outside. Okay, let's sketch the outside. How? Square root of x, right? No problem. So I've got a square root of x like that. That's great. Okay. Now, hear me out. It's very important. I'm going to use the range of inside function as an input, as a generator. And he was defined from 0 to infinity, except, right? Except, very, very careful here, except 1, right? So I'm going to make it as an empty circle, right? So that part cannot be defined. Okay, you got to be very careful. All right, so in that case, right, if you look at the range of that composite function, you're looking at all the output except at 1. So it's going to be, what is it? Range of the composite function is now going to be from 0 to infinity except the square root of 1, which is simply just 1. Okay? Imagine that horizontal asymptote had been, imagine the following function. In such case, I would say, okay, the range was from 0 to infinity, except for who? 2 square root, okay? With a similar reason. You can try this by yourself and see what you get. But, for the range of a composite function, you got to be a bit more careful, right? You got to use the range of inside as an input and then put it into the outside function. In this case, it was a square root of x, okay? Very good. So another skill that I would encourage you to memorize. Well, not memorize, but understand, right, of composite function. Okay, that's great. So sure, then we go more on the composite function and the inverse function. Easy peasy, lemon squeezy. Okay, for this one, I chose this one because what matters a lot? Sketching matters a lot for finding who? For finding the range. Hear me out. It says, right, domain of the inverse function. I would rather go with what? Range of who? The original function. And here, the hx given to be the composite function, no problem. I would just composite right away. The f goes inside of g, so this is a 1 over e to the power of x squared plus 3, okay? And if you ask me how to sketch this, well, you don't have to sketch the exact points. Well, sometimes they ask you to find the extremum, maximum, minimum, local maximum, minimum, inflection points and whatnot. But for things like the domain and range, what I can do is simply just graph roughly and get an idea. Okay. So if you ask me how to sketch this, is what I would do is probably go with the ex squared plus 3 first, right? And it's an exponential function. I'm squaring it super fast. It goes very, very fast. And on top of that, I'm adding by 3, so things has been translated by 3 units up, right? So if you look at the y-intercept, that's 0.4, right? And it goes very, very fast. It's faster than exponential growth, super fast. And now I'm doing the reciprocal, right? All the increasing behavior now is going to decrease, converging to 0 as a horizontal asymptote. So if you ask me how to graph for the reciprocal, then it's going to be having what? 0.25 and then things are going to go very smoothly to 0. Okay, so it's just rough figure is fine. Rough figure is fine. Why? Because you want to get the idea of finding the range. So for me, the range, remember you had a horizontal asymptote as at the 0, so I'm going to go, is from 0 to 1/4, which was y-intercept, is going to be the range of the original function, which is going to be equivalent to the domain of the inverse function. Okay? Good example. All right, so another very, very nice problem. Why I'm saying this is a nice problem is the following. Sometimes you may not have inverse one-to-one function. And it is a condition that you have a one-to-one relation to find the inverse relation. And if I just roughly sketch this function, as I remember, it looked like this. So it had a horizontal asymptote at 0, like that. Okay. And as you can see, it's an odd function. You can try yourself. It's symmetric by the origin. All right. And then the maximum I think happened at negative 2.24, something like that. You can find it. It's not on scale, but roughly speaking. And as you can see, it does not, my friend. It does not pass the horizontal line test. Okay. So what you can do is you can restrict the value of x, right? So and you know what? It gave you the interval to restrict. You know what? You could have restricted from negative a to a, okay? Or you could have restricted from less than or equal to negative a. But then they have given me the restriction for x bigger than or equal to a. Okay. So for me, what I would do is probably just restrict from the maximum, right? From the local maximum, x bigger than or equal to 2.24 is what I would restrict, and I have a one-to-one function, which then gives me what? That I can do I can actually find the expression of the inverse function. And let's do that. Let's try to find the expression for the inverse in this time. We haven't been doing that. But for that, maybe I will use the next slide. So let me quickly copy that expression. Voila. Right, let's try to use that. Let us try to use that. So, what you typically do is interchange x and y, and that works beautifully for rational function, exponential, and log. Let's see if it works for that one too. Okay, let's see. So what I like to do is simply interchange the x and y. So if I did, it's going to be x is equal to 3y over, 5 plus y squared is what I have. Voila. And let's do the rearrangement again. So it's going to be 5x plus xy squared equal to 3y. Beautiful. And I'm going to rearrange that to the left once again. So it's going to be xy squared minus 3y plus 5x is equal to 0. And you know what? Okay, so maybe I went too fast on that one. Don't worry about that. Let's try to use the typical method. The typical method I'm talking about is to group by the y and rearrange the others, right? And if I try that, for example, pairing this and that together, you have 5x is equal to 3y minus xy squared, right? That's what I have. And if I group this by y, I have 3 minus xy, okay? And then maybe I will rearrange it to the other side and claim that the inverse function is a 5x over 3 minus xy. But unfortunately, this is not cool, right? Because in my function expression, I've got y's as well. I don't like it. How can we then make it likable? Is that, from this, first of all, it didn't start off as a one-to-one relation. So no wonder that we have some strange expression that we need to involve more algebraically. And inverse function is really just finding the solution of y in terms of x. And for linear rational, it works like a charm if you just do the rearrangement. But when I have a quadratic expression, maybe that rearrangement wouldn't work well. Okay. So for this one, I will simply use quadratic formula. Okay. Let's use the quadratic formula there. Y is going to be 3. 9 minus 20x squared over 2x is what I claim as my inverse function. Okay. Very good eye. Thank you for saying it. Thank you for saying it. It's still dodgy. Okay, still not okay. Why not? Because I still have a plus minus. I don't like it. Okay. Where can I determine whether it's going to be positive, negative? You're absolutely right. Remember, my original function was like oh, there you go. It was 3x over 5 plus x squared. And he was defined, what was it? For x bigger than or equal to 2.24. And you should realize that x should be, what is it? Range of who? The inverse. So he should play the role of determining whether it's going to be positive, negative. And that, I'll leave an exercise for you. Okay, I want you to try yourself and convince yourself whether it's going to be positive or negative depending on the initial domain of the function. Okay? Very good. But let's move on. Okay, very good example again. Why? Because in this skill set, in this part, what we had to be aware was, one, restricting the domain if it's not one-to-one and make it one-to-one to be to be able to have an inverse function. Number two, finding the expression may require more than just the rearrangement is my point. Okay? Okay, so yeah, you know, for the quadratic part, for the HL student, I got nothing much to say, but except for who? Discriminant. Okay? Every time you have some sort of a number of solution, you know, or two distinct roots, you know, things like that. For example, like intersection, you know what I mean? Or touching. All that really implies you gotta use the discriminant. Okay? And let's have a look at this example here. Nice inequality problem. I want you to read this one carefully because remember, in this one, I'm not solving for x, y, because this inequality must work for every value of x. So I'm not looking for the particular value of x. Okay. If I simply rearrange this, you know, let me quickly rearrange this. How? Maybe I will probably write it in here. So, you know, if I rearrange this expression to the other parts, what I've got was x squared minus mx minus m is bigger than or equal to 0. For any value of x is what I want. And what I notice here is that this is a concave up. This shape is a concave up. Okay, so if I just quickly talk about several cases of a concave up shape, you know, you can have a floating around, touching, or passing through, right? And when you look at that, you realize, it really depends on the discriminant to claim whether it's going to be always positive, right? So that discriminant there is what? Negative, okay? This discriminant is 0, is positive for the last one. So, you know, what you're really looking at for solving this inequality is in fact to check what? To apply the discriminant on that one. And this time it's going to be m squared plus 4m. I want them to be negative is what you're solving, okay? But I wanted to show you that sometimes it wouldn't be a quadratic function. Still, if it's discussing about the number of solutions, it is talking about the discriminant. Number two, using the graph, you can determine whether what sort of discriminant I want. In this case, it needs to be floating around, no solution, hence the negative discriminant, okay? Very good. All right, so, you know, we talked about some properties of exponent and logarithmic equation above. And for this chapter, it's really just about function. I have several things to say about the function, and let's get to it. So, blah, 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 it's fine. Sure, you know, I want you to take your time reading this carefully and realize if it's talking about the exponential function, it's really just either growth or decay. It's really just about either growth or decay. And from this one, there's a hot cup of tea, very good, but it's falling exponentially. So this implies that we are working with who? You're absolutely right, decay. Okay? That's great. And as soon as you realize that it's a exponential function, what are the things that you must indicate if it's exponential function? What's its a significant feature? You're right, the horizontal asymptote. Okay, so what would be the horizontal asymptote in this question? I want you to take your time reading this carefully. You're absolutely right. The horizontal asymptote here should be, in fact, 22, the room temperature. It was very hot. It was very hot, but eventually it's going to converge to who? Horizontal asymptote. Okay, that's great. Of a 22 degree. Okay, so for me, I'm going to write, okay, my horizontal asymptote is 22. And then, whatever the constant coefficient to determine the initial temperature will have e to the power negative kt form. Why am I putting the negative k? Well, I'm assuming k is a positive here to indicate that this is who? dk. Okay, so negative k determines that it's a dk. And I know it is a dk because the paragraph says it. And then I can find the a naught using the initial condition of who? 0.98. So I believe, right? So this should be 76, right? That's great. And you can find the k later using what? Another initial condition. What is it? After the 2 minutes, it's going to be 94 degree. And how do I find the k? I'll leave that as an exercise. But what I'm trying to mention here, if you get a exponential function question in paper 1 or paper 2, please be careful whether you're dealing with the growth or decay, number 1. Number 2, what is it? What is the important thing to remember? You're right, horizontal asymptote. Okay, horizontal asymptote. Please indicate where my horizontal asymptote is. Okay? And also, yes, not only sketching the exponential function is important, so as well as the logarithms, right? Inverse function, what do you notice? Exactly. If the horizontal asymptote matters for the exponential, vertical asymptote matters for the logarithmic function. Okay, so if I have a y equal to ln x, please do not hesitate to who? Indicate the vertical asymptote. So it's going to look like what? X equal to 0, right? And then a very, very slow function, a very, very slow function is what I would do. And then why I prepare this problem is, okay, it matters a lot for sketching, for solving this problem, even though you are working with the equation. But also, they ask you to sketch this in paper 1. So what you would do is simply draw the logarithmic function with the vertical asymptote at x equal to 0. But we're going to talk about this very soon in the modular transformation. If you take the absolute value inside, what happens? Must be symmetric by the y-axis. So we're going to look like that. So ln absolute value of x is what I have, right? And yes, don't forget to indicate the x-intercept. So what I have x-intercept here is a 1 and -1, right? So now the gap here between the two x-intercept is 2. And now they are saying, I want to translate the function g by the k units to the left, where k is bigger than 2, so it's shifted to the left, right? So, but bigger than 2, so roughly speaking, it's going to look like that, isn't it? Where its vertical asymptote is going to be at -k. Then as you can see, you can find the intersection there, but absolute value is really just a piecewise function, so that left piece of the original function would have been ln -k, and then that would have been the positive piece from the gx, I believe, wasn't it? Yes. So it's going to be ln x plus k, and you can equate them, okay? But the modular transformation, we're going to remind ourselves later in the function transformation chapter. But the point of this question is to show you what matters a lot. Sketching matters a lot. And for the vertical asymptote, and the x-intercept, okay? Voila. Let's move on. Oh, yes, now, very good. Function transformation, you should be aware of describing all the transformation there, right? For example, if I have a y is equal to -2 f 3x minus 1 plus 1 from, what is it, fx, you should be able to talk about the order of transformation there easily, right? So For that, however, there are many different ways. I got it, okay? But what I prefer is to separate by the horizontal and vertical, not together. You can do it, but I don't like it because you might have to change the numbers. And if I just attack on the domain for the horizontal transformation is what I'm going to do now. And for the horizontal, what I want you to start is to work with the who? Oops. All right. Work with the translation first. Okay. And either dilation or reflection. Right. Okay, that's great. So for this one, I'm going to go by what? F of x minus 1, and then f of 3x minus 1, right? And then now I'm done with the horizontal, right? So what are we going to say? Well, for subtracting by 1, that means shifting to the right by 1 unit, okay? And then multiplying by 3 means shrinks by, or compress, right? Get smaller. Factor of 3, but it's a vector, so do not just mention about the magnitude, but also direction horizontally. Okay. You know what? You can say stretched out by a factor of 1/3. You can say that. Okay. But I don't like it because it sounds like little giant. You know what I mean? And for the range, you know, what are we going to do? For that one, now it's gonna go to -2 times the f, and then -2 plus 1 is what I'm going to do. So as you can see, for the range, I mean the outside, the vertical transformation, it's going to happen with the dilation, reflection first. And then what do? Translation. For who? Vertical. And this was who? Horizontal. Trying to write in cursive, but it's not working. It's okay. Anyways, so -2 has 2 transformation, right? The reflection along which axis? X-axis. You're absolutely right. And then multiplying by 2 is stretch out by a factor of 2 vertically. And then shifting up by 1 unit will be the next order. Okay, so that's what we do on the range. Okay, so just a brief summary on the transformation because it's important. But yeah, sure. So for this one, you realize from the cosine x, I want to shift this up to here. So what you can do is I'm going to start with the cosine x. And then what do I do? I'm going to tack on the domain first. So cosine pi x over 6. What else would you do? Now I'm going to tack on the outside because the domain is all done. I'm going to multiply by 2 first. And then 8. Okay? So again, you should try yourself how to describe it. Maybe I'm going to only just talk about that. As you can see, it's a pi over 6. Is it bigger than 1 or less than 1? You're right, it is between 0 and 1. Okay? So for me, if you multiply any factor that is between 0 and 1 on the x, it shrinks, it enlarges it, right? So I'm going to say it's stretched out by a factor of, this time, if you chose the right compression or stretching, you need to always write down the factor that is bigger than 1. So I'm going to say 6 over pi horizontally. Okay. The rest, I will leave it as an exercise. But as you can see, important for you to talk about describing the transformation. Okay. Oh yes, but you know, sometimes in the previous example, right? It's pretty straightforward what my domain and range is, right? In this function, right? But some functions, it's not that obvious. such as what? Quadratic or rational function. They are not that obvious. Okay? And you need to apply some of the algebra to make it look obvious. Okay? And for quadratic, what I want you to do is to always apply who? Completing the square. Okay? So if I have a ax squared plus bx plus c, and then you want to talk about the transformation from the x squared, what I want you to do is always try to work with the completing the square. So I'd rather go with the x a times x minus beta squared plus gamma. Then you realize, aha, that's my domain, which is going to work with the horizontal transformation, and that's my range, which is going to work with the vertical transformation. Okay, and same thing for who? Rational function. Oops. If I have a, what is it, ax plus b over cx plus d, what I want you to do is to the long division. Okay, to the long division. Then you have who? Horizontal asymptote of a over c, and then whatever the remainder with the cx plus d. Okay, so then you can see what is that's going to talk about the horizontal transformation, and then the anything else is going to talk about who? Vertical transformation. I want you to try yourself. Okay, try yourself. But if we do this quickly together, why not? So 3x squared minus 6x plus 5 is going to have 3x minus 1 squared, and voila, plus 2. Then you can describe the transformation, right? Such as x squared, x minus 1 squared. So notice that I've attacked on the horizontal inside on the domain, and the 3, and then 3x minus 1 squared plus 2 is what I've got. Okay? Then describe the transformation. Easy peasy, lemon squeeze. So why I have brought that example? Because sometimes it's not that obvious to see the horizontal and vertical, such as quadratic and rational. In that case, completing the square or do the long division. Okay? I love this problem. Okay? This is a very, very good question. It makes you think. Okay? It makes you think. So what I mean by that is the following. So if you look at it, there are, I would say, two dodgy parts. There are two dodgy parts of this problem that is not so obvious. Is that first of all, we didn't learn anything about doing the perfect square on a domain to describe its transformation. So we don't like that. Okay? But because it's logarithmic function, I can take him outside, right? That's great. So, that one, I can rewrite that as what? 2 plus 2 ln 3 x plus 2 is what I have. We notice that I factorize it just because I want to. Okay? But yeah, you should realize what is. If you look at the 2 on the range, what does it do when you have a, c times fx? It is usually talking about what? The vertical dilation, doesn't it? You usually talk about the vertical dilation. But if you actually go through the description of a transformation given by the question, it is not talking about who? Oh, sorry, it does. It does. My bad. It does. So I'm happy, okay? I'm happy. However, yeah, you're right. What about 3? Right? If you multiply something on the x, it usually talked about horizontal dilation, right? But I don't see anywhere with the horizontal dilation. So actually don't like it. I don't like that I have some multiple of 3. Although you could describe it by the horizontal dilation, the question doesn't want it, okay? Then what should we do? You're absolutely right. We actually have to do further property of log. How? I'm going to rewrite this as what? It's a multiplication property, right? So it's going to be 2 plus 2 ln 3 plus 2 ln x plus 1. Voila. And I'm very happy with this. Why? Because if you look at now, if you look at now the domain there's no multiple on the x. So there's no need for me to describe what? The horizontal dilation. Instead, I can just talk about the vertical translation, vertical dilation, and horizontal translation as the question wants to ask, okay? I want you to try yourself. But I wanted to show you sometimes you have to use the property of functions to meet the demand of the question. There are many different ways of describing it, but maybe the question asks you in their order, then you got to follow them, okay? Very good. All right, let's have a look at the next one. So talking about the polynomials. Topic 2, the first thing that I'm going to check with the polynomial is that you're able to factorize it, right? So after having factorized, you should always be concerned about sketching because it's often used for inequality. So if I just quickly show you the factorized form of the following, it looks like that, right? So whenever you have the multiplicity of 2, I want you to make sure that it's going to be indicating the touching part, right? So, if I just briefly sketch the function without the y-axis, I'm going to go with the least value, -3, and 0 and 1. Always try to put it in ascending form. And, for the degree is 4, so it's going to look like a parabola eventually, right? And however, we got the leading coefficient being negative, so it is ultimately going down, right? So we know the shape is sort of looking like a McDonald's shape, right? And now we have at -3, I have a multiplicity of 1, so it's going to pass through, touching, and 1. So, being able to sketch the polynomial function is important because it goes with the sign diagram and later on solving for the inequality. So I think I have attached the graph here. Let me quickly show you. Yeah, it looks like that. Okay, you don't have to write in scale. However, make sure you're able to sort of briefly sketch that, okay, and use for inequality later on. And yes, synthetic division, very important. It's often used for the long division with the linear divisor factor. So that what we do here is typically try to put the leading coefficient, right, of the polynomial. So what I'm going to do here is just put 1, 2, -3, 4, right? And what is the root of the divisor? It's a 2. And what we do is that outside, I'm going to multiply, okay? The first term comes down, 1, multiply 2, and inside of the box, I'm going to add, right? So it's going to be 4, 8, 5, 10, and 14, my friend, is going to be the remainder, right? So we have a 1x squared, 4x, 5 as the quotient, divisor, and remainder. Okay, so make yourself more clear with the synthetic division. And then yes, there are many theorems on the polynomial called the remainder theorem and factor theorem. It's quite trivial, right? And then it's very often they ask about the simultaneous equations, right? There are 2 unknown coefficients in the polynomial, and I want to derive them, and you have to use the 2 equations on them, right? And one thing I want to remind you here is that yes, when you are trying to divide by the quadratic function, right? So typically, we are often talking about the dividing by the linear, right? Hence, the remainder was a constant at most, right? The degree has to be smaller. But if I'm dividing by the quadratic, make sure your remainder can be at most degree 1, right? That's the one thing I want to make comment of. So here, if I go with the polynomial, right, and I'm trying to divide by x minus a, that I have some quotient here, and I'm going to have some remainder, which is going to be a constant because it has to be strictly less for the degree, and the remainder is given as a alpha cubic. So I'm going to put alpha cubic. Okay, that's great. And then I'm going to go what? X minus 2 beta, right? So that is great. And I have a q2 x plus beta. Was it beta cubic? Yeah, the remainder here was given as a beta cubic, so here's what I'm going to write, okay? But now, I'm trying to divide by who? The quadratic term, right? So then, I'm going to have a x minus alpha, x minus beta, and then some other quotient that I don't know. However, here's a very important part. When you are trying to find, the remainder of that polynomial, you need to write down the at most degree 1 for the remainder, which is going to be, let's say, px plus q. So your job, my friend, is to get that p and q, which requires two equations, isn't it? Because I have two unknown parameter p and q, which is then you can derive from the first two equations by the remainder theorem. So use that information. We know p alpha by the remainder theorem is equal to alpha cubic. P beta is what? Beta cubic. So we can directly apply there and be able to solve it. Okay. So I think I've written down some of the equations here. So you are more than welcome to try the algebra by yourself. I've actually written some parts because it was time consuming to write all that, but I will put this in PPT in our video. So yeah, sure. As you can see now, I'm using that initial condition, and then I'm trying to use the algebra, right? The difference of cube, right? Difference of cube is going to be factorized such then you can factor out some parts to find the A, and then you can find the B later as well. Okay, so the remainder is therefore is going to have this linear form. Okay, if you're dividing by the quadratic, at most degree linear. It can be, of course, 0 if the coefficient is, it can be, degree can be 0, meaning the constant, if the leading coefficient is 0. It depends on the alpha and beta. Okay, so imagine if you're dividing by cubic polynomial, let's say, what's going to be the at most degree for the remainder? You're absolutely right. It's going to be, in fact, 2. Okay, that's great. Okay, another form, sum and product of roots for a polynomial. It is often associated with the, the complex number as well, with the fundamental theorem of algebra. So one thing I want to remind you is that, I think it's called the Vieta's formula. I have a an x to the power n, an minus 1, x to the power n minus 1, goes all the way to the constant term is equal to 0, right? And then imagine for the degree n polynomial, let's say that I have n many roots, okay? So suppose that the roots were, roots were alpha 1, alpha 2, alpha 3, all the way to alpha. And suppose I found n many roots there. It doesn't matter if it's a real or complex number, doesn't matter. Then, ones that what is it? Sum is given by negative an minus 1 over an, right? That's the typical formula that we know. And also the product, alpha 1 going all the way to alpha n should be, remember, very careful, the product of roots alternate, right? Depending on the degree, it can be positive or negative. So I'm going to write as a negative 1 to the power n, alpha a naught, of the constant form term of the polynomial, and then the leading coefficient is the way to go. Of course, there's a slight variation. I think sometimes you're asked in the cubic polynomial of the other parts, such as, if I go with the only product of two roots, so alpha 1, alpha 2, alpha 2, alpha 3, whatever, alpha n minus 1, you can think about the number of combinations that can happen here. It's going to be, it's always, one step next, right? So if I was finding the ratio between these two, then you're going to find the ratio with the next term. So it was a minus, so in this case it's going to be plus, a n minus 2, okay, over a n. And you can see sort of you can expect what's going to happen, right? So if I go with the, product of three roots, it's going to be minus an minus 3 over an. You can easily prove this by using induction, okay? But anyways, if I erase all that, let's have a look at what's going to say here. So yes, it's a very important here. This, I'm trying to find the P and Q. Okay, I'm trying to find the P and Q, and for that I want to use sum and product of roots. And when you do so, I want you to realize this is a cubic, but I have a perfect square. You may assume that I only have two roots, which is a and b. You're right. However, for the for the perfect square, it's often regarded as the repeated roots. So I want you to consider that it's also a here. I have two a's. Okay, so that's how we're going to consider. So in this case, therefore, you can easily figure out what the sum and product is going to be, right? So 2a plus b is going to be the coefficient of x squared is 0, so 0 over 1, 0. Okay, so that's what I have. And number 2, then you can associate some other the coefficient with the p and q. The p is going to be the one that we just talked about, right? The product of these three numbers of these three, I'm going to just multiply by 2, and then this is going to be the product, and you can solve a simultaneous equation. Okay. Let me quickly show you. I've already typed the equations for you, I think. Yeah. There you go. Oh, sorry, I will leave that as an exercise for you. Right, so make sure now I've got that, then I will use the variation that we just talked about from the Vieta's formula to solve for P and Q, okay? Yes, another very popular example here. It says the equation of, so this is one of the past exam paper in a very recent year. It says I have a degree 5 polynomial, and it says the equation of 3 distinct real roots which can be written as the following, right? And then the equation also has 2 imaginary roots. I don't know what the imaginary roots is, okay? So, but then one of them is given by the I, and by the fundamental theorem of algebra, I've got the conjugate as a root as well, isn't it? And I'm happy, so I've got actually 5 roots, right? That's great. So here, what I want you to do is to use the sum and product of roots, right? So what you can do is simply just add them together, and then find the ratio with that, right? So if you multiply all that, if you add all that, you're gonna get with the negative 3. And then also if you multiply with all that, it's going to be, what is it? Negative 1 to the 5 times q, isn't it? Because it's a alternating term, don't forget to put the negative 1 to the power of n, then you can solve it, right? Show that ABC is equal to 8. Well, what you can do is if you add these two, it's going to cancel out, right? So then if you add all that, by the property of log, you can combine it. So then, voila, we have a log 2ABC is equal to 8, then you can use it, okay? So, but very nice example, the essence of this video is not to extensively go over the questions, right? I don't think we can have time for that, right? For each questions that we're going to go over, but it just talks about why these skills matter, right? We talk about the skills from the syllabus, and then go over some examples that has it, right? And then as soon as we check it, then we're going to move on, okay? And I think detailed explanation I already indicated on our PPT, so you can have a look, okay? So I'm going to just skip through. It's okay. I will leave it as an exercise. And now, yes, superstar, right? In the new AA syllabus, we have many superstar in functions such as partial fraction, right? And that also extends to rational function. We should be aware not just the linear over linear, but other kinds such as the linear over quadratic or quadratic over linear. This, I think, is trivial. However, the second kind, one with the quadratic over linear, but sometimes you can have a cubic over a linear, or cubic over quadratic, who knows? It induces different types of asymptote, right? So it's going to induce, what is it? The slanted asymptote. And what else? It can also go with the curved asymptote. Who knows? Okay. So if I quickly show you some examples to associate, for this one, right? We often think of okay, what's gonna be the end behavior of that function, right? Every time we have some rational function, we wanna talk about the asymptote, right? The obvious kind in this case is going to be who? The vertical asymptote. So I'm going to indicate the vertical asymptote here. And now I want to talk about the horizontal asymptote. I want to send x to infinity, but of course, this diverges, right? This diverges. Right? No questions asked. However, you're right. Its end behavior of the divergence is very, very similar to the linear form. Why? Because the 1 over x is going to converge to 0 if you send x to infinity. So then we have actually slanted asymptote like that. Y is equal to x. So make sure you are aware that you were aware of distinguishing between the horizontal asymptote, slanted asymptote, or sometimes curved asymptote. And then, the best way to indicate which quadrant it's going to fit is to work with the intercept. So, if I put into the common denominator, I have a x squared plus 1 over x. And as you can see, what do you recognize? I don't have an x-intercept. So, I'm not going to indicate it there. So going like that would be good to go. Okay? So I think I have a picture attached here, so we can show it. So a detailed explanation, I put it in the PPT, so have a look. But for me, I just want to show you the shape. So it's going to look like this. Okay? Do you see? Okay, that's great. All right, so this is also a bit different, right? But doesn't change the fact that your slanted asymptote is going to be x. And the detail of questions, I will leave it as an exercise. But whenever you see this type of rational form, right? Bigger degree over smaller degree, be aware that you might have a different type of asymptote. Okay? Not only the horizontal could be linear or curved. Okay? So yeah, this is the example of a curve, right? So because if you send x to infinity, 1 over x just goes to 0, okay? So now I know it is going to diverge very, very similarly to who? 4x squared, okay? So for me, I'm going to indicate, okay, the vertical asymptote like that. And what is it? Curved asymptote 4x squared. So it's going to look like this. And then which quadrant do I indicate? It depends on the intercepts that you find. I'm going to leave it as an exercise. Okay. You can have a look at the PPT. It's really, really well expressed and described. So have a look. Right. So the shape is going to look like this. Yes. Right. Curved asymptote of a quadratic function. You see that? And vertical asymptote. And then depending on the x-intercept, I go through this quadrant. This quadrant I cannot go because it's not going to pass the vertical line tested for function. If I was moving around, this quadrant would have induced another x-intercept, which is not possible. Hence, I only choose this. So these two shapes are going to determine that fancy function here. Okay. Sure, even and odd is pretty trivial, right? Sometimes you're asked to prove it, so make sure that you're able to prove it by using composition. Okay. So fine, it's just to set up if you're trying to prove, for example, the product is an odd function, what I would like to do is define it as a new function and try to compose it with the negative x and see what you get, okay? Trivial, it's fine. But there's one comment that I want to make for the typical even and odd function that could possibly come for the paper 3 is that I think it's kind of getting a trend. You really want to, even though it's not in syllabus, be aware of a hyperbolic function. Okay, so mark my word. Hyperbolic function is a very, very popular, all right? It looks like what? E to the power of x plus e to the power of negative x over 2 is a hyperbolic cosine, right? And then another function is the e to the power of x minus e to the power of negative x over 2 hyperbolic sine. Okay, and there's a reason for this to be popular because it's an interesting shape. And it starts with even and odd, so maybe they're going to ask you to prove it. And it can be used a lot for calculus, right? Very, very popular for calculus. And you know what? Even better, I give you better. A complex number, right? It's also accompanied with, it goes along well with the complex number and the Maclaurin series, okay? So very, very popular Maclaurin series, very, very popular example to come along with the paper 3 problems, okay? So make sure you're aware of it at least, okay? And I think I give some details on that function on our PPT, so have a look, okay? And I gave some explanation there, so I would encourage you to read through, for your potential paper 3 problem. Sure, very important, solving inequality. As we have discussed before, solving inequality is very important with the, function, topic 2, finding the domain and range. And when you do so, sometimes you're going to do the graph or analytical. It means a sign diagram. Okay, easy peasy, lemon squeezy. So with this type of question here, what I want you to do is I do not want you to rearrange this to the other side. I don't want you to do that. Why not? You're absolutely right, because it might change the sign. I don't know whether it's going to be always positive or negative. I don't like that. But what I want you to do is, just to rearrange to the other side of 3, because subtracting doesn't change the direction of inequality, and put them into the one common denominator. So let me quickly show you exactly blah, 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 it. So it looks like that, okay? So the inequality I've got was this. After having rearranged, I've got that, that's great. On this, you know what? I don't like having the leading coefficient -1, so I'm going to multiply -1 on both sides, resulting the change of the direction of inequality. So blah, blah, blah. Okay, sorry, I didn't write that. Sorry, maybe I'm going to write it here. What I want you to do is that, well, you know what? Let me just screenshot that picture. Undo this. I do believe this is going to be send me to the next slide, right? That's great. So, okay, so what I wanted to do is this. So I'm going to multiply by the -1 on both sides, right? So if I did, it's going to be x minus 4, 3x plus 2 over x minus 3, x plus 1 is it bigger than 0, okay? So that's what I have, right? And then what I have is that on these x's, I want you to indicate the x-intercept, right? So it's going to be who? -1 and -2/3. Make sure you're putting in the ascending form, and 3 and 4, okay? All right, that's great. And what is a vertical asymptote? I have a 3 and -1, okay? That's great. And I'm going to check which one is going to be positive and negative. Okay, so in this case, if I put just a 0, it's a positive, so interval that contains a 0 is here, right? So it's going to be positive, and anything other than that is pretty much alternating. Not always. Remember, if I had something like a perfect square and always positive term there, it may not change the sign after the interval, so you want to check that. But because I see automatically that it does not have any perfect square or anything like that, it's going to always alternate, right? So now, for anything bigger than 0 is going to be, what is it? X less than -1. What else? Between -2/3, 3, or x bigger than 4. So that is going to be a fancy way of working with well, not fancy, sorry. It's a very efficient way of dealing with the inequality using sign diagram. Okay. So let's move on to the next slide. So I've already graphed it for you too. So have a look at this slide if you want to get more details of that question. Okay. I think these are way more important, right? The function transformation, right? Function transformation, what we know is the translation, dilation, reflection. That's the transformation 1. Okay. But we have different types of transformation. I would call it miscellaneous, right? There are many different kinds that can memorize it. Okay, but you need to see the general pattern of it, right? Something like the modular transformation, reciprocal, translation, and squaring it. What's going to happen? Let's see. Okay. So for the modular transformation, what I really want you to strongly suggest is that you try to put it into piecewise function, right? I want you to put it as piecewise function. And how do you distinguish it? It depends on what value of x it makes the 0 inside. I'm not talking about the x-intercept. I'm talking about the individual modulus, and then talk about the values of x that makes it 0, because that's going to be the point where you're going to create the piecewise, who's going to be positive and who's going to be negative. So I've created the piecewise function here for you because it's very tedious to write all that. So I've got, x less than 1 was a -4x. Between -1 and 0, I've got -2x plus 2. Between 0 and half, I've got 2. and then bigger than 1 over 2, I've got 4x. Okay, that's great. So then I should be able to picture it, right? I should be able to picture it. And then the question was asking to find the intersection with 7, right? Then you can let the y equal to 7 and realizing the intersection only happens between two functions, the function number 1 and function number 4. Okay, so I'm going to only look at the function here that is less than negative 1, and I'm going to look at the function that is bigger than 1 over 2 with 4x. So that's the only two functions that I'm going to make intersection with. I don't want to square this. I'm aware that if you do the modulus squared, that's going to be x squared, but this is really not the function that you want to square around, okay? Because first of all, there are 3 terms, and then even if you square it, some terms are going to be put in square, but in between you're going to have 2ab or 2bc, right? So you're going to multiply these two and then multiply these two functions and then have a 2 coefficient that still has the absolute value, and you need to keep squaring it. It gets very messy. Okay, so do not get accustomed to squaring it when you have modular transformation, when you have an absolute value on a function. Okay, so that's one comment. So yeah, this is a very, very good example. Okay, because I see an absolute value, what I'm going to do is, okay, you know what, I'm going to just square it. Let me quickly, sorry, I'm not going to use that. Let me quickly square that, so let me show you why I do not like squaring when I see an absolute value. Okay, moving on to the next slide, and let's see what we can sort of talk about here. So let's square it. Boom, boom. I've got 9x squared plus 6x plus 1 is bigger than 4x squared, right? So that's what I have, and then I'm going to rearrange. So it's going to be 5x squared plus 6x plus 1 is bigger than 0. Okay, so that's great. And let's see if it's it's a factorizable. That's great. 1, 5, 1, 1. I have x plus 1, 5x plus 1 bigger than 0. Okay, that's great. So now if you look at the x's, I see what is it? Negative 1 and negative 1 over 5. Okay, and then I've got minus plus plus. Then I see, okay, so the answer must be x less than negative 1 or x bigger than negative 1 over 5. But if you actually try to sketch this, okay, if you actually try to sketch this without squaring it, let me define the fx as a modulus 3x plus 1 and then gx as a 2x. So then I look at the x's, okay? And what I recognize is that for that one, it's going to have a V shape, isn't it? So at the x-intercept of a negative 1 over 3. And it looks like that. Okay, that's great. And now if you look at the 2x, it's got smaller coefficient than the 3x. So it's going to be a bit more obtuse. And as you can see graphically, there's no intersection, right? So this function is always bigger than 2x for whatever value of x. In fact, the answer should be all real. However, right, if you look at the algebra of squaring it, that actually makes some confusion there. Hence, this is another example to indicate that I would be very careful when I want to square things, when I see an absolute value. Okay, if it's an equation, you may try, but inequality, I'm against. Okay. So detailed things I described there, so please have a look. So it's fine. All right, so this is a very, very good example. This is a very, very good example, right? Why? Because it talks about why sketching matters. And as you can see, if I see an absolute value, I can say, okay, maybe I want to square it, but I want you to realize it's squaring this is fine. Squaring that is not fine, you see? So I want you to graph this, right? So this is actually just a modular transformation of the outside and inside of the same function, right? It is essentially dealing with the fx being e to the power of x minus 2, right? So you want to sketch that first and then follow what transformation you want to do, right? And it's an exponential growth, right? With the horizontal asymptote of negative 2, so I can easily sketch this, right? So I'm going to sketch that function first. No problem. So it looks like, and then you're gonna do the modulus of x and modulus of domain, right? So what I want to also remind you is that, okay, if you want to do the modular range, that means that everything, all the negative, is going to where? Positive, you're right. So that part is going to be positive, this part is going to be positive. So that's something that we are aware of it already. But if you want to do, what is it? Modulus domain, if you want to sketch the function of, what is it? Absolute value of x, what you want to do is, first, what do? Sketch. So get rid of the left. I want you to get rid of the left like that. And then make it symmetric from the right. I want you to make it symmetric from the right, like that. So that's going to be the shape of the modulus domain. Okay, so if I quickly graph it for you here, I had a exponential growth, but this orange function is going to be the one with what? Function of absolute value x, right? Because it made a symmetry from the y-axis. And then, I don't think you can see it clearer, but if you look at the modulus range, all the negative part has been shifted up, right? Positive part was already positive, so there's nothing I can do. There's nothing I need to do. It's the shape that we have. And as you can see from here, you see there are two parts of intersection. So one as a point and one as a, what is it? Oops. One as a region, right? So that is always the same. And that was given by, what is it? X-intercept ln 2. So, they are the same for x bigger than or equal to ln 2, so that's okay. But that intersection, you actually have to solve it, right? And then why it's good to sketch is that you know where the intersection is going to happen. It all happens in the left piece. You see that? It all happens on the left piece. Okay, so what I mean by that is for that one, the left piece is going to be what? Negative e to the power of x plus 2. Okay? If you look at the function there, the left piece is, what is it? E to the power of negative x minus 2. And I will encourage you to solve this equation to find that intersection. So graphing is good because I can easily get rid of the absolute value depending on whether it's going to be the left piece or right piece. Okay? Good. And yes, I want to talk about the next transformation of the reciprocal, right? What happens if I do the reciprocal transformation? Okay, no problem. Well, typically, the x-intercept of the original function is going to become the vertical asymptote, like that. Okay, that's great. Vice versa, right? The vertical asymptote would have been x-intercept, just like that. Okay, and yes, the horizontal asymptote, I think that's horizontal asymptote, isn't it? Yes, horizontal asymptote also is going to be reciprocated. So I have a new horizontal asymptote of who? Reciprocal 2/3. Okay, I have a 2/3 as a horizontal asymptote. That's great. The sign wouldn't change, right? If it had been a positive, it's going to be positive. And then the behavior is going to be reversed. Everything going up, now it goes up on the denominator. So for the fraction, it goes down, right? So increasing, we change into decreasing. The decreasing, we change into increasing, right? So that's what we have. So from the vertical asymptote, you need to determine whether it's going to come from the positive infinite or negative infinite. All the value to the right were positive, so I'm going to come from the positive infinite. Okay, so positive infinite, and also, one more thing. When do they intersect? If you let the function to be 1 over f, f squared is equal to 1, so they are going to intersect at plus minus 1 of a y, not the x. Okay, so maybe I want to indicate the y equal to 1 as well. You know what I mean? And negative 1, because I know that's where the function and reciprocal function is going to intersect. So coming from the a positive infinite, and what is it? Intersecting at 1, remember that. And then, what is it? Touching at 2. Sure, it should be touching, right? Because if it was a passing, it suggests that my original function was a negative, but it's not. Okay, so it's going to be touching there. And then converging to who? Horizontal asymptote of a 2/3. Okay. And what about the left? Well, everything was in the negative. And then coming from the vertical asymptote of a negative. And then, what is it? Again, intersect at y equal to -1. But as you can see, you know, the horizontal asymptote towards the left seems to be a 0. So for the reciprocal function is in fact going to diverge like that. So that we have that bullet function. Okay. So that's great. So the graph looks like this. Okay, I want you to practice yourself as well of this reciprocal transformation. Yes, you know, another example from the exam, right? So, you know, you had to sketch the reciprocal. No problem, you know, the vertical asymptote would have been the, what is it? X-intercept. X-intercept would have been what? Vertical asymptote. Horizontal asymptote was 1. It's going to be still 1. Is there anything else that we have to consider? Not really. And therefore, look at this. This positive part, okay, of the function is going to indicate that I'm coming from what? Positive infinite. Oops. It's going to come from the positive infinite and goes to y equal to 1. That's great. And for that one also, remember, it was all negative here. So I'm going to come from the negative infinite, passing at y equal to -1. So maybe it's not on scale. Sorry about that. It goes like that. I'm going to pass that, what is it? Y equal to -1 for the function, reciprocal function to intersect. And at that x-intercept, I wonder if it's going to be touching or passing. Well, you know, the sign doesn't change, so it's going to be touching. And also, the initial y-intercept was a -2, so now I'm going to do -0.5. Right, so it goes past through there, passing there, and now, you know, the sign changes. Therefore, you know, it's going to be passing and converging to y equal to 1 is the graph you want to sketch. Okay, that's great. All right, so a very, very good trigonometric function sketching. Okay, if you want to sketch this, you know, you may try with the compound angle. I don't want to do the compound angle because you should realize this really suggests that you use what? Something called the complementary angle. So what I mean by complementary angle here is that the tangent pi over 2 minus theta, do you remember? Can you please tell me? Yes, you're right. It becomes cotangent. Oops. It becomes cotangent theta. Okay, that's great. And what about the vice versa? You know, cotangent, cotangent pi over 2 minus theta becomes a tangent theta. Okay, that's great. So now I see that I can actually convert that into who? This is the same as tangent pi over 2 minus whatever the angle that we have. I'm going to call that as my theta. Okay, no problem. So pi over 4 minus x. Okay, then you realize that this becomes tangent x plus pi over 4, in fact, actually. Right, so you're actually sketching, what is it? Tangent square x plus pi over 4. Voila, right? Why I came up with this example? Because when we were looking at the function transformation 2, it had f square, and this is a very example that I want you to try. And you know, have I graphed this in the next slide? Give me 1 second. Oh, sure. So we were sketching what? Tangent x plus pi over 4, I believe, wasn't it? Square. So what I've just done now is I've graphed the tangent function first, because that's what I'm more familiar with, right? And then what do you have to do? And then you need to square it, okay? And then you need to square it. Okay, that's great. So here, you know, I've got the vertical asymptote there. That's great. I've got the vertical asymptote there. That's great. And then you want to square it. But, you know, what would be the things that you're going to be careful other than everything becomes positive? You're right. When you are squaring between 0 and 1, it got smaller. But if it's bigger than 1, it gets bigger. So, you know, the reason I'm going to be very careful is with the y-intercept. You know, his y-intercept is 0, 1. So anything less than 0, 1, anything between 0 and 1, it should be smaller. You see? You need to indicate that. But anything bigger than 1, if you square it, it gets bigger. Oops, doesn't look like it gets bigger. So that's what I will be always careful about when I'm graphing with the square. What is between 0 and 1 gets smaller, after 1 gets bigger. So and all the positive just becomes, positive like that is fine. So we have a very nice graph. Okay, so this question alone was a very, very nice example. Why? Because you use the trigonometric identity. And then when I'm thinking about the square, we need to think about between 0 and 1. So that region is super important, okay, for squaring it. Yeah, so that should be the graph of it. So very good. Let's move on. All right, finally, finally, superstar. You should spend the most of your time learning topic 3, okay? Well, let me specify, trigonometry, it is the most important topic, okay? Because it goes along with what function, trigonometry, vector, calculus. Okay, without further ado, let's get started. So yeah, the first example I came up with was sure, it says sine, cosine, tangent ratio to find the side of the right angle SOHCAHTOA. Right, SOHCAHTOA is easy peasy lemon squeezy. Every time you see right angle triangle, you really want to use a SOHCAHTOA, and you should be very comfortable solving a question like this. Okay, I want you to pause your video and read through worthy problem. It's a very, very typical example, and then the diagram looks like this. Okay, and then what I mean by that, you should be very comfortable is that building up an equation, right? Our aim was h to find the height of the cliff, but here it should be your deductive thinking to set up another variable. It didn't say to find that, but to be able to create an equation, you need to add that. And as soon as I see a right angle triangle, no hesitation, I'm going to use a SOHCAHTOA. So for this one, what's going to be a better trig ratio out of a sine, cosine, tangent? Here, right, I'm going to use tangent. So the first equation I'm going to do is maybe with the tangent tan, right? And then you have h over, what is it? X plus 50. And then the second one will be tangent 15, right? That's great. So that's going to be h over x, right? Then you can solve it simultaneously. Maybe I think division is going to help you to get rid of the h and then find the x first, and then find the h. Okay? So, this type of modeling problem on the right angle triangle is very, very popular. Oh, sure, another thing after the right angle triangle was, sine and cosine rule, right? So, let me talk about that. Sure, so when you read this question carefully, every time you got a triangle problem, I just want you to randomly sketch the triangle. Just do that for me, okay? And now I've got the P, Q, R, right? So as PQ is a 6, and then PR is K. And then PQR is a 30 degree. And then for the case of K equal to 4, is given, I want to find the QR. Okay, what rule does this remind you? We got the SSS, right? So depending on the classification of a given information, you should be aware of what rule you're going to use automatically. I know I'm going to use cosine rule. Okay, I'm going to use cosine rule for that. Okay, that's great. So then you can use cosine rule to find it. I will leave it as an exercise. I think it's going to be just a simple quadratic equation. Okay, and both of the solutions are okay because they're positive. But another one that I want to talk about is who? The next question, right? Next question. Let me talk about the next question. So if I quickly draw the PQR once again, PQR was a 30 degree, and PQ was a 6, and PR is K. At this time, K is not given. Okay, so then I have to find the K so that it's going to be unique triangle. Okay, sure. So how do I work with the unique triangle? Well, if you look at that, that's a, what is it? SSA. right? So what should that remind you? You're absolutely right, sine rule. And yes, you gotta be extra careful. What do you have to be extra careful? For the sine rule, there's a case of ambiguity. We have ambiguous case. You have to be super careful with the ambiguous case. Okay, so you need to know the condition of K that makes it unique, or two solutions, or no solution. Right? So we need to be aware of those conditions. I think I put a slide on it. But by the way, so if I quickly show you here, every time you want to check with the unique case, you want to look at the A over sine A and then the B. What does this A over sine A means? It's the given angle and then opposite side. Every time you have a pair of angle and opposite side, that's going to indicate the lowercase a and the capital letter A. And B is the another given length, which is a 6 that does not have the opposite angle. Okay? So you really want to look at the ratio. So if it's a unique triangle, one condition is that yes, that ratio needs to be the same. Okay? And or A is bigger than equal to B. Okay? So we need to know those conditions for ambiguous case of a sine rule. In this case, we're talking about a unique triangle. Therefore, the answer is going to be K is either equal to 3 or bigger than equal to 6. Okay? And you can download this PPT for further reference of, okay, when is it going to be ambiguous case, two triangles, or no triangle. Right? So in that case, you still have to check with who? A over sine A and B. You will not have a triangle if A over sine A is less than B. Then it's going to be no triangle. Okay? So we should be always aware of those conditions for sine rule. Okay? Because it's an ambiguous case. So sure, for this one, also I know it is cosine rule. Okay, let me ask you. Why do you think for this given information I'm going to use sine rule? I'm sorry, cosine rule. Think about it. Very good. You're absolutely right because it's case of SSS, isn't it? So for that, I know it's going to be cosine rule. So you can apply the cosine rule there. I've done it for you, blah, blah, blah. But this question alone was to check your algebra, whether you can cancel things out quickly. So if you have done it, blah, 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 comes out as a negative half. Right? Remember, this theta was an angle of a triangle. Okay? And only solution that you can have a negative half is going to be in where? In the second quadrant. And that's going to be giving you the 2 pi over 3. Okay? Easy peasy, lemon squeezy. Okay. The next thing that I want to talk about is those angles. Okay, super important, right? You should be very careful with what? Reference angle. And what is complementary angle? Wow. Writing in cursive, okay? Right, so you must be master of it. All this, all that, okay? Let me quickly show you an example. Sure. Whenever you have these sort of humongous angles, you want to really express it in terms of integer pi. Okay, integer pi, not pecan pie, not apple pie, but integer pi, and then find an acute angle, right? So the closest integer that I can do with this rational number is maybe negative 4 pi. So it's negative 16 pi over 4 plus what is it? Pi over 4. So it gives you which quadrant you have, right? So, after negative 4 pi clockwise, I'm located here. I'm adding by pi over 4. It is in the first quadrant. So it's going to be same as a sine pi over 4, which is a root 2 over 2. Right, so think about the next example. Right, what's going to be your closest integer for 17 pi over 3? You're absolutely right. So it's going to be cosine, what is it? 6 pi. Right, not pecan pi. And then I'm going to subtract by pi over 3. Right, brilliant. So which quadrant does it send? Yes, you're absolutely right. 6 pi is even pi, so it just comes back to here. Right, it's going to be 1, 2, 3 cycle, and then subtracted. Oops, my bad. I rotated by clockwise, didn't I? I meant to go by anti-clockwise. And then subtract, so it's in the fourth quadrant. So who is positive in the fourth quadrant? It's a cosine, so it's gonna be positive cosine pi over 3. It's brilliant. Okay. The next example, I'll leave it as an exercise. You do it. And also another important angle rotation is the complementary angle. So whenever you see odd pi over 2, or namely pi over 2 plus k pi, where k is an integer, it is going to be complementary angle, and you gotta be extra careful because it changes the ratio, right? So what I mean by that is if I could, we saw the example with the tangent, didn't we? And then another example is, let's say, sine pi over 2 minus theta is cosine theta, okay? Vice versa, cosine goes the same thing, okay? So, I know for sure that this is going to convert into cosine x, you know what I mean? But then you gotta be extra careful. Why? You need to know whether it's gonna be positive or negative. So, that depends on the quadrant. Okay, that depends on the quadrant. So 3 pi over 2 is 270, and then I subtract by x, then it's in the third quadrant. So for sine, it's negative. So I'm going to indicate negative there, okay? Very good. So for this one, without hesitation, I know it is converting to the sine x, right? Very good. But whether it's going to be positive, negative, I don't know, okay? I don't know. So that is, which axis is it? One above or is it one below? Let's think about it. Let's think about it. I had a minus 12 pi over 2, and then we add it by pi over 2, so it's located there, and I subtract by x, it's in the first quadrant, so it must be positive. Okay, so that's how you determine. The next example, I will leave it as an exercise. Try yourself. But if it's something with the odd pi over 2, remember it's a complementary angle, right? And it's important for you to see because, for example, the previous example, do you remember from the function? I believe it was x plus pi over 4 or something like that, right? Cotangent pi over 4 minus x. If you do not use the complementary angle on that one, if you didn't see that, sketching that would have been very, very complicated. Okay? Anyways. Yes, what is Pythagorean identity? Super important, right? With the, oops, sorry. I think I meant to do with the, angle of elevation and depression. That's the one that I was trying to do. So what I mean by that is, check this out, you're gonna have worthy problems like this. It's an exam question, I think. This is a pun intended by the examiner. Depression going down, elevation going up, right? And what is important is that you're always able to visualize things of the worthy problem. If you're given a problem like this, without diagram, I think it would make it extra harder. But I think during the exam, they are very, very kind. Examiners are very, very kind, and they are trying to grade as generally as possible. Trust me. If I was marking, I'll be very harsh, but I'm not. And here, luckily, they have given me the diagram. Okay. So and what you want to do is to indicate all the information you have. Okay. Angle of depression is something from the horizontal line going down, right? But you can do the alternating angle with the parallel lines, right? So in fact, same thing as the elevation, easy peasy, lemon squeezy. So I'm gonna indicate the 25, 35, and I believe there's an included angle in the base of a 70. You can pause the video and read it through, and then follow my instruction on the next slide, all right? So 25, 35, 70, and 80. So I get all the numbers going to indicate on the slide. So let's do that. I have a 80 here. I forgot. I think in the middle, this was a 70 degrees, isn't it? And then it was a 25, 35? Yes, there you go. So the angle of depression was 25, 35, no problem. I'm just gonna do 25 degree here, 35 degree here, because why? It was a alternating angle. And this type of 3D shape, super popular, so make sure that you are aware of it, okay? Then I'm going to look at the triangle there. Oops, let me draw better triangle. Let me draw a triangle like that. And for that one, you know, I'm going to indicate the information of the base. You know, I'm looking at the 2D shape of it, right? S, X, N. Okay. That's great. And I'm looking at the 70 degree here. All right. And our aim was to find the SN. So if I call this as X, sure, don't be afraid of using the right angle triangle. The standing triangle here is a vertical height, so it's a right angle triangle. And we love right angle triangle because I don't need any fancy formula like a SOHCAHTOA. I can simply do the rise over run, right? Or I can do the, this one I can do the rise over run. So if I call it A and B, right angle triangle, SOHCAHTOA, and I'm going to use TOA. So here I can do the tangent 25 degree is going to be 80 over A. Therefore, what is it? A is going to be 80 over tangent 25 degree. That is brilliant. And I'm sure you can do the same thing for B, right? That's going to be, what is it? 80 over tangent and 35 degree. And I can use that information for what? On that triangle on the base. So, you know, the whole point of me of describing this example is because I wanted to show you 3D shape matters, and this is a very popular shape. And with that, please make sure you're trying to derive some information of the standing triangle. Okay? Thank you. So blah, 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 you can check yourself and it's good to go. All right, circular measures. In a radian, you should be able to derive all the length and angle using just the radius and theta. The formula should be very comfortable. You should be able to derive sector, segment, chord, arc, you name it, okay? But it just requires 2 parameters, that's it. All right, so if I get a shape like that, you know, what you want to do is to indicate what is it with the angle and then the radius according to the given equation. Here, I'm given the radius here is a 2r. Okay, that is great. And here I'm given the radius, oops, it's not in best shape. It's given as r, okay. And the angle, what were we given? I don't think it mentions it here, right? Sorry. Oh, there you go. CAD. Alpha is a CAD. Okay, so that is going to be alpha. Oops, maybe I'll write in blue for that shape. Okay. And then, what is it? Here, this angle was a theta. You know what I mean? Very good. So on this one, what I want to do is to indicate the chord as well. Because you realize this is really just a expression for who? Segment, right? Remember the formula for the segment. What is? The segment was from the sector, I subtract by the triangle, right? So that was, the formula was a 1 over 2 r squared factorized by theta minus sine theta is what we're gonna do, right? That's great. So if I use that formula here, number 1, did I write? Let me see if I written. So yeah, there you go. Great, yeah. The formula is, what is it? The segment. And then I've used that information about the radius. Make sure when you're using calculator also, you are aware it must be in radian. Okay, it's a very, very common mistake. You know the formula, okay, but then you put like very large number like 30 degree here. No, that's not okay. That's not cool. Make sure all the formula that we memorize for the circular measure is always with the radian. Okay, that's great. And I will leave it as an exercise for you to solve that problem. I've put some more information. My whole point here is what formula, what information, what skills we need to tackle the problem. Actual solving is your task. Oh wow, Pythagorean identity, very important. Right, now let's go with the Pythagoras theorem. Many formulae to memorize. And there's a lot of a composition with the inverse trick, so let's get to it. So whenever you have some sort of a identity problem, what I want you to do is try to use a right angle triangle. Okay, I want you to use a right angle triangle. Well, you know, I've got technology, so maybe I would draw the right angle triangle more beautifully like that, okay? That's great. So what I want you to do, forget about the positive, negative. Even though, for example, let's say this problem, I got negative there, forget about it. And I'm gonna go with the x there. I think it's meant to say x there. Then I'm gonna use the ka adjacent over hypotenuse. So I'm gonna go with the 3 and 4. And then the opposite is going to be given by the Pythagoras theorem, right? 16 minus 9, so I have a square root of 7. From there, I'm going to derive, what is it? Sine x, right? So that's going to give me root 7 over 4. Okay, so of course you can use the Pythagoras theorem, right? So sine squared plus cosine squared, but that's literally derived from the right angle triangle. And the point I'm trying to make, after having done that, try to determine the sign, whether it's going to be positive or negative, right? So in this one, from pi over 2 to pi, that's the second quadrant. So I know it's going to be positive for the sign, so I'm going to put a positive there. Well, let's have a look at the tangent x. Why not? So if I go with the tangent x, that's going to be root 7 over 3. But in this time, however, it's in the second quadrant there. So the tangent must be negative, isn't it? So I'm going to use negative sign on it. So make sure, you know, if you want to derive an identity or to convert the value, just use the Pythagoras theorem, that's fine, okay? But later on, depending on the given domain, determine whether it's going to be positive or negative, okay? You can check yourself, you know. And same thing for here, you know, let me try to use that example. Why not? So I'm going to go with the tangent x. Let me do the right angle triangle. Voila. And then I realize for tangent x, it's a rise over run. So I have a 12 over 5. Sorry, it's not on scale, but it's okay. So then, you know, the hypotenuse is going to be 13, okay, by using the Pythagoras theorem for the right angle triangle. And here, if I want to get, for example, sine x, what I would just instantly do is, you know, 12 over 13. You need to be aware, however, it is in the fourth quadrant. So we know for the fourth quadrant, only cosine is positive, so sine must be negative, right? Likewise, if you want to get the cosine x, it's going to be, what is it, 5 over 13. And for the fourth quadrant, it's going to be positive, and that is how we get it, okay? Easy peasy, lemon squeezy. And yes, you know, doubling formula, please memorize it. I'm not going to go over the formula list, but talk about what sort of exam skills you need to have whenever you have a double angle formula. So for the sine and tangent double angle, there's only one form, right? So you know, there's no way that I can change around. However, cosine double angle, we have 3 of them, right? And for that, what I want you to choose is depending on whether we have a 1 or negative 1 in the equation. So for example, if I have a, you know, I might have a 1 minus cosine 2x or 1 plus cosine 2x. Whenever you see that, our aim is to get rid of that 1. I want to get rid of it, okay? How you can get rid of it is choosing the one that has, in this case, positive 1, right? So that you can cancel out with the negative 1, you know what I mean? So maybe I want to associate this with the 1 minus 2 cosine squared x, so that it's going to cancel out with him. Oh, oops, sorry, my bad. I meant to say sine. Oh, it's okay. Sine. Yeah, there you go. So that it's beautiful. It cancels out. Double negative becomes a positive, right? Think about it. So if I got the 1 plus cosine 2x, I want to derive negative 1 to cancel it out. Then voila, we have a 2 cosine squared minus x, and it cancels out. Okay, so the very likely for the double angle problem with the sine and cosine, especially cosine, it's in pair with the 1 or negative 1, and you want to get rid of it, okay? So as you can see for this one, you know, for the double angle of sine, no problem, we already know it, right? So we already know that this is 2 sine x cosine x, okay? That's okay. There's only one form, but of that one, of the double angle of the cosine, there are 3 variations. But on the right hand side, I've got 1. So my aim is to get rid of that 1, isn't it? And for that one, I should get the same one on the left hand side, so that it's going to cancel out. And I've got the negative 1 there, so you want to get the negative 1 there as well, so that it's going to be alternating, right? So it's going to be minus. Let's choose the one with the negative 1. It's the 2 cosine squared x minus 1. Then voila, if you expand, it's going to be 1 minus 2 cosine squared x, and it's going to cancel out with 1. It's beautifully canceled out. Let me quickly show you the equations. I already typed it, but you can check yourself how you want to do it. Okay. Easy peasy, lemon squeezy. You can download this PPT and then solve it. Okay. No problem. No problem. But also, do not, only work with the doubling of a sine, cosine with 1. Also, sine is very popular to pair with the 1 or minus 1. So, I want to show this. How can we show that? Maybe you can start from the left-hand side to the right, right to the left. Maybe I'm going to start from the left. So in this one, it's going to be sine square plus 2 sine cosine, cosine square. And as you can see, I can use the Pythagorean identity to get rid of a sine square, cosine square as a 1, right? And 2 sine cosine is simply just doubling of a sine. So it's proven. Okay, so make sure you also memorize 1 plus minus sine 2x is in fact the perfect square of a sine plus minus cosine. Okay, so very neat. This is also a very, very neat example. So if I want to work on that one, have I written it? No, I haven't. So I'm going to talk about that little. So let me just quickly screenshot that equation. Yes. Unclick that. Move into the next slide. And voila, I have it. So on this one, what I want you to do is this. So you can go from the right to the left, left to the right. It's up to you. Okay. Maybe I would go from the left. All right. So let's try. So this is what is it? 1 plus sine 2x over cosine 2x. I've just put it into the common denominator because the secant is a reciprocal of a cosine. And then what I realized is that for the doubling of a cosine, there were 3 forms, and I said you got to be very careful with the existence of a plus 1, minus 1 because you want to get rid of it. But in this time, I don't have it, so I'm going to choose the one that does not have 1 or negative 1, and that was exactly who? Cosine squared x minus sine squared x. That's great. And on the numerator, it's a perfect square, so I'm going to go with cosine plus sine square. Okay? That's brilliant because in the denominator, what can I do? I can do the difference of a square, right? So it's going to be c plus s, c minus s, and then c plus s square. That's great. So I can get rid of that. Then we do have the desired result, okay? That's good. So the point here is also make sure you memorize it with the 1 and then doubling of a sine, okay? That's great. And yes, using that, you can also work with the half-angle formula. Okay, half-angle formula. Please memorize. These all half-angle formula. It's not in the booklet, okay? You can derive this half-angle formula from the doubling of cosine. You can also derive this using these 2 information. Very, very important, especially the doubling of tangent. Super popular. So please memorize it. It's not in the booklet, okay? Fine. So also, we are able to discuss the sine, cosine, tangent just in terms of tangent. And you may ask me, okay, where do I use it? Right. So first of all, memorize it. And then it's a very popular for who? Integration. So if you, if examiner feels fancy, he's going to ask a very, very advanced integration problem using this type of identity. I think it appeared once or twice throughout the years. To do that well, you need to know this formula, okay? So make sure you are aware of it, okay? I'll strongly, and also be able to prove it, okay? Very important. Sure, the next thing I want to talk about is what? Working with those identities with the inverse trick. Super important, right? Super important. What is important? Domain and range. You should know it. You should definitely memorize the domain and range. So important, okay? I wouldn't talk about too much on it. But one thing, let's talk about it. Inverse sine of a half is a pi over 6. That will be, negative pi over 3, right? And for this one, it cannot exist. Sorry, it's indicate the negative because the domain was from -1 to 1. So this does not exist. For D, right? inverse function, input becomes the output, you can say pi, right? Is wrong. Got to be very, very careful. And very careful because arc sine x, his range is what? From negative pi over 2 to pi over 2. So make sure that it cannot come out as pi, okay? What you want to do is evaluate the inside first. Sine pi is simply 0, right? So inverse sine of 0 was 0, so the answer is actually 0. So make sure you are aware of the range of arc sine x. Same thing for cosine. You can try this out with these examples, but sure, you know what? I'm not going to put this as a 3 pi over 2. Okay, that is a wrong answer. Why? The range of our cosine x is from where to where? Talk to yourself. You're absolutely right. It's from 0 to pi. Okay, so it's not in the range. So what would you do? Yes, you're going to evaluate the inside first and then work on it. Okay? Please attempt yourself. Pause the video and attempt yourself. Okay? Sure, you know what? This is a... Sorry. Very, very popular example, right? Sine of arc cosine x. In fact, I want you to memorize this with who? Cosine of arc sine x. Okay? It's very popular for integration as well as a trigonometry. And then, the main point here is to work with what? Main point here is I do not like that I have a sine outside, right? Because I have inverse cosine. So I hope that I'm compositing with the cosine so that I can use a property of a function, an inverse function. Remember, the function composite the inverse function is going to come out as an x. But I don't have a cosine there, no problem. You're able to convert using the Pythagorean identity. Right, so here, I wrote it here. What we are using here is the Pythagorean identity. There you go, sine theta is a plus minus 1 minus cosine square. But then our cosine is only from 0 to pi. So the sine is going to actually be positive because it only sweeps around the first. And what is it? The second quadrant, right? So that's great. So then it's gonna be converted here, and I'm only compositing with the theta with the arc cosine x, and it becomes like that. Super popular identity. Please memorize it, okay? Oops, sorry. What I want you to memorize with him is that this is also same as cosine of arc sine x, okay? Just memorize it. Do not hesitate to apply that identity right away as soon as you see one way or the other. Okay, that's great. So sure, another identity that I want you to memorize, there are two of them. Arc sine x plus arc cosine x is equal to pi over 2. Arc tangent x plus arc tangent 1 over x is pi over 2. Not only memorizing, be able to prove it, okay? There are many ways of proving it. Either using composition, as you can see, and then use the compound angle, or simply just the right angle triangle. Okay, I'll leave the exercise, and I think I'll put the detailed description in the PPT. You can read through. And yes, you know what? Every time you're working with the inverse trig, it's really an angle. So you can think of it as some sort of a theta, right? So here, I'm really dealing with sine 2 theta. You know what I mean? So, it asks you to use what? Double angle. It is just really working on the double angle. So it's fine. So what you can do is to expand it like a double angle. So there we go. We have a sine of arc cosine x and cosine of arc cosine x. What is very trivial to expand? Cosine of arc cosine x will be simply x. That's fine. But what about sine of arc cosine x? It's going to be who? Square root of 1 minus x squared. Then I'm multiplying this by 2. Okay, so that's a way to go. Okay, so make sure you will think of this as an angle, and as soon as you see some multiple there, you want to apply some angle formula, such as a double, triple, half angle, you name what. Okay, there are many example questions along with that, so you can try yourself. And yes, I'm going to talk about the trigonometric function. You should know already how to sketch things around with the sine and cosine. So things like that, if you want to sketch, what do we do? Indicate with the amplitude. So, with the 5, it would have been plus minus 5, but I've got the vertical shift, which is the principal axis. That's your principal axis. So it becomes 3 maximum, -7 minimum, right? So I'm going to indicate then the 3 and then -7, right? Sure. And then I'm going to consider this as a starting point. So, it's a periodic function. There's no really start. However, one full cycle of a cosine can start from whatever the value of x that makes this 0. So let me start with -pi. And then in order to, make a complete one cycle, you need to go one period further. How do we work out the period? You're right, 2 pi over the b, 2 over 3 becomes 3 pi. So I'm going to terminate the cycle at 2 pi. Right, and then we already know the principal axis was -2. And then what's in the middle was, what was it? It's going to be between -pi and pi, or 2 pi, right? So you add them and divide by 2, it goes with the plus pi over 2. Okay, then your cosine function, if it doesn't have a negative, comes from maximum to minimum to maximum, right? So I know the shape is going to look like that, but one more thing, I need to indicate where my y-intercept is so that whether it's going to be positive or negative should be indicated on your graph. So if I put 0 there, I've got 5 cosine 2 pi over 3 minus 2, but that's a negative, negative, so I'm sure that my y-intercept is going to be around there. So the graph is going to look like that. So be confident after having one cycle, then you're just going to repeat the shape with the same period and the same amplitude, okay? So what I'm really interested in is just where it starts, where it ends, and that can be shown in the domain, okay? Easy peasy, lemon squeezy. So I've written down all the details in the PPT. I want you to check yourself, okay? So it looks like that. Sure, also be able to work with the tangent function graph, right? It comes with the vertical asymptote when, this is pi over 2 plus k pi, so indicate where the vertical asymptote is going to be. That's the only thing you really need to check, all right? And yes, another thing, the period of a tangent is a pi over b, right, rather than the 2 pi, unlike the sine and cosine. That's the only thing that I really have to warn you about. Be able to sketch the tangent function too. Why? Because again, let me remind you, this you should be able to sketch after having done with who? Complementary angle, and then working with the tangent function, indicating well with the vertical asymptote and all that. Okay. Sure, we should be able to, derive this function from the modeling. What is very, very important? Ferris wheel, right? Very, very popular to work with the modeling of sine and cosine. And for those problems, what I want you to do is sketch the graph first. I want you to sketch the graph first. So what I mean by that is, if you look at this problem, where does it start, right? It starts from the minimum point. So on the graph for the circular motion, either you're gonna have either sine or cosine, and I'm gonna start from the minimum, and it's gonna go up and down like that, okay? And for that one, what graph is gonna be the best fit? Would you use a sine or cosine? It doesn't matter, right? However, if it starts either maximum or minimum, I strongly suggest that you try to graph with the cosine. So I'm gonna have a y negative. Okay, because if it was a positive start at the maximum, negative coefficient reflects it, so it starts minimum. So that's the first thing I'm going to do right away. And then the amplitude is going to be always the radius of a circle. So we have a 61 cosine. Okay, then I need to choose the coefficient that is going to give you the period. What does it say? It says 2.4 rotations every hour. Okay. And I think the question was asking you to use the time in minutes. So let's talk about, so one rotation is going to be the one period. So 2.4 to 60 minutes. Okay, I want to talk about the period for one revolution. So what we can do is 60 is equal to 2.4x. Right? So then we have x being, 60 over 2.4. right? So that's going to be, but you know what, let me write it as a B. I think it was a 24 or 5, something like that, isn't it? Yeah. 12, 0. Sure. Oops, my bad. It should be 25, my bad. Okay. Right, that's great. So that's my period. Sorry, that's my B. Is what I'm going to put, okay? But I can't leave it like that because if I didn't have a vertical translation, the maximum minimum would have been plus minus 61. So what you want to do is to indicate, my minimum is at 13, my maximum would have been where? 135. So, you know, how much do you need to add these? I'm going to add by, what is it? 74, right? So then it's going to obtain you the minimum of a 13. So the point of this question is to remind you, if you have a worthy problem, especially the Ferris wheel, just graph it. Just graph the function, right? Does it start from the top? Does it start from the middle? Does it start from the minimum? If it either starts from the minimum or top, it is going to work with the cosine. If it starts in the middle, which indicates the principal axis, I'm going to use a sine, okay? And then depending on the shape, you're going to also indicate with the negative. And the rest is just pretty straightforward, okay? Blah, blah, blah. You can have a look, you can check yourself. It's pretty okay. Sure. Oh, my bad. Yeah, sure, my bad. Right, so period was 25 minutes, my bad. That is 25 over B, so B should be 2 pi over 25. Yeah, you're right. Okay, let's check the slide. Gotta note it there. Yes, not only using the identities to convert, equation is the most important part because not only topic 3, throughout the topics you get to see them, okay? So the very first example is the analytic method. Let's talk about the analytic method. Sure, so what I mean by the analytic method is this, you know, if I go with the trivial example, right, let's say sine 2x was negative 1 over 2. X was defined, let's say, from negative pi to 0. Okay, how I want you to solve this one is, okay, think about any acute angle that makes it half. Forget about the negative, right? So it was a pi over 6, wasn't it? And then I realize for 2x, it's going to be from negative 2 pi to 0. So I have a full circle. Okay, that's great. Oops. That's great. And then on here, I'm going to indicate a quadrant where I'm going to have, what is it, negative half. So that's going to be third and fourth. All right, so that's great. So we are looking at 2x being who? Negative. What is it? I'm going to go by pi and then 2 pi over 3. So, sorry. How much should I go? Negative pi over 6 and then negative 5 pi over 6. And therefore, the solution is going to be negative pi over 12 or negative 5 pi over 12. Right? So that is what I mean by the analytic. We need to know exactly how many solutions in a given domain. So when I'm solving a question like this, what I want you to do is to set up the domain well. Right? It's given by the x. But if you look at the tangent function, it goes by 2x minus pi over 3, isn't it? And that's the one I want to work with. So here, let's go with the 2x minus pi over 3. And what domain is it going to give you? Well, it's a bit of algebra, isn't it? So 2, it's going to be negative 2 pi minus pi over 3 gives you negative 7 pi over 3. And for the next one, it's going to be 5 pi over 3. So how I like to see this question is to draw as many circles as possible. For that one, I'm going to go, what is it, from 0 to 5 pi over 3. Or, what can I go? Negative 2 pi to 0. And last slice of pizza, which is negative 7 pi over 3 to negative 2 pi. Okay, that's what I've got. So on this one, what I want to do is what? Tangent being 1, right? So for that tangent function, to make it 1, I need to go with the first, third, so I have 4 solutions, right? We are aware of it. So as you can see, I'm not going to bother solving there because it cannot have either first or third quadrant. And from this, what I'm going to do is 2x minus pi over 3. What do you want? I want them to be the angles coming from here. The first one is going to be, what is it? Right, the acute angle that makes tangent 1 was pi over 4. Right, that's great. And I want to send it to the third quadrant. You got to use a reference angle. I go by pi, add by pi over 4, so it's going to give you 5 pi over 4. Right, that's great. And for the ones clockwise, you just have to subtract by 2 pi of the same angle. Then I'm going to go with negative 7 pi over 4 and negative 3 pi over 4. Then you can find the x by rearranging, isn't it? You can add by pi over 3, divide by 2 is how you solve it. But the point of this question is that you're able to solve it analytically. You need to know the exact number of solutions and find the value after some rearrangement. And I think detail of this problem, I put it here. You can read through. And then the solution must come out like that, okay? Please check yourself. And this is a very, very popular questions on the exam. Sure. Right. And then let's have a look at this type of equations which requires you to use what? Trig identity. We're talking about the analytic equation. Now we're moving on to identities. So what I mean by the identities, let's have a look at this. So what you want to do for this problem, okay, is that I don't like, look at this, I don't like with this cosecant and tangent. I'm more familiar with what? Sine and cosine, right? So what you want to do is the following. Let me quickly copy that, okay? I'm going to unclick that, add it onto the new slide. There you go. So on this one, what I want you to do is I'm going to go with 1 over cosine 2x is equal to 3 over 2. Oops, I bet, not the cosine, it's a sine. It's cosecant. Okay, and then 3 over 2, and I have a sine x over cosine x. Okay, that's what I have. And on here, what I also want you to do is to realize, right, that this is a doubling of a sine. So I'm going to go with the 2 sine x cosine x. And you know what? Don't worry about it. It's not equality. It's not inequality. So what you can do is play around with the rearrangement by multiplying without worrying the change of direction. So, let's do I'm going to multiply by 2 sine x cosine on both sides. Then you're going to have, what is it? 1 is equal to who? 3 times sine squared x. Isn't it? Is what we have? 2 sine x. Sure, is what we have, right? Oh, sorry. We were having a negative half here as well, my bad. Then you're gonna have a minus sine x cosine x, okay? That's great. And then the problem for this one is that, if this was a 0, it would have been beautiful. You can just factorize by the sine x. But I have 1 there. I wonder how I can solve it. If you get a question like this, what I want you to try is always try to convert the 1. Using what? Try to answer yourself. Absolutely right. I like to use the Pythagorean identity. So if I use a sine squared x plus cosine squared x is what? Let me select the right hand side. and then paste it. Very good. Move around there. Very good. Now you realize that this looks like what? A quadratic equation, isn't it? So now I have, if I rearrange the left-hand side to the other side, I've got 2 sine squared x minus sine x cosine x minus cosine squared x is equal to 0, right? That's great. So I have a 2 sine, cosine, cosine, minus plus. Aha, there you go. Therefore, what do we have? It's going to be sine x is negative 1 over 2 cosine x, and sine x is going to be cosine x. But whenever you're solving the trig equation, what is very important? The domain is important, so anything with the negative is not possible, so I'm going to get rid of it because it's only talking about the first quadrant. And whenever you're given sine equal to something of a cosine x, just divide it, making what? Tangent x being 1. Therefore, the solution is going to be simply pi over 4. Okay? So, what I want to remind you here is that try to be open with the substitution, such as 1 as a sine squared plus cosine squared, using the Pythagorean identity. Okay? I think the detail of the question, I put it there, so please check yourself. Wow. Both of trigonometry. So many formula. Okay? Let's get to it. Okay? Fasten your seatbelt because there are many formula for you to memorize. Please be able to derive it. I've just put it on the slide here to remind you why this is so important and be able to prove it. You can prove this by what? Sine 2x plus x and use the compound angle. But make sure you memorize all that. You're taking an exam, okay? You should memorize the things that is not on the booklet. All right? Okay, so that's one comment on the compound angle. And then the next thing is, yes, I'm not going to talk about the compound angle formula. You should know it already. It's in the booklet. But I'm talking about the application. It's called a factor theorem. So we have a one sum to product, and then later on we're going to talk about product to sum. And these are very important identities for you to memorize, okay, for solving certain trig equations and induction, okay? Let's have a look. Sure, if I have a question like that, and you know what, I want to use those formula. And if you ask me how do you solve it, it's the following. Let me quickly check if never mind. Sure. So how would you like to check it? What I noticed is that this reminds me of who? Triple angle formula of a cosine. So that becomes cosine 3x. Okay? Easy. Peasy. Lemon squeezy. So that reminds me of a minus cosine 2x is equal to 0. That is brilliant. Okay? And what I want you to realize that using the sum to product formula, I can actually put it into the multiplication form. So, using the formula from the previous slide, that this is going to be same as negative 2 sine x over 2 sine 5x over 2 is equal to 0. Brilliant. And then why we prefer the product than the sum here? Because if you're working with the equation, if a product being 0, you can use what? You're absolutely right. Null factor law, right? That means we're looking at what? Either the first part has to be 0 or the second part has to be 0, and it's quite trivial to solve it. I think it is going to come out as a 0, pi over 5, 2 pi over 5, something like that in the given domain. Okay, you can check yourself. Can I have a 4 pi over 5? 4 pi over 5? Yeah, sure, right. Can I have 3 pi? No, I cannot have 3 pi over 4, but 4 pi over 5 is fine. So yeah, sorry, can I have a pi over 5? No, I cannot have it, sorry. So only these 3 solutions are going to be the roots, okay? So it's a very popular form for solving equation. Make sure you are aware of it, okay? That was the exam question, by the way. And now we're gonna have a look at the product to sum. right? It's very similar, as you can see. It's just, it's an extension of a compound angle. You should be able to prove yourself. Please pause the video, make your own notes, and then memorize it, all right? And why is it popular? Because it's popular for the induction. Okay, it's popular for the induction. So what I'm going to do is, I'm not going to go over the basic step because it's trivial, but let's have a look at the induction hypothesis. Implies the result to prove. I'd like to talk about that. Where am I going to talk about that? In the next slide. So let me quickly cut this. Okay. Whee. Yes. Undo this. Put it onto the next slide. Boom, I have it. Right, beautiful. Beautiful. So here, let's try to write down the induction hypothesis first. I'm going to go with the n equal to, let's say n equal to k is true. Then I have a, what is it? Sine x plus sine 3x goes all the way to who? Sine 2k minus 1x is equal to who? 1 minus cosine 2kx over 2 sine x. All right. And for the, it's always nice. It's always nice to write down the answer for the induction, and the induction is great because I already know the answer. So what I'm going to do is just going to copy that, okay? Now, can I copy this once again? Sure. And I'm going to paste it, put it right here. And I'm going to just increase for what? K plus 1. Right? So what I need to do is just add the next sequence. So it's going to be plus sine 2k plus 1x. Okay? It's very good. So on the right hand side, I've got, what is it? 1 minus cosine 2n plus 2x over 2 sine x is what I have. It's a result. I want to prove that it's the aim. You can't use it, but at least I know where I'm heading, right? Okay, that's great. So what I want you to do is simply start with the left-hand side. And then, using the induction hypothesis, all that, right, all this can be replaced by my induction hypothesis. It's beautiful. So that's what I'm going to do. So let me select this. Once again, select that. I'm going to paste that. That's great. So that substitutes all the highlighted part, and then at the next sequence. I don't know why. Yeah, there you go. Paste that. Okay, beautiful, beautiful. And then what you should realize is that, I will put it into the common denominator. So it's going to be, what is it? 1 minus cosine 2kx. Let me go in red. Plus 2 sine 2k plus 1x sine x over 2 sine x is what I've got, right? That's great. Okay, and one thing I want you to remember is that if you look at this, paste that. Brilliant. What I want you to realize is that product to sum formula. If you go back to the slide and then check what was the formula to decompose this as sum was, in fact, the difference of a cosine. So it's going to be cosine of two angles, subtraction. So that angle minus that is going to give you 2kx minus, okay, let me put the bracket more beautifully. So like that is what I have. And then the second term was addition. So it's going to be cosine 2k plus 2x. Beautiful. Is what I have, all right? Okay. So I'm going to replace that on here. So what I like to do is maybe I will copy that. And then I'm going to raise this up. it's okay. Sometimes stuff happens. We keep going, okay? Paste that. All right, and what I want to do is to get rid of that, right? And then replace with who? With this is what I'm going to do. Beautiful. I think it would have been better if I just typed it. Anyways, right, so here, is there a term, anything that you see canceling out? Voila, very good. These two cancel out. So I'm just left with who? 1 minus cosine 2k plus 2x over 2 sine x as desired, okay? So induction is beautiful because you already know the answer. You know where you're heading to. And then since we proved that, oh, sorry. What is here? I had to write it as a k plus 1. So this would have been 2k plus 2 after the substitution. Don't forget, right? The n is the general statement. We haven't proven yet. So you got to write in k. And that's what we have, okay? Why am I making this example? Because it's important for you to be aware of who? Sum of the product. Okay, vice versa. Very good. So another application of, what is it? Compound angle is to be able to combine those sine and cosine with the same input but different coefficient into one trig ratio. Okay, make sure you are able to do this, and then this is a very popular example to find the maximum minimum. Right? Sometimes you see a bunch of questions like the 1 over, you know, let's say I have a 2 sine x plus cosine x plus 1, and for example you want to find the minimum of this, and you know what, yeah, you can differentiate this directly and then find the stationary point and check on whether it's a maximum minimum inflection point. You can do that, but it gets then very complicated, right? So what I would like to do is maybe I would just convert that as a 1 over k sine, you know, x plus phi plus 1, and you know, for a fraction to be the minimum, you want the denominator to be the maximum, all that, you know, and sine becomes maximum when the inside is a pi over 2, so you just have to solve x plus phi being pi over 2 a lot quicker than differentiation method, okay? And also some graphing question comes along with it, so make sure you memorize this skill, okay? Okay, you know, sometimes they ask you with the x minus phi, with the cosine, doesn't matter, because if you remember the compound angle of a cosine, that's cocosasa with the positive inside. Have I written it? Nope, I haven't. It's okay. Let me just quickly solve it for you. So what I want you to do here is just use a compound angle. I have a r cosine theta cosine x and plus r sine theta sine x. So you're just really comparing with the coefficient, aren't you? So boom, boom. What I want you to do is compare with the coefficient of the cosine x. Here was a 1, so you have a, what is it? R cosine theta is equal to 1. Okay? If you look at the coefficient of a sine x, I have a, what is it? The R sine theta being root 3. So your job is to solve simultaneously for finding the parameter R and theta. What I like to do is maybe I will divide this, then I've got the tangent theta being root 3, therefore theta is a pi over 3. So I've got that theta. Find the r, what I like to do is maybe just square it and then add them together. Then you have a r squared. Remember, you know, sine squared plus cosine squared simply becomes 1 is 4, therefore r is going to be 2. Okay, so then you can combine them into one trig ratio. So it's going to be 2 cosine x minus pi over 3. Then you can use it for finding the maximum, minimum, and whatnot, depending on what the question asks. Okay? That goes with the trigonometry. Now let's go on the vector. Okay, let's go with the vector. For the vector, what you should be impeccable first is the algebra. You know, the addition, subtraction, dot product, cross product, and then what sort of skills we need is the next, okay, aim of the lesson. So let's talk about all that. So all this chapter here is really talking about the operation, whether you can add or subtract and multiply. Okay, so what I want you to remember is that every time you have addition of the vectors or difference is really a diagonal of a parallelogram. Remember, if I have, for example, A vector here and then B vector there, the resultant vector is, what you can do is draw the equal vector B and A here. So the diagonals of a parallelogram is going to be the resultant vector. So you can always think of it as what? Diagonals of a parallelogram. That's the one thing that we're going to use. So here, if I look at the difference and addition absolute value, it's really just asking you what's going to be the length of what? Diagonals, okay? Oops. A, G. So that's what they're asking, okay? And why it is important knowing that is because you get to see some special case of parallelogram. You can see sometimes a rhombus, rectangles, and square, and whatnot. And here, if I look at this, I've got unit vector, right? So unit vector means the length is 1. So actually, you're looking at the parallelogram with equal length of a 1. So that actually creates what? Rhombus, right? So in fact, this problem here becomes the diagonals of a rhombus. And you know what? You can apply as many properties of polygons possible if you want to, okay? So what I do know is that if I draw the bigger picture, and you know what? I wonder if they have a shape of a parallelogram. Do they have a shape of a parallelogram? They don't. Never mind, okay? But let me just put a bigger scale. So, boom. Does it look like an equal length? Just be cool, be generous, please. And sure, this is now the rhombus with the length of 1, isn't it? Let me call this as A, and this is B. Then resultant vector is going to be the diagonal. So I'm going to do the A plus B. And then you know what? Let me call this is a minus B. And then among the many properties of rhombus, they're right angle, aren't they? So you can use a right angle triangle. Do not try to use a sine rule or cosine rule. If you have a right angle triangle, it's the best kind. So if I call the length of the rhombus here L, this is going to be L over 2, right? And then another property of rhombus is bisects the angle. So the angle between them was given by A, was it? Sorry, alpha. I think I meant to type alpha here. So that would have been alpha over 2. Then you know what? Then you have a right angle triangle. Alpha over 2 becomes what? Is L over 2. And then remember, it's a unit vector. The magnitude here is a 1. Therefore, cosine alpha over 2 is simply L over 2. Therefore, the L, the magnitude of A plus B, is going to be simply 2 cosine alpha over 2. So the problem, the aim of this problem is that you realize sum and difference is really the diagonals of a parallelogram. And depending on the length or the angle, you realize that you can use some property of a polygon, such as in this case, rhombus. Okay? Don't attempt this by the cosine rule, it gets nasty. Okay. Then yes, another property that I want you to use is that every time you have an absolute value, right? For example, in real number, what did we do? If I have an absolute value of x squared, there was x squared, wasn't it? And then if I had a complex number, the modulus of z square was a complex number times complex conjugate. Remember that? Okay. But for a vector, I want you to memorize this. For a vector, modulus of a vector square is the dot product of itself, okay? So make sure you know how to convert those absolute values depending on the real number, complex, and the vector, okay? So, what I would like to do here is maybe I would just square it, then you can solve it right away. It becomes A plus B dot same vector. Just try yourself with the a minus b dot with the same vector. You can distribute, then you're going to end up having 4a dot b is a 0. What do you know? A is a perpendicular to b. Okay. By the way, dot product is commutative. Remember, means if you change the order, it's the same. Okay. But yes, not cross product, which we're going to talk about in a second. But yeah, you know, absolute value, be able to convert, okay? Not just the vector. All right. Sure, another formula that I want, that I think this question is beautiful because it really talks about all the formula that we need to be aware of, right? Every time you see some dot product, it is to associate with the cosine, right? Remember, a dot b is a modulus of a modulus of b cosine theta, right? But what was a cross product? But, you know, remember, dot product gives you a number, it's a value. Cross product gives you a vector. So to get along with the sign, I got to put absolute value of cross product. Gives you the modulus of a, modulus of b, sine theta. Okay, please remember that. And this problem really talks about these two formula in hand, and I think it's a nice one to sort of summarize. And yes, this is what I'm talking about, right? If you see, you know, switch order of a cross product, it is really insinuating that you are working with the non-commutative property. Okay, so make sure we are aware who is commutative, who is not commutative between the dot and cross product. So what I would suggest is that, you know, if it's a cross b minus, what is it, b cross c at the moment is equal to 0. There's nothing I can do at the moment because it's not in the same order. But no problem, right? From the right-hand rule, if you multiply by negative, you change the order of a cross product. So in fact, this becomes, if I just select this, and yes, I'm sure. Then it becomes, what is it? Minus. And what do? We just simply have to change the order, right? I'm going to do C, B. Then I can factorize it, right? Because in the same order. So we're going to go A plus C cross B is what we have. Understood? Just a nice example. And then one more thing that I want to mention about the cross product is there's more utility on the cross product than the dot product. Dot product is talking about the angle, right? Whether it's obtuse or acute, the right angle. But for the cross product, there are a few properties such as a collinear, right? When are the two vectors are collinear? When their cross product is equal to 0. Okay, area of a triangle in a parallelogram. Triangle is going to be 1/2 modulus of A cross B, so that I don't need to worry about what? The angle, right? I don't need to compute that. I just need vectors and volume of parallelepiped. It's not in the syllabus. It's only for the AI students, but sometimes you can have it in either section B on paper 1 or paper 3. So I still have to talk about that, okay? So if I quickly show you, sorry. This is the formula for the volume of a parallelepiped, and how does it look like? It looks like this, okay? It looks like that. And then one of the applications of the parallelepiped is that of the volume formula of the triple product is coplanar. So make sure you are aware of the dot product, cross product, and triple product being 0. By the way, I think, sorry, this must be in that direction, okay? Sure, so make sure we know all these 3 products, dot, cross, triple product being 0, what does it mean, okay? Thank you. Now we're gonna go with the vector equation. So now we're able to add, multiply in 3 different ways. We should be able to use it. For what? We're gonna talk about with the vector line equation. Is what I'm gonna do next time. All right, let's have a look at the topic 5. fasten your seatbelt. It is going to be the most important topic for AA students, and we're gonna go on the layers of differentiation and integration. And without further ado, let's get to it, okay? So the limit, very important chapters, and it's talking about all the differentiability and whatnot. So a very, very important concept here. One thing that I want to specify for the limit is that you are aware of the left and right limit. If the limit wants to exist, you need to make sure to check with the right limit and left limit, okay? So a very popular example to come along is things like that. You know, I want to show that whether this limit exists or not. And how you want to check is to go with the left limit and right limit. And in fact, what is so interesting about this example is that I've got an absolute value, which is a piecewise function. You know what I mean? So the absolute value of x minus 3 is x minus 3 if x is bigger than or equal to 3, negative x minus 3 if x is less than 3, isn't it? So, you know, depending on that, because of that, we have a different left limit and right limit, right? So the left limit is going to come out as a negative x plus 3. And then if we evaluate that, let me quickly show you. Oops, yeah, there you go. Right, the left limit is going to come out as such, and if I'm doing some algebra and factorization, x minus 3 is going to cancel out, very good. And what's going to happen, the limit is in fact going to be negative 6, you see? But if you actually compare it to the right limit, which is now going to take the positive part, and then if you do the similar step, the limit comes out as 6. Hence, the limit of that function does not exist, okay? So a good example to show, to know the difference between the left limit and right limit, you have to check both of them to see whether the limit exists or not, okay? It does not exist. All right, let's move on to the next slide. Okay, another thing that is very important for you is to work with the squeeze theorem. I don't think that it's gonna count for the paper 1 or 2, but a very popular example for paper 3. Okay, so make sure you are aware what it means by the squeeze theorem. If he goes to A, and he goes to A at a certain value of x, he's going to go to A as well, right? So if I quickly, the squeeze theorem definition by the limit, and if I show you by the picture, it looks like that. It looks like this, right? So whatever the crazy behavior I have on the fx and gx, whatever in between the hx must converge to the same limit, okay? And then also, there are many examples that you can associate with the squeeze theorem. I think that would come out as an example, but these are the result of using the squeeze theorem that you should memorize. A very, very important limit here. Among them, let me quickly show you the example. Sorry. Yeah, this one here. This is known as what? Fundamental limit of trigonometry. So important. I do believe some questions can come up either in paper 1 or paper 3, especially with proof questions, okay? And also using the squeeze theorem to get, when you send to infinity, it becomes 0. There's another variation of this limit that I want you to also memorize. It looks like that. If you make a substitution, these two forms also should be memorized, okay? Pause the video, make a note of it. You should see, whenever I have this dodgy 1 over x, I want to multiply by his reciprocal is the way to do, okay? So another limits that you should memorize, tangent theta over theta. Because of that, you can actually prove all this, okay? So there will be some questions to prove this, and then you can use either L'Hopital or squeeze theorem, okay? But it's good to know the result, because if you know the limit, then you can say, okay, because of this limit, things are going to be etc. So some example that I can show you with that is maybe, if you have a limit theta goes to 0, let's say sine 3 theta over tangent 2 theta, okay? You might as well do the L'Hopital, but I don't want to, it's going to involve a lot of differentiation. So because we know the limit from the fundamental limit of trigonometry, I want to associate this as a limit theta goes to 0, sine 3 theta over 3 theta times 2 theta over tangent 2 theta, you know what I mean? and then I want to multiply by the reciprocal, which is going to be 3 over 2, right? So essentially, this all cancels out, preserving the same form. But why have I changed in this way? Because now I can refer to such limits, right? That converges to 1, that converges to 1, so that it's going to just remain as a 3 over 2. Knowing the limits help you, okay? You don't have to do the L'Hopital on that one. I wouldn't do so, okay? Sure, another example that you should memorize is this, right? The limit for the Euler's number, right? So for that one, another form that I would encourage you to memorize is if you let the u to be 1 over n, then this limit is going to same as a limit u goes to 0, 1 plus u to the power of 1 over u. Okay, make sure you don't necessarily have to know the proof. Memorize the proof, because it will be given as a question. Okay, so it will be given as, okay, do this and do that, hence prove this, right? But I think it is important that you memorize the limit. Okay, you don't have to know the process because it's going to be given as a question, but make sure we understand either this form or that form gives you the e, right? If you, if I let this to be x here, right? And also, you make a relevant substitution, it's going to be to the power of x, okay? Make sure we understand that limit as well, okay? Very important to memorize. Okay, let's move on to the next part. Increasing, decreasing talks about monotonicity of a function. So what I want you to do is not only differentiate. And here's the thing, I think this is a good example. Increasing, decreasing really is about solving inequality. Okay, after you having done the derivative well, solving inequality, what does that remind you? You're absolutely right. It's all about the sign diagram, isn't it? So let's have a look at 2 examples. So this is a trivial example, right? If I differentiate that quickly, after having differentiated that function, make sure you always try to factorize. I managed to factorize by the difference of a square. That's great. And then if you want to find increasing, you want to show this being positive, right? But like I said before, I don't like having the negative leading coefficient, so why don't you multiply -1 both sides, right? So, I've changed this way, then I'm going to apply the sign diagram. Do you remember that? It's going to be, what is it? -1 and 1, right? And then if I put the 0 in here, negative plus plus. So only this region is the one that I'm going to attack, okay? Very good. But on the exam, I don't think you're going to be given this question. More like a different form, like a quotient form, right? So let's have a look at some quotient form here, right? A rational function here, we're going to use the quotient rule for the differentiation, and I already have done it for you. So let's have a look. So blah blah blah. So please make sure that you are able to differentiate this, okay? And you know what? Let me quickly use that. So I differentiate using the quotient rule. Please make sure you can do that and factorize. And I want to use it for solving inequality. For increasing function, I need to make sure the derivative is a positive, right? So and here's my question. So I want to solve for being bigger than 0. Okay. Okay. So here's my logic. Tell me if my logic is correct or not. Okay. Oops. So my logic is this. Oh, okay, hold on a sec. You know what? This is a perfect square, right? This is a perfect square. Therefore, he's not going to determine the inequality. So that's great. Well, you're right. I don't like having the negative sign there, so I'm going to multiply -1, change the direction of inequality. So who is only going to determine the direction of inequality? Only the numerator does. Okay? You might say that. Sure, why not? And then if I apply the sign diagram there, then I would say, okay, I have a -1 and 3. Okay? And then if I plug 0 on the top, it becomes a -3. No problem. It becomes a minus plus plus. Right? Therefore, I would say, oh, the negative region will be just between this. Would be a wrong answer. Why is that? Because for the sign diagram, do not just work on the x-intercept. Also indicate the vertical asymptote as well. we have actually vertical asymptote at 1. So what I like to do is put it as a -1, 3, and 1. It indicates that it is a vertical asymptote. So in fact, sure, the perfect square doesn't change the sign. However, there are some number that I cannot have, which is 1. Right? So I need to think about that. So here it's going to give you minus, minus, plus, plus. So for me, I would say, all right, after that, I need to indicate x cannot be 1. Okay? For the sign diagram, to not just use the x-intercept, but also the vertical asymptote. Think about that. Okay? Very good. So yeah, as you can see, they distinguished it. Okay? Sure. So I've put some nice sign diagram there, so please check on the PPT. So tangent and normal, another applications, right? So here's the thing. I hope you understand why the questions ask in terms of tangent normal, because they really want to check on your simultaneous equation skills. Tangent normal is really just a simultaneous. Why? Think about it. Simultaneous. Okay. Is it right spelling? Simultaneous. Okay, so that's correct spelling. If you want to talk about the tangent normal, there are two things that you need, right? So the gradient and the y-intercept. I want to have gradient and then the y-intercept for a line equation. For that requires two information, is that the gradient and a passing point. And the passing point, you can get it from the function. So that's a one expression, okay? And then the gradient, you can get it from the derivative, right? So that gives you two equations to work with. So if you have a two unknown parameter in your question regarding with the tangent normal, that's really just working on simultaneous equation. So this is really just extended version of simultaneous equation. I want you to be aware of that, okay? Let's move on. So, things like that. I have a and b unknown for the, what the equation is this? This is a normal, okay? Well, right, this video is really not about the review from head to toe. It's really just about exam skills. So I'm not going to say, oh, okay, how do you find the normal? You know that the gradient of normal is a -1 over a prime of a. It's not a time to discuss that. We should already know. But more like we're talking about why such questions are asked, because we want to solve simultaneously, right? Okay, so here I've got, what is it? A and b unknown. Simultaneous equation. Where can we get it from? We can get it from the original expression, right? If it's a normal, it's a perpendicular to the tangent, and it's going to have the same passing point to the function. So I have that, and also the gradient of the normal line. I can get it from the derivative. So we can get it from, what is it? Two equations. I've nicely written down the equation for you. So make sure you read through the PPT. I've written down more detailed information, but if I want to show the equation, sure, after the derivative, I plug the passing point x equal to 4, and then compare with what? Compare with the line equation, because it must have the same y value, doesn't it? So I let that to be that. Oh, sorry, my bad, gradient, right? So the derivative is associated to gradient, and gradient of the function is the gradient of a tangent. So because I've got the gradient of the normal being -4, I'm going to do the negative reciprocal. Hence, I've got 1 over 4. And then what are we going to do? We're going to talk about the passing point. Right? We're going to use the original functions expression. Now you can work simultaneously to get the a and b. I will leave that as an exercise. Okay, but tangent normal is really about what the simultaneous equation. Okay. But way more popular example for the HO exam is the fundamental doesn't change. It is really working simultaneous equations. However, it is going to involve a lot of implicit differentiation. Okay? It is going to involve a lot of implicit differentiation. Sure. It doesn't matter. The principle stays the same. You get it from the original expression and the derivative. Okay? Have I written it? Sure, you know what? So I just did the implicit differentiation here, and then regroup by the dy over dx, and I've got that. Okay, so I got the expression. And let's go back. In the previous slide, Sure, he says, what is it? Parallel to the x-axis. It's very common. It's very common to ask. If it's a parallel to the x-axis, the gradient must be who? It's 0. Gradient must be 0. If it's a parallel to the y-axis, my friend, what would you do? The gradient must be undefined. Hence, if I got the derivative as a fraction, the denominator should be 0, right? It's a very common questions to ask. But yeah, if I quickly check it here, I got the derivative here. I want it to be parallel to the x-axis, so I want this to be 0. So only I'm going to work with the numerator, right? But you're right, I've got one equation, but it's got two variables on it. I can't solve it, but no problem. Like I said before, tangent and normal is really working on the simultaneous equations, right? So what you want to do is to plug that back into where? You're absolutely right, onto the original expression, right? I'm going to put it back into the original expression. So like I said before, it doesn't matter if it's the usual derivative or implicit differentiation. It's really working on the simultaneous equation between who? Derivative and the original equation. Okay, then you can solve it simultaneously. Boom, boom, boom. Easy peasy, lemon squeezy. Then I can find the desired k value. I will leave it as an exercise. Okay, I've typed it. Okay, because I just realized that the writing takes too much time. I want to condense the information so that I can give you as much information as possible. Essence of this video is not to discuss how to solve it fast or quickly or accurately, but it's about the required understanding to tackle the problem. So do not mind me jumping over the questions because I've written already, right? Thank you. All right, let's have a look at the next part. Fundamental theorem of calculus. So this is a very, very debatable. Okay, this is very, very debatable. I'm going to talk about one concept that is not discussed in any other books, only on Pearson. Okay, only on Pearson. But I think it's important to know. Okay, there's one discussion that the Pearson book gives, and I think it's great. It's something that the other books also used to discuss, but not anymore. But I think it's examinable maybe for paper 3, so that's why I'm going to talk about it. But yeah, the fundamental theorem of calculus is just going back and forth, isn't it? So, I have x squared, I differentiate, I got 2x, and I anti-differentiate, then I get the x squared plus c, right? So that's what the FTC was all about, wasn't it? But the reason I'm going to discuss a bit further is this kind, right? So I think it is important for you to know this expression, okay? What is this t? You're right, it's called dummy variable. So, for this kind, I want you to think about 3 conditions. You should have constant here. That's number 1. Number 2, I should have a dummy variable for the expression. And number 3, I should have, whatever the variable that you're differentiating with should be on the upper bound. Okay, so as long as you have these 3 conditions, boom, I can use the FTC. This is another version that we are well aware of. This is a definite integral. So there's a version number 1, version number 2. And Pearson, in details, talks about this, and I love it, okay? It's a relatively new exam, so I think I don't want to miss any points on the teaching. So even though you feel extra, it used to be examinable. I'm not sure if they're going to completely get rid of it because some books talk about it. So let's talk about it. So it's good revision for differentiation. So what I mean by that is if you look at that expression here, all right, let's have a look at this. Does it follow the condition? Dummy variable, constant, variable that I'm differentiating with, no problem. It just becomes what? Just replace the t with the x and you're good to go. It just becomes 2 cosine to the power 5x. It's just same thing, okay? Easy peasy, lemon squeezy, but of course, that wouldn't be given in the exam, is it? What we're gonna have is, it looks like this. Sure, right? So what is a bit strange? You're right. I've got the dummy variable, right? But I don't have the upper bound, lower bound being what we want. We used to want just a constant, and I used to want just the x, but I've got x squared. So here I'm gonna use several things. The one is the property of integral, right? If you remember the integral, let's say I want to have a, b, c. I'm trying to describe using the area, right? So if you want to get from b to c, I would do from a to c minus a to b, right? So that's what we used to do, isn't it? And yes, that's what I would probably do. Replacing who? Let me use a different color. Maybe I would call this as a so arbitrarily constant that I don't know, x and x squared. You see? So that integral, right, x to x squared, can be changed into a to x squared, a to x. Okay? So I'm using the linearity of integral. So easy peasy, lemon squeezy. So I've got that. Now what I'm going to do is to differentiate on both sides, right? I'm going to differentiate on both sides. Okay. But here's the thing, out of number 1, number 2, which form do you like? Which form is the one that we are familiar with? You're absolutely right. I'm more familiar with the second term. Why? Because I've got the lower bound being constant, x. So this will just, by the fundamental theorem of calculus, it's just going to come out as a sine x squared. You're right. But then the problem I have is the first kind, right? I've got the lower bound being constant. Good. I've got the dummy variable in terms of t. Good. But I don't have the upper bound. As what I wanted to discuss, I wanted to have just the x, but I've got x squared. I wonder what problem I have, okay? Let's see what we can do. Sure, so for that one, I want you to use chain rule. Okay, so this is what we discussed, this is what we have, but this one I want you to use a chain rule. Right, remember the chain rules? If I have a composite function, right, what happens? F prime gx times g prime x, isn't it? Okay, so this is the same thing, what I want you to do is to make some substitution. So what I would encourage you to do is this bit of jump, but let's say I'm gonna make u as x squared. All right, and then d over du is a 2x. Then boom, I've got what is it? The d over du times 1 over 2x is simply 1, right? I just rearranged it. Oops, du. All right, looks very wrong. Sorry. My bad. Okay, so du over dx is a 2x. Okay, so if I rearrange that to the other side, I've got 1 over dx is equal to 2x times 1 over du. All right, that's good. And for that one, I'm going to replace it. So that form, d over dx, is going to be 2x times d over du integral c. Okay, and then x squared will be replaced by u. And the dummy variable just remains the same thing. Okay. So now this is a beautiful dummy variable constant and variable I'm differentiating with. So I can simply use the fundamental theorem of calculus that u is going to go inside of a t. So it's going to be sine u squared. That's it. However, you're right. I want to put it back into who? X. Right? So the u was x squared. So if I replace the u with x squared, this is going to be 2x times sine x to the power 4 is what we have. Okay, so it is just a chain rule. It is just a chain rule. And obviously that's the kind that you are expecting for the actual exam question. Okay, so therefore, I'm going to combine these two, then we have it. All right, so another generalized rule for that is if I've got some other expression than x, no problem, just to use the chain rule. It's fine. Okay. Right, let's move on to the next part. Yes, derivative of the other functions, such as not only the polynomial, but also exponential and whatnot. No problem, no problem. But yeah, why I brought some random integration slide is because wanted to specify knowing the derivative is important because you want to use it for integration later by using the fundamental theorem of calculus. Because if you know, right, the derivative, what is it? Negative cosecant x is cosecant x times cotangent x. Integral gets very simple, right? This is just going to be, what is it? Negative cosecant 2x plus c. Notice that it's an indefinite integral, but also multiply by 1/2 by the integration by substitution. So, just good example to not realize why knowing the derivatives is important. So make sure you know what is the derivative, not only sine, cosine, tangent, but also secant, cosecant, cotangent, and arcsine, arccos, and arctangent. And as well as, not only just e to the power of x, but also a to the power of x. Later on, and when we discuss the integration, I prepare some slide for that. So, let's discuss more in that case, okay? So it's gonna come out as such. Move on. It's okay. Sure. So yeah, this is a very important example. So this is a typical paper 1. A lot of people, right, sometimes forgot how to translate between the f and f prime, and it could be a trap question, right? So actually, commonly, a lot of points missed in this section. So let's have a look. So yeah, this is some important information whenever you're trying to sketch from, let's say, the function or f prime. You need to indicate about its behavior, increasing, decreasing, what it means for the function and second derivative and whatnot. I've organized it for you, so please read the summary, okay? We all know this, okay? I will leave that as an exercise for you to read. So if you want to sketch the f prime, please try to follow these steps. But if it's also conversely, if you try to sketch from f prime to f, make sure you pause the video and read them through. Make your own notes, The essence of studying is, I think, really coming from the notes. It's not just about recording your data, but also of your brain to getting familiar with the concept, right? But yeah, let's, just forget about all the concept. I mean, you shouldn't forget about the concept, but let's actually get into the practice, right? So what if I was given the f here, and I want to sketch the f prime, right? What are the things that I would ask you to indicate? The first thing I would probably ask you to do is indicate where the stationary points are, right? It can be maximum, minimum, or stationary inflection point, isn't it? So I'm going to put boom, boom, boom. Okay, very good. And also, what would you do? Yeah, you're right. The inflection of f is going to be maximum, minimum of who? F prime. So remember, I'm trying to sketch the from f to f prime right now. Okay, so that's what I want to do here. And not only am I going to indicate the stationary points from the maximum, minimum, but also from the inflection point, right? This is concave up and down, something like that, down and up. So that's also an inflection point. All of those f is going to give you either maximum, minimum of f prime. Okay, so it really saves a lot of time for us to sketch. So what I'm going to do is this. Look at this. It's a concave down and up. So down and up for the f prime, that's going to be minimum. So maybe I'm going to, it's not on scale, so I'm just going to put it there. And also it's going to be up and down. So that's going to give you maximum. Voila, that is great. That is great. Then, did I say Groot? Okay. And then down and up. So that's going to give you minimum. Here's the thing. But at that point, it's a stationary inflection point, isn't it? So it needs to be on x-intercept, but it needs to be minimum of a turning point. So it's going to be touching. Okay, that's great. And then we can talk about from the concavity, whether things are going to be increasing, decreasing, right? So what I mean by that is, if it's a concave up of f, it will be same as what? Increasing of f prime. Okay, so look at this. I have a concave down, so things must be decreasing for the f prime. So I know things are going to look like that, decreasing, because there's always a concave down, there's concave up, so it's going to be increasing. That is good, something like that. And just, be bold, As long as we got all these extra points, sketching is very, very trivial, okay? So that's what my graph would look like. Notice that it's not on scale. And furthermore, I think this is also good thinking. What is? Look at the degree of the initial polynomial. If I look at the fx, right? This is eventually going down to the left. So it's coming from down and up. So it's odd degree, okay? It is odd degree. So if you differentiate odd degree polynomial, you get even, don't you? So that's why I'm expecting some sort of an even degree polynomial. So if it matches that, I'm very happy. Okay, I'm very happy. Anyways, let's have a look at the second example. This is a great example. Why? Because it really makes you think. What about this sharp point? What about this sharp point? Oops, sorry. What about this sharp point? Right, sharp point is not differentiable, right? So absolute value of x, remember, is not differentiable at x equal to 0. Remember? So if it's a sharp point, there's no derivative. Make sure you're comfortable of sketching around between the f and f prime. So maybe thinking like a polynomial is helpful. Right? Oh, okay, so I've got an odd degree to polynomial, so eventually my function would look like a even polynomial. And also make sure you have a sharp point is not differentiable. So this is what the answer looks like, so please check yourself. Okay? All right, let's have a look at the superstar optimization. So if you can do optimization well, you absolutely have no problem with the differentiation, because it's really the essence of everything, isn't it? It's got the modeling from topic 1 and topic 2, differentiation, and verifying whether that stationary point is going to be maximum minimum. So I have several things to say. Okay, so what I want you to check after having differentiated and finding this the stationary point is to check whether it's maximum minimum using the sign diagram or the second derivative test. I don't want you to do the second derivative test all the time, because it does give you, but I'm not sure if it's going to give you the most efficient way, right? So I've prepared some of the points when how it allows us to choose sign diagram with the second derivative test. Let's have a look. So, when it's easy to find the neighborhood, I will do the sign diagram. We're going to talk about what it means by easy to find the neighborhood. And number 2, when it's hard to differentiate twice, I am not going to do the second derivative test, but using the sign diagram. But it's, then it's vice versa, isn't it? When it's easy to differentiate twice, when it's hard to find the neighborhood, then I would use the second derivative test. Let's have a look. Okay? So think about it. I want you to think about it. Just pause for a second. Oh, well, sorry, I've mentioned it already. Yeah, sure. I'm going to do the sign diagram and second derivative test. But, without having seen this, okay, think why I will use sign diagram for that one and second derivative test. I mean, you can do both on this, but I'm saying this, I would definitely use the sign diagram. Why? Yeah, you're right. I don't think it's easy to differentiate twice, okay? So let me quickly show you. So I've done already some work for you already, so let's have a look. So, okay, for this one, I've differentiated. Remember, derivative of a cosecant is a negative cosecant cotangent. It's a negative cosecant square, so it's going to be positive cosecant square with the double negative. Boom. And I put it into the common denominator, and it looks great. I want this to be 0. And let's say the domain was defined from 0 to pi, and for cosine to be half would be simply just pi over 3. So far, so good, okay? But here's the thing. I wonder if I would use a second derivative test to verify this. But in fact, as you can see, to find the second derivative, I got to use a quotient rule on this, and I don't want to. Yeah, I don't want to. So I did a sign diagram. And it's brilliant to do the sign diagram. Why? Because I've got a, sine squared x, which is always a positive, so I'm not too worried about that, okay? But what I'm more worried about is, okay, so if I have a 1 minus cosine x, and you're using the sign diagram like this. I've got a stationary point. What was it? It was pi over 3. Sure. then I have to apply the sign diagram. I just have to find the relevant neighborhood. This is what I mean by the neighborhood. I want to choose a relatively small value that I can evaluate for my value for the derivative, and a bit bigger value in the neighborhood. Okay. Sure, you can then apply maybe a pi over 4 here, and for this one, I'll go with the pi over 2. Why not? I think it's fine. Oh, oops, sorry. Is it okay to do the pi over 2 here? I think so, right? Because cosecant is a 1 over sine, and cotangent is a cosine over sine. So, that would become 0 in the denominator at pi over 2, so that's okay. So that's great. So I've got the 0 here as a stationary point, and if I put pi over 4, I don't care, all right? I don't care about the value, I only care about the sign, you see? So if I put pi over 4 for this one, it's root 2 over 2, cancels out, 1 minus root 2, root 2 is bigger, so it's gonna be negative, hence indicating decreasing. At pi over 2, cosine pi over 2 is a 0, so I've got 1 minus a 0, boom, positive, hence increasing. So I'm going to have minimum right there. You know what I mean? Sure. So I would not use a second derivative test on this, but just using the sign diagrams looks great. Okay, so, and same thing, but on contrast, if I got a polynomial function like that, I found the stationary point there, and also it's so easy to differentiate once more, then the simple second derivative is going to be enough, okay, to verify the maximum minimum. So I want you to be always careful what you want to do to determine whether it's going to be maximum or minimum, okay? Let's have a look. Sure, and a few more comments. I can't go over every possible optimization problem, but the one thing I want to talk about is the fixed constraint. In IB math, on the optimization at least, you really just want one variable. But sometimes your question might involve more than one variable, and that means you need to use some substitution to convert in terms of one variable, and that substitution can come from the fixed constraint. Okay. It says, find the circular cylinder greatest volume that can be inscribed in the right circular cone with altitude of 20, diameter of 10. Okay, sounds very fancy, doesn't it? But yeah. So one more comment. One of this worthy problem, I think it's better to visualize. Okay, make sure you visualize it. So what do we have? Inscribed cylinder. So who is a right circular cone is going to be much bigger. So I have that, right? And then I'm going to put, what is it? Cylinder. Sure, that's great. So, just quick sketch always helps, okay? Sure, so on this one, for the optimization, it's always important what I'm looking for. It says greatest volume, so I need to have a volume expression of that cylinder, right? Which I don't know his radius. Height, I don't know. Right, so the volume, RH, is going to be given in terms of two variables, isn't it? So it's going to be pi r square h, and I don't like it. I do not like it. Why not? Because I've got two expressions. We really want to have one expression to start differentiating. So before the differentiation, we need to find the relevant substitution, and that's usually come from where? Fixed constraint. So here the concept of a fixed constraint that it has to be inscribed in the cone. And whenever you have a 3D shape, it's always better to make a cross-section and try to derive some information from the 2D shape. So if I make a vertical cut, it's going to be a triangle, and I've got what? Rectangle is what I have. Okay, that's great. And from here, what information can you find, right? Many information you can derive, but I would probably use a similarity, right? So the gradient here must be the same for a big triangle, a small triangle, right? So, this picture is too small, but it's okay. Yeah, let me just scale it like that. Yeah, sorry. Looks better. So here, I've got the diameter of a cone was 10, so the radius is gonna be 5, and altitude was how much? 20, right? Okay, so that rise over run, which is 4, right? So 20 over 5, the gradient must be same from either coming from this tiny triangle or slightly bigger triangle like there. So maybe I'll get the gradient from there. It's gonna be, notice the 5 minus r, and then h, you see? Then I've got it should be equal to who? H over 5 minus r. And voila, from the similarity, right? So, and then I can then use some substitution. This is a 4. So h is 20 minus 4r, and it's good to go. I will just substitute that h here. Then I got a function in terms of just r, for which you can then start differentiating. Okay, so for the optimization, if you have more than one variable, please be willing to substitute using the fixed constraint. So this is what the picture looks like. I've gotten the volume expression first, and what have I done? And then make some relevant substitution. This one using the similarity, and then you can find the expression there, and you can start differentiating, right? Blah, blah, blah. So finding there is pretty simple, so I will leave that as an exercise. No problem, no problem. Easy peasy, lemon squeezy. And here's another point that I want to make. What is this? Is the following. Look, check this out. Find the point of the curve x squared that is closest to point 10, 0. So, if I visualize this problem also, I've got a x squared, and I've got a point, what is it? 10, 0. It's an external point. And then you can find the distance function in terms of x and y, right? So I've got a x and y. But remember, we do not like having more than one variable for the optimization problem. So I'm going to replace the function expression as an x squared, right? So, and then the distance formula is going to be who? Square root of the difference of an x, which is x minus 10 squared plus, what is it? X to the power 4, if you look at the difference of y. So that's the typical distance formula, right? And then you can say, oh, you know what? From there, I'm going to differentiate. However, you know what? I don't like it because the expression is nasty, you see? Oh, by the way, it should be very comfortable that you are able to differentiate root fx quickly, right? So, yeah, you can put it in half, but, you're taking an exam in May very soon, so you should be comfortable that the derivative is always f prime over 2 root f. Okay, what are the other ones that you should memorize? 1 over f prime by the chain rule minus f prime over f squared. What else can we do? 1 over square root of f. If you differentiate that, what do you get? Minus f prime over 2f root f. So, this type of differentiation helps. However, when I'm trying to do that here, you could, but it gets very nasty. And before differentiation or before any computation, if there's a room for simplification, I strongly encourage you to do so. What I mean by that is I don't like square root, man, So what I like to do is d squared is equal to x minus 10 squared plus x4, and maybe consider the optimization on that expression without the square root. And you might say, oh, okay, hold on a sec. Is it allowed? Because technically it's a different expression. And the answer is yes, it's okay. For a certain function, not for every function. Okay? It's okay to do the d squared. It's okay to do the tangent composition to simplify. And it is not going to change the nature of inequality. Why? So blah, 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 I wrote it there. But the critical value, the maximum, minimum, is not going to change when you square things, or when you composite with the tangent. Okay, I want you to take your time reading this, and it just helps for simplification. Okay, so that is okay. That is okay. However, you got to be super careful with the cosine. Got to be careful with the cosine. So the reason this is okay is because you think about it. The square function or tangent. What do they have in common? You're right, they are both increasing in a certain domain. Okay, so whatever the, let's say, maximum value I found, the inside is going to also be a maximum because it's an increasing function. Same thing for tangent. If you found something of a tangent maximum, then the inside of that expression also has to be maximum because of the increasing function property. But if you composite with the cosine, you gotta be careful because from 0 to pi, what is the nature of a cosine function? Decreasing. Okay, so in fact, think about it. If I found the cosine fx, if I found the maximum of that will be who? Minimum of fx. So this is a very common mistake, okay, and it's often asked a lot in the exam. So compositing with the square or tangent, I think it's meant to be written like that, is fine. But cosine, I'll be careful because it's a decreasing function. I mean, you can use it, of course, but notice that the critical points would change, okay? So this is a very, very good example. I want you to take your time attempting this, okay? So I put some work on it, so, have a look. So this one, first, so gotta be careful when I'm compositing with the cosine. Am I looking for the maximum, minimum? Okay. Great. So another application is going to be now what? Inflection point. Sure, second derivative and whatnot. But one thing that I want to two things that I will discuss for the inflection regarding with the exam skills are the following. Second derivative being 0 does not imply that it's an inflection point. It does not guarantee. And you know what? You should memorize 2 counterexamples. Please memorize 2 counterexamples. What is x to the power 4 and ln x to the power 4 plus 1. So very, very common example to ask you whether their inflection point will happen at 0. And then the answer is no. After having found the second derivative being 0, you should check whether the sign changes or not, right? Of the second derivative. So, if you look at the, I think I'll put some example. Yeah, there you go. X to the power 4. Second derivative is 12x squared. So letting this to be 0 is x equal to 0. However, it's always concave up. So make sure you can come up with a counterexample that second derivative being 0 does not guarantee the inflection point. Okay. What was another example again? Can you tell yourself? I talked about it a second ago. The x to the power 4 plus 1. A very common example. Simply, the derivative of that is a lot more complicated. Another inflection regarding with the inflection point is, logistic growth, we do not learn this in AA with the topic 2, but you do see in topic 5 with the differential equation. And I want you to always remember that the inflection of the, where the concavity changes for the logistic growth is the half of the carrying capacity. Okay, if you found the carrying capacity, make sure half of carrying capacity is going to give you the inflection point. So you don't necessarily have to differentiate twice. It's not that simple if you differentiate this expression twice. So knowing the second, instead of doing the second differentiation, instead of doing differentiation twice, just let that function to be equal to the L over 2, and then it's going to give you the time when that inflection happens, okay? Or just memorize that formula. It's good to go. Okay, that was another comment with the inflection point. Let's move on to the kinematics. Okay, superstar. Maybe on the paper 2 with the use of a calculator, or paper 1 with differential equation. So let's get to it. So yes, I'm not going to talk about what it means and etc. But I'm only going to talk about the exam skills. Please be able to distinguish between the velocity and speed. It is a magnitude, my friend. Okay. So whenever you hear something like increasing speed or decreasing speed, you really want to work with the absolute value of the velocity, okay? Sure, so this is a typical, can you see it well on the screen? Sure. This is going to be typical velocity function, and if you want to find increasing region, it's going to be like there, right? So we just differentiate and then make it positive, okay? However, if it's a speed, please make sure the absolute value of t. Sketch that and then indicate where it's going to be increasing. Or if it had been a paper 1, you need to find when the if sign of velocity and acceleration matches, then it's increasing speed. So how do we typically see that? Velocity times acceleration. If their sign matches, positive, positive, negative, negative, that's increasing speed. So product of that is positive, is going to be increasing speed. Vice versa, right? The product of the velocity and acceleration, if that's negative, it's going to be decreasing speed. Okay, so using calculator with the absolute value function, or the product and solve the inequality, it would be typical paper 1. Easy peasy, lemon squeezy. And yes, make sure you're able to distinguish between who? Distance and displacement. Displacement is a typical, what is it? Definite integral. Okay, it can be negative because it's talking about the location. But this is how much you travel. It's the finding area under who? Velocity graph, okay? Please make sure you distinguish that. And the typical example that I want to also discuss in the kinematics is this. Sure, for that I need to copy that. So let me cut this. Sure, super nice. Typically, we see the acceleration or velocity expression in terms of time t, right? But now I've got the acceleration in terms of velocity. So that really implies that you're working with the differential equation. So if I have a acceleration, velocity, and displacement in terms of t, I'm happy. But if I'm not given it in terms of t, no problem. It's just solving differential equation. Let's have a look. So how do we express the acceleration? That's the first derivative of who? The velocity. Right, so great, then I've got the negative v squared plus 4, and what does that imply in terms of differential equation? You tell me. Very good, it tells me to work with the separation of variables. So I'm gonna rotate around, so I'm gonna have a, what is it? 1 over v squared, sorry about my handwriting, let me write with more care, with the more posture. 1 over, it's the same, v squared plus 2 square dv. I'm gonna match the the variables with the relevant variables, right? This is called the separation of variable, is equal to negative dt, and I'm going to integrate, right? Then do you remember the left hand side? This is a, what is it? Right arctangent, right? So this is gonna be arctangent v over 2, 1 over 2 is equal to negative t plus c. And of course, you can find the initial constant c using the, what is it? The initial condition. That's up to you, but this is how we work, right? So if it's not given in terms of t, no problem. Just differential equation is the way to go. So maybe I will multiply by 2 here, and composite with the tangent is going to give you v over 2 is equal to tangent c minus 2t, where you got to find the c from the initial condition. Okay. So yeah, make sure that you're not afraid of solving differential equation using the kinematics. And maybe one more comments here, right? So when you deal with the kinematics, you might deal with a lot of a chain rule. Okay, so check this out: dv over ds. We don't like it. I mean, we like it. That's what they asked me to do. But how can I describe it? Maybe I'm gonna do just arbitrarily just put t. Right? That's what we are more familiar with. But I didn't have t, so what do? I'm gonna cancel it out. dt over, so that cancels out. The initial denominator was ds. But as you know, dv over dt is simply acceleration, and dt over ds will be 1 over v. So you can use whatever the expression already there and then derive it, okay? Just one comment with that problem. So implicit, chain rule, differential equation, all together with the kinematics. Likewise, check this out. It's an acceleration. It's in terms of v. It is a differential equation. Just either do the separation of variable homogeneous equation is good to go. It's going to be typical. What is it? The separation of variable, isn't it? So, I'm going to match the. If I just quickly do that for you, where am I going to write? Okay, let me write here. So I'm going to pair the v's with dv, right? So it's going to be 1 over v, 1 plus v squared dv is equal to negative 1 over 50 dt, and then I integrate. And yeah, what do you have to remember? On the left hand side, you got to think about the partial fraction, right? So that's going to be, the linear, so constant over v, and it's a quadratic. It's not divisible further, so I'm going to do the at most degree linear 1, bv plus c over v squared plus 1. And obviously, you need to do the partial fraction to find the ABC and continue with the integration and whatnot, okay? Easy peasy, lemon squeezy. Boo, boo, boo. So make sure you try this, and I put in a PPT, so I would encourage you to work with it. But yeah, let's talk about the integration by substitution. I've categorized into many different parts, so let's talk about the fundamental first. In this syllabus book here in the guideline, only thing that you should really remember is this. Wow. Yeah, you're right. For the integration by substitution, it's really for the composite function, f composite g. But you need to make sure whether the g prime has been multiplied or not. Okay, this is our aim, whether that g prime has been multiplied or not. So that's where you choose your relevant substitution. So this is super important. Now who's going to be my u? So that the u prime is multiplied outside. So in this one, it's pretty easy to see. It's usually typically inside the function, right? So his derivative is a 2x plus 1, so it's multiplied there. So making this as a u is a good choice. But sometimes it's not that obvious. I've got a cotangent, I don't see outside where I can find the g prime, but no problem. I can actually convert that into who? Cosine x over who? Sine x. And not always, okay, not always. But it's often when you have a rational function that you have f prime over f. And then there you want to tack on the denominator. I want to make that as a substitution. What needs to be supported then? His derivative is multiplied outside. Then boom, his derivative is indeed multiplied outside. I'm very happy. So easy peasy, and squeezy. X cubic minus 2, voila. We have it. Jawohl. Dankeschön. So that's good. Oh, okay. Pause yourself, just pause the video for a second. Think about what substitution you want to make, okay? So let me put on your shoes, in your shoes. Denominator, maybe I want to try denominator. It's f prime over 2 to the f. I don't think it cancels out with the numerator, so I'm going to give up on that. Should I work with the 2x plus 1? It's 2, it doesn't cancel out anything. Yeah, you're right. You need to be exceptionally good with the derivative. I will substitute with the arc sign. What is it? 2x plus 1. Because, every time you have something fancy of 1 over square root of a constant square minus x squared, it's very much likely to work with the inverse trigonometry, especially the inverse sign. Remember, the derivative of who? Arc sine x is 1 over square root of 1 minus x squared. So from that reason, maybe substituting that is going to give us a good rule, and indeed it does. Okay, so I'm not going to do that. I'm not going to do that. Why? Because his derivative is not shown in the function, but it's good to go with him. Why? Because if you differentiate that, I probably typed it very good, and then you need to show that it looks like that. So I will leave that as an exercise. But I always try to practice, where I'm going to make my relevant substitution. Oh yes, and then the next slide is going to be the definite integral, is finding the area. Okay, let's have a look. Sure, the reason I came up with this is because I wanted to show you definite integration by substitution. So yeah, sure, you know what, you are able to work with the definite integral already, but I'm just only talking about examinable ones, right? The ones that you practice. So for this one, I'm going to talk about that later. But the good substitution, you could do the, I believe, 1 over root to 1 minus x squared as a substitution. But what I would like to do is every time I see a squared minus x squared, it's often, not all the time, but very often, x is going to be with the a sine theta. I talk about that later in the slide. But so for this one, I'm going to let x to be there for sine theta because a is given 1, isn't it? Then here, after having made the substitution, I want you to differentiate. So I get the cosine theta. So third one is going to be dx is a cosine theta d theta. That's great. Okay. Now I'm going to change everything in terms of theta. All right. But when you do so, you need to make sure everything is in terms of theta, including your bounds. This is for the x at the moment. For the definite integration by substitution, change your bounds, okay? I mean, of course, you can bring it back into x, but what's the whole point? Why do we substitute then? So now let's plug it in. It's going to be, I will think about the bounds later, but let's try to substitute right now. It's a 1 over 1 minus sine theta, right? That's great. If you put a sine theta, it's 1 minus cosine square, sine square, cosine square, square root, so it becomes cosine theta. And then, what do we have? dx was who? Cosine theta, d theta, do you see? Right, that's great. So what am I going to do? Cosine theta cancels out. And the bounds of integral must be who? For x to be half, theta needs to be, what is it? Pi over 6, okay? And then, what is it? 1 over 3, I don't have a special angle, no problem. I'm gonna just put arc sine 1/3. So your bounds must change. And it's a beautiful, beautiful integral. Oops. Oh, wow. I didn't know that. Okay. Yeah. So I will leave this. This is an exercise for you to work with. Okay. So how do I proceed? Maybe you want to multiply something like a conjugate. Whenever you see 1 minus some trig ratio, you want to multiply by maybe 1 plus, and see yourself what you get. Okay. And I think I've written down all the procedures here on the PPT, so you're more than welcome to read through. Blah, 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 blah. So please check it, okay? But I will skip. Sure. So we talked about the exam skills with the definite integral, especially by the substitution. Please change your bounds. And then the next thing is finding the area, right? We always, for the area, it's not only important to integrate, but also one before, you need to sketch. Please sketch. Even if it's a paper 1, you need to sketch because you need to check where it's going to be negative. So if I was given x cubic for x squared plus x plus 6, maybe it's important for you to factorize it first, isn't it? So if I have a x cubic minus 4x squared plus x plus 6, and imagine that this was a paper 1 problem. How would you approach it? I want to factorize it. I really hope that it has a rational root. So I'm going to do the rational root test, isn't it? So I'm going to go x equal to plus minus, factor of 6 is a 1, 2, 3, 6, and I have a leading coefficient 1. So very likely that the roots is going to be either plus minus 1, plus minus 2. So sure, if I plug in 1, doesn't work, right? If I plug in negative 1, oh, it works. So I'm going to do the synthetic division, right? 1, negative 4, 1, 6. And I'm going to put negative 1, 1. Multiply outside is a negative 1, negative 5, 5, 6, negative 6. Then voila, we have it. So, it's going to be x plus 1, x squared minus 5x plus 6. Well, of course, that can be, factorized. So what we're going to do is just put x minus 2, x minus 3. So it's a cubic polynomial, eventually going up with the positive leading coefficient. So boom. So we know which part is going to be positive and negative, just as you can see on the diagram. So how are we going to then separate the integral? I'm going to go from negative 1 to 1 being positive, so I don't need to do anything. However, for the second part, because it came off as a negative region, I would put negative, and then what is it? From 2 to 3, function x dx. Okay, that's how we're going to do. Sure, no problem. I put a work on it, so make sure. And also, please practice yourself with this nasty calculation. Sometimes it happens, all right? Sometimes it happens. So you need to be comfortable evaluating all this fraction and whatnot, and come up with a simple expression like this. Please practice. Working with fraction, you have to, especially for paper 1. And yes, for the area between, what I want you to do again, sketch. Okay, but in order to sketch, what you want to do is find the intersection first, right? You need to know when it's going to intersect, and then check who is above, right? Who is above? Easy peasy, lemon squeezy. So what I've done first is to find the intersection, and then sketch that. This was a relatively simple to sketch, is a cubic and quadratic. Then you'll be able to see which region is above and below, right? So do not be afraid of working with the definite integral. Do not just practice with the calculator, because some nasty calculation happens in paper 1. So please practice. I cannot emphasize further. Oh, wow. Let's talk about the applications of limit. Talking about continuity and differentiability. So I'm not going to talk about the definition, but I'm going to talk about how to prove things. For example, with the limit, you can prove the things are not differentiable if the left and right limit is not the same for the first principle. Remember? So in this time, I want to show the differentiability at x equal to 0. So x goes to 0 of, what is it? Absolute value of x minus absolute value of 0 over x minus 0. So you're looking at the limit of what? Absolute value of x over x. And obviously, with this absolute value, it's going to be interesting working with the left limit and right limit, right? So, boom, boom, boom. Sure, sure. Left limit of that first principle, I've got -1. Right limit, I've got +1. Ain't the same, not differentiable. Be able to prove it, right? Whether it's differentiable or not, using the first principle. Sure, also a very important simultaneous equations with the differentiable function for the piecewise. If this piecewise function is differentiable at 1, by the way, differentiable implies continuity. We should know that the converse is not true. The counterexample will be absolute value of x. Here, typically for this type of piecewise function, you have two parameters. Means that you need to find the two equations. And for that, I'm going to use both of them. What is continuity and differentiability? Left limit and right limit, as well as the left derivative and right derivative must be the same. So the very first thing is, I'm going to call this as a maybe f1x. Oops. Let me call this as a f1x. Let me call this as f2x. So how you're going to set up the equation is, f1 of 1 is the same as f2 of 1. And then what's the next one? F prime of 1 is f2 prime of 1 is how you work on it, okay? Then you can find who? A, B. So I've written down some work on it, so please go through, but please attend to yourself, okay? So that will be from the continuity, the left limit, right limit of the function. And then after having differentiated, then I put the using the differentiability, hence we can solve it simultaneously. All right, so piecewise function, continuous and differentiable, very much likely to work with the simultaneous equations. Oh wow, I have a dream. What is the first principle of sine is really going to come for the paper 3. One day, in that day, I'll be a happy man. I'm really hoping that it's going to come soon. There's some modification of that approach in the previous past exam papers, but not the full extensive work of proof on the derivative of sine has been given on either paper 1 or 2 yet, but now we have a paper 3. I really hope that they're going to one day give paper 3 questions on the derivative of sine. But anyways, yes, please be aware of working with the first principle. Do not just say, okay, derivative of a quadratic is a 2x. It is correct, sorry, but you should be able to prove it, right, using the first principle. But on the slide, I gave some work on the derivative of sine because I don't think it's gonna be, well, technically, it could be examinable on paper 1, section B, but maybe it's more like on paper 3. But yeah, I gave more information on the derivative of sine. This is, by the way, exam question diagram. I think, this is where you start with the derivative of sine. But I've written down some information. Please help yourself to read it, okay? So, no problem. And I also gave I thought I gave the derivative of an exponential function, but I think that's later on. We're going to see that, but try to read through of the derivative of sine and exponential function using the first principle. Why? Potential paper 3, I think. And also, it's a very good revision for you anyways, throughout the topics. Sure, let's talk about another application of a limit, which is called the L'Hopital's rule. I have a few more things to say. What I want you to do is to not use L'Hopital all the time. What do I mean? Please simplify. Oh my God, my cursive is on fire before using the L'Hopital. So what do I mean by is the following. So you know what? In order to have the L'Hopital, you need to have an indeterminate form. 0 over 0, 0 times infinite, infinite over infinite, whatnot, right? But not all the time. Sometimes you have that 0 over 0 form. It's still not indeterminate. We can discuss later. But for the exam questions, typical, right? Indeterminate form. So if I put pi over 2, 3 pi over 2, cosine 0, cosine pi over 2, 0. So I do have indeterminate form. So I want to use the L'Hopital. I've done it once. Okay, I've done it once for you. However, check this out. This is the form I've got. But here's the thing. If I put pi over 2, unfortunately, I have something of a cosine, makes both of them 0. So I have an indeterminate form, and you may do the L'Hopital here. However, for me, I don't like it. Why not? Because, check it out, man. I got to do the product rule here. On top of that, I got to do the chain rule on the numerator. So my point here is, if you can, please simplify. What I mean by that here is, every time you see the product of a sine and cosine, what should that remind you? You're absolutely right. The double angle of a sine. So I'm going to just multiply by 2 and 2 here and convert into the double angle of a sine, which is a lot easier for me to work with the derivative. You're sure, you know what? I am going to do the L'Hopital. But at least I'm dealing with just a single term rather than the product of the two functions. I don't like it. Okay? So please simplify. So for that one, I multiplied the extra 2 there, right, and then came up with the double angle of sine. So let me quickly show you. And it's all, well, you know what? You're right. You don't even need the L'Hopital here because you know that the, sine theta over theta, limit theta going to 0 is, oh, sorry, my bad. I'm not sending to 0, my bad. So I will do the L'Hopital here. Let's do it. Then, yeah, it's a lot easier to differentiate, you know what I mean? Right? So, and now I'm happy because even though I've got the cosine, if you put the pi over 2, this becomes pi, becomes a negative 1, isn't it? Same thing for the cosine 3 pi here. Then we can simplify the limit. Okay? Please simplify before doing the L'Hopital. Before I move on to the next example, typical exam question was let me think. It would look like tangent beta x minus secant beta x, something like that, over tangent x. It came like 2 times throughout the exam. It gets really nasty if you don't simplify. If you do the L'Hopital mechanically, I think you need to do like 4 times. I don't want you to. After having done once, try to do the algebra. And you realize things are very cancelable. So that purpose of that question is not, I think the limit comes like -2, doesn't it? But the purpose of that problem is not to differentiate, is to check on your differentiation skills of doing this 4 times, but seeing whether you can simplify before continuing, okay? Sure, and why I came up with this example, for the L'Hopital, if you notice that this is infinite times 0, indeterminate, I could use it. I could use the indeterminate form, but I would try my best to put it into the fraction form, right? Because then it's easier to differentiate top and bottom, right? So make sure I would be more willing to put it into the fraction form and continue, okay? Then you can do the L'Hopital here, no problem. I've done some work on it, but make sure I prefer fraction moreover. So you know what? Sure, sometimes you have a 0 to the power of infinite, something like that, or 0 to the power of 0, or infinite to the power of 0. Do you remember how we can put into the fraction form of such? Very good. When I have a y is equal to x to the power of x, if I want to see the behavior x going to 0, what we do is put a ln on it, right? For the exponent form, if you want to get into the fraction form, what I would do is to compose it with the logarithms. I have a x ln x, and this will be ln x over 1 of x, and you can talk about what happens with the limit, all right? Easy peasy, lemon squeezy. Okay, another application with the differentiation, related rates. It's very similar to the optimization. I think the essence is on modeling. right? Who do we need to differentiate? What am I differentiating with is the first question you should ask yourself. And then, after that, differentiating is pretty simple. I think this example really covers pretty much everything I want to talk about the related rates. So, for the related rates, what I want you to do is always indicate known, unknown rates. Okay? Because it gives you that, okay, so from that derivative, I need to come up with certain equations, is what it tells you. So what I mean by that is the following. So check this out. In this question, what I'm given here is that water is poured into, that's also very important, is it? The sign. Now, if it's leaking out, I'll put a negative sign on it for my derivative. But if it's pouring into it, when it increases the velocity, it needs to be positive. So what I'm going to put here is the volume expression with respect to time t is positive 2.4 meter cubic per minute is what I have. It's a known rate, isn't it? So from here, I'm already aware that I must somehow need to work with the expression of a volume, okay? This implies, okay, please come up with who? Volume expression is what I'm saying, okay? That's great. So that's number one. Number two, indicate the unknown rates as well. So, oops. If you read the question carefully, find the rate. Water level is rising. Okay. So for that one, I'm realizing, okay, so unknown rate here is going to be, what is it? You're absolutely right. dH over dt is unknown. I don't know it, man. So what you need is somehow I need to involve with the equation of what? H. Okay, so it gives you a clue what modeling we need to do, right? So I think the problem that the people have with the related rates is what expression do I need to find? Well, the question is telling you, you got the dv over dt, and you're finding the dh over dt. Somehow you need to work them together. Maybe some questions have a separate equations. Maybe some questions can combine it, okay? So you really, really want to try this problem. It's super nice, Let me quickly move around so that you can see the full questions. Pause the video and try yourself. But I've already solved it for you. So yeah, the visual looks like that. Please be able to sketch. I'm sorry, it's given as a diagram, no problem. So I want to find the volume expression there, right? Oh sure, so here's the thing. I've got an expression. I need to find the expression of the volume as a 3D. And for that, maybe I will get the base area, right? And then multiply by the length to talk about the volume of the 3D, isn't it? But for that one, I have an unfortunate case. What is? Sure, I was dealing with the height, but I don't know the length here as well. So maybe I will deal with the volume in terms of x and h. But here's the thing, you know what? It is okay to have more than one variable for the related rates because I can just do the implicit differentiation. As long as you have some information of the dx over dt and dh over dt, it's okay to have two variables, unlike the optimization. But if you look at remember the previous question, I don't have anything with the rate of change of the length. So I wouldn't have it. I don't want to have it. It's a situational. You could have it sometimes if the information is given accordingly, but in this time I'm not given, so I will do my best to describe only in terms of h, okay? So for that, what I want you to use is, yes, very good, I want to use the fixed constraint. So for that one, what am I going to do? Voila, 3D shape. If you want to do the fixed constraint, make a cross section. So here I have a trapezoid, isn't it? Then, here again I will use maybe the similarity, right? What I mean by that is that was the altitude is 2 meters, but I've got the height of h, and if I call this x, and then the length on the base was 2 meters, then this is going to be, what is it? X minus 2 over 2, and that rise over run must be the same throughout the triangle, isn't it? So if I use the big triangle, 2 over x minus 2 over 2 must be the same as Looks wrong, doesn't it? It's all right. What about the wrong? Oh, my bad. This is the x minus 2 over 2, right? Oh, yes, this is the x. Oh, my God, my bad. Yeah, better. But yeah, on the top, it's 3 meters, my bad. Okay, so this is going to be 1 over 2. So the rise of a run on there is 2 over half. That should be same as h over x minus 2 over 2. Then you can find some substitution to find the x in terms of h. So then you can use for the volume formula, because now this is some sort of h. Then you can do the base times, so a plus b times height divided by 2 will be the area of a trapezoid, multiplied by 4 is going to give you the volume expression, which I've done already here. So I've got the h expression here, right? That's great. So boom, boom, boom. So it was in terms of xh, no problem. I can actually convert just in terms of h for my volume formula. It's what I've got. And what do? We're looking for what? The aim was to find the unknown rate of dh over dt. So I'm going to perform the implicit differentiation here. Let's do that. So there you go. Implicit differentiation here. And please highlight the unknown rate. So I got to find him. So what implies is that you need to have the dv over dt, which we had. And then you need to find the h, which we were given. So you can just plug it in, and you can find the desired rate of the height with respect to time t. Easy peasy, lemon squeezy. I like that expression. And another question was this. Okay, I think another question was super important too. Let me quickly show you what I mean by that. The reason I like the problem is not because of a modeling, but also about the third one. Wow. Why? Why? Because check this out. If you read the question carefully on the third one, yes, you're absolutely right. Why is it special? Because I'm given a time. It says 1 minute. We got 1 minute. How can I use it? Right? How can I use it? So it says find the rate, so unknown rate at which the exposed surface area. So from that sentence, you know that, okay, I got to find somehow the area expression. Probably just in terms of h, because we weren't given any information about the x. And then let's say I've got it, okay? So then I'm going to do the implicit differentiation. But here's the thing. This is probably in terms of h, and I've got the derivative of h, but I don't have any information other than the time. Where can I use the time? Think about it. Pause the video for a second. Think about it. Yeah, you're right. I can use it on the constant rate, right? Because I'm given 2.4 cubic meters per minute. After 1 minute, I got the volume of 2.4. Okay, so sometimes you're given the time, and you should consider with the given rate and with their time unit. Think about it. If it was 1 hour, I would probably let the 2.4 times 60. Okay, that's great. So the last question is beautiful too. So please have a look. Please have a look. I've written down very well with the fact that the time matters for the constant rate. So after 1 minute, I've got that. And you know what? We already had the volume expression in terms of h. And then we can let that to be equal to the 2.4. I can find the h. And with that, I can find the dh over dt like the previous question. We're good to go. Okay, we're good to go. So blah, blah, blah. I've written it down. Please have a look. Okay, it's a very, very good question. Essence of this video is not to talk about the details of the problems, but of the skills. Right? For the related rates, what do you need? Modeling. Where do I find the modeling? From the known rates and unknown rates. Using the extensive implicit differentiation, always highlight which rate I'm looking for. And be careful with the time. Easy peasy, lemon squeezy. Let's talk about the advanced derivative. I said I've added some of the slide for you to remind you. Sure, please remember if I differentiate all this, right? So cosecant, what is it? Negative cosecant x, cotangent x, secant is a secant x, tangent x. The cotangent was a negative cosecant squared x. A to the power of x is, what is it? A to the power of x ln a. Make sure you know how to prove it. I will use the chain rule with what e to the power of ln a times x. And you can do the chain rule. Same thing for the change of base. You realize this is going to be 1 over ln a times 1 over x. And why knowing this is important? Because it is going to be used for what? Integration. Okay, it's going to be used for the integration. Okay, so it's important that you know them well. Sure. Derivative of arc sine, arc cosine, arc tangent. I've written down the proof of it. Please read, because sometimes question can ask you, I think one exam asks you to prove the derivative of arc secant x. Okay, that was actually the question. Well, not with the first principle, but using algebra. Well, we can talk about it actually. You know what? Let's talk about it. Have I written here? Oh, I did. Sorry. So yeah, if I want to prove the derivative of arc sine x, I'm not so familiar with it. Maybe I will work with his inverse function, which is a sine. I just composite by the sine and I work on the derivative with respect to y. But I use the Pythagorean theorem and I realized the y was arc sine x. If you composite, this just becomes what? X squared. Right? Very happy. By the chain rule, I can just do the reciprocal here. Therefore, you're going to have 1 over square root of 1 minus x squared. Okay? Easy peasy, lemon squeezy. Well, here I want to talk about some advanced integral from what, especially with the inverse trick. So whenever you see this dodgy constant over some sort of a difference of a square, it should really remind you about what? The arc sine x, okay? So remember, integral 1 over square root of a squared minus x squared. What was it? Arc sine x over a plus c. Remember, the 1 over a does not pop out for the arc sine. So I've done the, what I would do is the completing the square, blah, blah, blah. So I've got that. So this is a 3 square, isn't it? So it's going to be, something like arc sine 2x plus 1 over 3. However, one more thing that I also want to remind you is that if you're integrating the f of ax plus b, right, what's going to pop out? In this case, 1 over a pops out, right, for the antiderivative. So in this case, 3 would not pop out for the arc sine, but the substitution with the 2 is going to pop out. So the half is going to be the coefficient there, isn't it? Yeah, there you go. 1 over 2. Here comes from who? 2x plus 1. So make sure that you're able to, integrate this actually quickly. You don't even need the substitution. Just say, oh, okay, this is just the antiderivative of arc sine x, and good to go. Right? If you have a constant over quadratic term, very likely with the arctangent. Right? Remember, integral of 1 over x squared plus a squared, it's going to be who? 1 over a arctangent x over a plus c is what I have, okay? So then I will use it. Easy peasy, lemon squeezy. So I've done the completing the square for you. So in this time, you got to be very careful. You got to be very careful because that 1 over 8 came out. This substitution with the 2 also needs to come out reciprocal, isn't it? So actually the coefficient is going to be 1 over 10. Okay, that is very, very important details. I want you to practice it. Arc sine and arctangent, it ain't the same. So please practice, and boom, you get the part before. I want you to actually try that. Whole point of me coming up with these two examples is to remind you to use the antiderivative of the derivative of arc sine and arctangent well. Okay. Sure, and another advanced integral is going to be in a format like that. you need to use substitution very, very well. Okay, you need to use a substitution like this very, very well. It is very likely that you are given those substitutions. They always say, oh, okay, substitute x equal to 4 sine or 2 tangent, etc. Even if you don't have it, you should be able to see that, okay? So let's have a look at this problem together. What I'm going to do is to cut that, okay? So let's try to integrate this. I mean, in the exam, they will probably give you, okay, let x to be 2 tangent theta. Even if you don't have it, you should be able to see that. And then, after I have a substitution, I'm going to differentiate this. And then dx is equal to 2 secant squared theta. D theta is what I've got, right? That's great. Then I'm going to start plugging in. It's going to be integral. The dx will be replaced by, what is it? 2 secant squared theta d theta. On the denominator, x was 2 tangent theta, so it's going to be 4 tangent squared theta. And if I substitute with the 2 tangent theta, 4 is going to be factorized. So 2 is going to come out of a square root. And I've got the tangent square plus 1, which is a secant square. Put a root on it. I've got a secant theta. So it should be a very easy trigonometric identity practice for you. Then what I can do is I can get rid of a secant theta. 2, voila, I have 1 over 4 integral secant theta over tangent square theta d theta. That's great. But I agree with you. It looks nasty. I'm not familiar with the secant and tangent. So maybe what I would do is to convert into the forms that I'm more familiar with, such as a sine and cosine. Why not? So, if I try to convert this in terms of a sine and cosine because it's more familiar to me, I have a, 1 over cosine theta times cosine squared theta over sine squared theta. Okay, so cosine cancels out. I've got quarter. Integral cosine theta sine squared theta d theta. Okay, I've got that. Very good. And then what are you going to do with this? Well, still confusing, isn't it? Well, it's not that bad. It's not that bad. Why? Because there's a room for me to use the antiderivative with the fundamental theorem of calculus. What do I mean by that? If I just separate by the cosine over sine, that is cotangent theta. And then I've got the remaining 1 over sine, which is a cosecant theta. Does that remind you anything? Very good. It is the derivative of negative cosecant theta. It is great. So I can just use the fundamental theorem of calculus right away. That is going to actually come out as what? Negative quarter cosecant theta plus c is what I've got. Okay, that's great. But I'm not done. Every time you make a relevant substitution like that, you gotta bring it back in terms of x. Unless it's a definite integral, then you can keep it. But this is not. This is an indefinite integral. So I gotta bring it back in terms of x, which is gonna require to use the the inverse trick. So now I have a think about it. I have a tangent theta is equal to x over 2. And now I want to derive something of a cosecant theta, and then we mentioned in the topic 3 that we're gonna do what? Use the right angle triangle. So I can just use the fancy right angle triangle diagram on this technology. It's great, and the rise over run. So I got the x, I got the 2. Hypotenuse is going to be x squared plus 4. That's brilliant. I've got the theta. Wow. And I wanted to get the cosecant theta, which is a reciprocal of a sine. So 1 over sine theta is going to be square root of x squared plus 4 over x. Voila. So that is going to be same as negative square root of x squared plus 4 over 4x, which is exactly what the question was asking. But plus c, of course, for the indefinite integral. So very nice example why. Using some substitution, we're working with the fundamental theorem of calculus, and then we're using the trig identity. Okay? Make sure, this is a way more popular form, substituting with the sine, secant, and tangent. So please help yourself to practice more questions like that. Okay, many questions in the book. Any books, Heath, Holder, Oxford, Pearson, IBID, so many books talk about it. So please practice. Now we're gonna talk about the partial fraction. Superstar is a newly added chapter, so obviously it's gonna come up. So things that I want you to be careful here is, if I've got that, what would you do? Same degree, please do the long division. If I have a same degree like linear over linear, quadratic over quadratic, or even bigger like cubic over quadratic, I would just do the long division. So I've got that, right? And then if you ask me how do I integrate this, well, this is the quotient and this is a remainder, so this is pretty easy to integrate. But what about the here, right? Because, okay, I've got a quadratic, and I really wish his derivative is on the numerator. Where some parts, right, because the derivative of the bottom is 2x, but I've got 5x minus 2. So this needs to be separated as well. Some part with the f prime over f, and some part with the constant over the quadratic, which is going to involve with the arctangent. Let's see what I mean by that. Okay, so blah, blah, blah. So for that one, we need to work with that. So what I've done was I've separated this part because that's going to give me the logarithms, right? And this is going to give me what? The arctangent, right? So if you remember this, it's going to be just 5 over 2 ln absolute value of x squared plus 3 minus 2 times, what does it give you? You're absolutely right, it gives me the arctangent. So I'm going to go 1 over root 3 arctangent x over root 3 plus c, right? So that's that. Make sure you're able to work with the fraction form, doing the partial fractioning and whatnot. And even if you have done the partial fraction, some integrals might be tricky because this I cannot divide any longer, but I can separate so that I can apply the f prime over f is going to come out as ln f, and then 1 over x squared plus a squared is going to come out as 1 over a arctangent x over a. Okay, that's correct. So altogether, it's going to be put it like that. Please help yourself to practice. Okay. Sure. So now this is going to be another partial fraction. It's not divisible because I got a constant over cubic. It's way below the degree of the bottom. But if I have things like that, you need to be able to separate, right? So if I got a linear form, it's going to be constant. It's the most degree that I can have for my remainder. But what about the quadratic? I cannot factorize this any longer. It is as it is. And what was the utmost degree for the quadratic? You're absolutely right, the linear. So our job is to find the ABC first and then integrate accordingly, right? And remember, when I'm integrating like that, you also have to separate, right, for the f prime over f and then the constant over the quadratic, which we have seen in the previous slide. So please help yourself to practice that you're able to find the ABC using the partial fraction and then be able to come up with an integral like this. I will leave it as an exercise. Okay, please practice. All right, let's have a look at the next question. Parts, integration by parts, another technique that we must be impeccable, right? So let's get to it. So, oh yes, for the form, for the parts, what I want you to remember is that there are 3 kinds of the parts that you will see in the exam. Polynomial times, trig, or exponential, what else? Trig, and exponential, and polynomial with who? Logarithms, inverse, trig, exactly. There are 3 kinds. And for that one, you see the typical form is u times b prime, right? So I think the practice should be put what I'm going to put my u, right? So the one that I'm going to differentiate with. So for the polynomial and trig, polynomial is the one that I'm going to differentiate. For the trig and exponential, doesn't matter. But you just have to do it twice, remember? So this must be always twice. For the product of polynomial and logarithms inverse, I will always choose either the logarithms and inverse trig to differentiate with. Okay. Without further ado, let's get started. So yeah, I'm not gonna talk about all the basic examples. I'm talking about only the exam skills, right? So when I have I don't know why. If I have a polynomial and an exponential, I know that I'm gonna work with what? This as my u, so that I can differentiate this. But then, I got a cubic, so I actually have to differentiate 3 times to make it constant. So this is going to be typical repeated integral. Right? This is going to be typical repeated integral. For that, I want you to think of it as a following example. So for whatever that you chose as your u and then v prime, I want you to keep differentiating this and keep integrating the one that I'm going to put as a v prime. And then I'm going to add them, but then you're going to add the terms by making their product and then alternating. So I need to do plus, minus, plus, minus. Okay, so that will be a easier form to work with the integration by parts. Okay, you just keep differentiating until you get the constant, and then you match that v prime with the integral, and then multiply them. You're going to add them. However, you're going to add them alternatively, right? Plus, minus, plus, minus. So if I give you the form for that one, it looks like that, right? So I use the table, put it into the product, and then put it into the alternating form. Okay. So it's an easier one with the repeated integral. And yes, do not be afraid of working with who? Definite integration by parts. You need to evaluate each term, right? So, if I was given a term like that, you got to evaluate each term with the bounds for the definite integration by parts. So make sure you practice with a question like that. What I've done here for you is I put it into the integration by parts. And so this was a repeated, right? Because it was x squared. And then you need to work with the also evaluations. You're gonna put the first, second, and third term with each bounds from 0 to ln 2, and then make sure that you're able to get to there. Okay, so please practice with the definite integration by parts as well. And yes, for the product of a cosine or trig, such as a sine and cosine with the exponential, I know it doesn't matter which one you choose as your u, but I know that we must do this twice. Okay, why? Because I'm gonna get into the same kind after having done the integration by parts twice, but it's going to be negative term of a sort. Then I'm going to rearrange. It doesn't cancel out, but it has some of the same different coefficient. You combine them and divide them through. So what I mean by that is, you can see from this work, I'm going to do how many times? Twice. As you can see, then I've realized that the same integral appears here, but with a negative sign on it. So if you rearrange, then it gets double, then I can divide by 2. Okay, so voila. But here's the thing, sometimes you have a like different coefficient here. Doesn't matter, the same principle. Maybe it's not doubled, but it's got some sort of a coefficient. Nevertheless, you need to do integration by parts twice. Okay. Also, the third kind is the polynomial times logarithms or the inverse trig. In that case, who am I going to choose my u? When I have a u and v prime, who is my u? My u is going to be the logarithmic function. That's the one that I'm going to keep differentiating with. Unlike the other examples where they use the polynomials to differentiate for integration by parts like this example, I'm going to attack on the logarithms. So I came up with some examples for you. So I want you to take a look at the integration by parts, practice with them. So make sure who am I going to choose my u is the key of doing integration by parts well. Okay. Oh yes, inverse trig as well. I'm going to choose him as a u. Then what's going to be my v prime is the polynomial term. In this time, the constant one is going to be my v prime. Easy peasy, lemon squeezy. And I just did the integration by parts, so that would have been a u prime v, u v, thank you, because we are doing the u v prime. So that's my u, this is my v prime. Oops, looks strange, doesn't it? Oh, my bad, it's supposed to be x, right? Yeah, there you go. So that's my v. This is my u. and this is my v, and this is my u prime. Forget about that, this is x. And then for that one, how would you integrate? Just talk to yourself. You're right, you're going to use a substitution with what? You don't necessarily have to make the substitution with sign. Why? Because it would be a lot easier if you just go with the 1 minus x squared as u. Why? Because his derivative is multiplied outside. So now I know this is going to be a good substitution. You could work with the x equal to sine theta, but why bother, right? Because it gets nastier than just simple substitution like this, okay? And then another example that I want you to try is working with who? So, things like that. But try yourself, if you can actually also work with the x times, maybe arc sine x would be another exercise that I would encourage you to do. Okay, integration geometry. So, we talked about the area already. So, only thing that I'm going to talk about is along the y-axis and then the volume, okay? Sure, for the y-axis, make sure, for this one, if I'm doing along the x-axis, it's nastier, isn't it? Because I got to think about many different regions. I got to talk about this region, that region, what else? This region minus this region. So, maybe it's nastier than just working with the y-axis. So for this one, definitely I'm going to use the y-axis. For that one, what is the most important part here is to work well with the inverse function, right? So, what we have here is the expression of y in terms of x. If you want to work with the y-axis, you got to find the expression of x in terms of y. For this one, it's going to be x is equal to y squared minus 1. And now you need to see who's to the right rather than up, above and below, to the right and left. So here, from here to here, linear function is to the right. So I'm going to use the 1 minus y first. We subtract it by who? Quadratic, so y squared. And then we need to integrate from where to where? From the intersection of a -2 to 1 is going to get you the area along the y-axis. Okay, so also make sure that you are able to find the area along the y-axis, of course, volume as well. Okay, so it's just a matter of whether you can see the inverse function and then using the different bounds, such as the y values of intersection. Sure, and it's going to look like that. So please help yourself to see that you get the same value. It's good to go. So this explains why I would not go along with the x-axis. You get the same value, but it just gets nastier. Okay. Sure, another volume of revolution. You already know the expression. Pi from x1 to x2, y squared dx. I got it. But then the example I want to give you is that we got to be careful with the rotation, right? We got to be careful with the rotation. What I mean by that is the following. Let's say I want to find the volume of revolution between these two functions. And let me quickly show you the graph. Do you see the graph? Well, yes, you do. So this is the graph that I wanted to work with the x squared minus 1 and x plus 1. Let me quickly write. So x squared minus 1, x plus 1. So I want to rotate around along the x-axis. Okay. But if you actually see, some parts you don't have to rotate because the other parts has already rotated the parts. What does that mean? Well, if you rotate around the quadratic function, it's gonna go above like this, you know what I mean? Well, it's not on scale, sorry about that. Maybe I'll write in red. Sure, look, so that quadratic part goes above like this, okay? What I'm saying here is on the left, the rotation already has covered most of parts by the quadratic function. So I don't have to rotate the linear function, you know what I mean? So from -1 to 0, I'm going to just rotate by what? The quadratic function, the x squared minus 1 squared dx. Okay, that's great. But if you look at to the right, it gets more interesting. Why? Because from 0 to 2, linear is bigger, right? So he covers pretty much everything. So I'm going to rotate from what? 0 to 2 with the linear function only. However, you got to be worried about from what? 1 to 2, there's empty parts, right? That part is not covered, so we got to subtract it. We have a whisker, right? So we have a washer. So here you want to get rid of it. How do I get rid of it? By subtracting the volume rotated by the quadratic. So what I'm going to go is a pi from, what is it? 1 to 2 of the quadratic function is what we're going to do. So if the functions are along the x-axis, you want to be extra careful because some parts are covered by one only, and some parts you need to also subtract by the other empty parts. So this is going to be the expression for the integral. Maybe it's a good exam question for paper 1 that because you got to go through the extensive algebra, which you should not be afraid of. Okay, that's great. Oh wow, differential equation. Right, there are 6 things that I want to talk about. What are the 6 things that I want to talk about is on the next slide. So analytic separation of variable, a homogeneous equation, integrating factor approximation, slope field, Euler's method, and Taylor series. And so slope field is an isocline. It's not in the syllabus. However, why have I put it there? Because of the potential example with who? Paper 3. So you should be aware of the method, okay? But of course, these are in the syllabus, so you should know. Sorry, Maclaurin series here. But let's talk about the analytic method first. You know, we already mentioned about the homogeneous equation, isn't it? So you wanna, if it's a separable, might be separable. We already talked about that example in the kinematics, right? With the velocity and dv over dt, things like that, right? So if you compare the variables with the dy and dx, that's a separable case. So, you know, if I look at that, so who are we going to match? dy with 1 over square root of 1 minus y squared, dx moving to the other side, 1 over square root of 1 minus x squared. Voila. Oops. No, right? Okay, I typed it wrong. Oops. So it's supposed to be 1 over, my bad, right? Thank you. The dy is here, right? And yeah, sure, that it reminds me of the derivative of arcsine. So, you know, by the FTC, I've got that, right? And if you want to simplify, you can, you can find the constant c using the initial conditions. So I've got the pi over 6. So then, you know, if you want to find the expression of y, I'm going to composite with the sign. So I've got that, but you can simplify further using the compound angle, right? Sakokosa. So make sure you're able to come up with an expression like that. But the point of this example is to show you we're going to match all the variables. Now the second one is a homogeneous equation. What was a homogeneous equation? If I can describe the dy over dx as a function of a y over x will be the homogeneous equation form. So for that one, we make the relevant substitution with who? Y is equal to vx, right? So that would be the homogeneous equation. And so yeah, you know, after having made the substitution, what we do is to differentiate with respect to x. Then you're gonna get, what is it? A product rule, so dv over dx times x plus v is what I've got. Okay, that is great. And here I want to describe that in terms of v, how I'm going to divide this by x on each side. So I'm going to get 4 plus y over x, 1 minus y over x. That's great. So y over x is going to be who? Simply v. Okay, so I have that, right? Now it became, so the whole point of homogeneous equation is really to try to convert into separable case. Right, so then, you know, I'm going to rearrange the v to the other side. Have I done that? Sure. Now I rearrange the v and then put it into the common denominator. I've got that. And here's a bit of a problem. So on the right-hand side, it's a ln x. How would you integrate this? You know, think about it. I got a linear over quadratic. I cannot do the long division anymore. But absolutely right. I'm going to separate it. Okay. So how I'm going to separate this as a 1 over 2 squared plus v squared dv minus v over 4 plus v squared dv. And imagine that this is going to be coming out as arctangent, and this is going to come out as a half ln 4 plus v squared, right? So please make sure you're comfortable with an integrator, with integrals like that, okay? Blah, 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 blah. So it comes like that. So please make yourself comfortable with an integral like that. And what we have done after that is try to substitute back, right? I'm substituting the v with y over x, and you should expect to have forms like that. We'll leave it as an exercise. That was the example with who? Homogeneous equations. So the next thing is the integrating factor. We want to have a linear combination of inhomogeneous equation. Okay, what is it? So dy over dx plus px y is equal to qx. So if you have that, what was it? Integrating factor was e to the power of integral px, isn't it? Okay. So for that one, you need to choose your px well. For that, you want to make sure the coefficient of dy over dx is 1. I don't have that. So what are you going to do? I'm going to just divide everything by cosine x. Let's do that. So I've got that. So who's going to be your px? You're absolutely right. I'm going to have a negative 2 tangent x. Okay, that's great. So blah, 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 blah. This integral, I will leave it as an exercise for you. By the way, you don't have to worry about the constancy for the indefinite integral, and you should know how to prove why adding the indefinite constant doesn't matter for the integrating factor. But anyways, I want you to memorize integral of a tangent x is who? Negative the absolute value of cosine x plus c. There are a few more things to ask you to memorize. Secant x. I want you to memorize, please. Secant x plus tangent x plus c. And please check yourself with the cotangent x and the cosecant x, okay? I want you to Google it. And then memorize them, please, okay? But anyways, if I do the algebra, the integrating factor comes out as a cosine x squared. And then what do? We multiply the integrating factor on both sides. You don't have to distribute this. Whole point of multiplying the integrating factor there is to put it back into the product root form, isn't it? It's going to be y times the integrating factor. Right, that was the whole point. Okay, that was the whole point. So it looks like that. Sorry, it looks like that. So what do? We integrate on both sides. That only that one is going to pop up by the FTC, and for that one it's pretty trivial because it's the integral of a cosine x. Then voila, we have that. Okay, and of course you can find the c using the initial condition. I think it was given, so you should expect to have a solution like this. Okay, I will leave it as an exercise. For me, it's really just about the exam skills check. I am not going to talk about how to solve it extensively. Okay. Sure, things like that is a bit tricky, right? Because it is not linear. This is not linear solution. This is a y squared. So far we had a plus px times y was linear, but it's not linear. But sometimes I can solve it if I'm given with the dy over dx multiplied by the 2y, which is in fact the derivative of that nonlinear form. It's called a Bernoulli differential equation. And for that, what I would strongly suggest is that you make the substitution z is equal to y squared. Okay, then problem solves it. So this is typically Bernoulli differential equation. So yes, I got the z as a y squared. If I do the differentiation, I've got that. In fact, that was the first term of the differential equation, wasn't it? So every time you have a form like that, and this comes as nonlinear, no problem. If the dy over dx is multiplied by the g prime of y, then you can make the relevant substitution and solve it accordingly. Okay, make sure this could be advanced differential equation questions that could appear on paper 1, possibly section B, or at the last question of a section A. So I convert the previous equation into all in terms of that, then it's beautiful, isn't it? It's a linear now. So what's going to be your integrating factor? It's going to be e to the power of integral of 1 over x. That's going to be my px. So it's e to the power of ln x, simply just x. Okay, it's going to be my integrating factor. And I can use it blah, 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 blah to find the general solution for the z. But of course, you got to bring it back, right? You got to bring it back in terms of y. Then you're expecting to have a solution like this. I want you to check it out. Okay, I want you to try yourself. Both of calculus, okay? Without hesitation, let's get to it. So one of the skills that I want you to do well is to use a composition, okay? I will show you the skills that I don't want you to do. Check this out. Does it look like a very happy method? man, I don't want to. It's a very inefficient. It's a drudgery. I got to look at that. I got no time for that during the exam. But I want you to be comfortable with the Maclaurin series using the composition. That's the whole point of learning the Maclaurin series. So let me quickly show you that. So if I have a Maclaurin series like this, what I want you to do is to write down the two formula. What is it? So I'm gonna write the ln 1 plus x. What would that be? That's gonna be alternating term, right? So very similar to the exponential. It's gonna be x squared, x minus x squared over 2, x cubic over 3, x4 over 4. Okay. Not only that, I'm going to work with the sign as well. So sign Maclaurin, it's an odd function. Remember, if it's odd function, only the odd degree survives, okay? So it's going to be x minus x cubic over 3 factorial. And I'm not going to bother expanding more because I'm only interested in about the x to the power 4. So what I'm going to do is I'm going to plug that into the logarithmic function. Therefore, it's going to be ln 1 plus all the substitution by the sign, which I'm going to copy that. Can I do this? Oh, very good. That's cool. Okay, so I substitute it there. So then this is a term that I'm going to replace the x of the Maclaurin series of a logarithmic function, right? So this is going to take over x, x squared, x cubic, etc. You might think, okay, isn't it nasty? Well, it's not that bad because you can actually throw out many terms because I'm only interested in x to the power 4. It's a lot better than doing the extensive differentiation to find the nth degree coefficient. I'm not going to differentiate this 4 many times. I got no time for that. Okay, so if we try, the first term is going to be simply x minus x cubic over 6, okay, minus 1 over 2. And hear me out, I'm doing the perfect square, but I'm only interested in the first term, minus 2ab. So minus 1 over 3, x to the power 4. And that's where I'm going to stop. I'm not going to square that because I'm only interested up to degree 4. That is great. And then the third one is 1 over 3 cubic. So here I'm going to do only the x cubic. The rest of the expansion has a bigger than degree 4, so I don't bother. Okay. Lastly, minus 1 over 4 x power 4. So if you simplify that, you're gonna get that. Okay, that's great. Well, you're right. You should try to ask yourself, okay, so that's what I've got for the ln 1 plus sine x, right? But what if, my friend, it was a sine x? Well, for that, let me quickly add one more page. Sure, so what I want to show you is what if it was a ln of a 1 plus cosine x? Unlike the sine x, there are several things that you need to consider. What if it was a cosine x? So the principle remains the same. You got to put a Maclaurin series of log and cosine x, but for the cosine x, remember, is even function, so only the even degree survives. So 1 minus x squared over 2 factorial, x power 4 over 4 factorial. And imagine that I wanted to describe just in terms of x. But here is a bit of a problem. What is the problem here is that if I try to substitute that onto log, right, which seems like a good substitution. However, you notice that 1 and 1 is put together. Okay, so this is going to be ln 2 minus blah, blah, blah. You know what I mean? All right. And I don't like it because for the Maclaurin series of log, I only know with what? The 1. You know what I mean? So I don't like having 2. What would you do? How do I get rid of it? We use the property of log. What we're going to do is to factorize inside by 2. Then I have who? This is going to be, well, let me put it in 2 and 4 factorial, what is it? It's 24. Then if I factorize by 2, it's going to be minus x squared over 4, isn't it? Yes. x4 over 48 is what I have. So that is, oops, my bad, 1 here, right? That's the one I'm going to use. Now, I'm going to use the property of a multiplication inside of log. So it's going to be ln 2 plus ln bracket, and I'm going to, what is it? Copy that. It is great. So that, my friend, is what I have, okay? Sure, here, so what are you going to substitute? I'm going to substitute with the negative x squared over 4, x plus 4 over 48. That's the one that I'm going to now replace with the x. Why? Because I don't have 2 anymore. I only have 1. Then you can start substituting. So make sure when you have inside of a log that is 2, you got to factorize. And I think in the exam, they often also ask you to find the Maclaurin series of this, and you notice that this is going to have a constant 1 as well when you expand using the Maclaurin series, and you got to do the similar step, okay? This is what I wanted to show you. But anyway, so, you can then derive it. I don't want to what? Use the derivative. It's very, very lengthy, and I don't like it. Okay, and then you know what? The question then extends, okay, how would you find the 1 minus sine x and cosine x and tangent x, right? It's actually a very, very nice problem. It's a mix of question. So if you had done the, what is it? We already have ln 1 plus sine x already, right? We found it. And then notice that the sine is a what function? It's an odd function. So you know what? I'm going to just compose it with who? Negative x. And because it was an odd function, I'm going to have ln 1 minus sine x. So you can easily find it. So, from the found form, I'm going to use what? Just compose it with the negative x. And then the next question was to work with the ln cosine x. Would you know how to derive the ln cosine x? Sure. Why? What would you do? Because I have the ln 1 plus sine x. I have also ln 1 minus sine x, and you really, really want to use these two information to derive something of a cosine. Can you think of any? You're absolutely right. Maybe I'm going to add them because it's going to give you what? Multiplication, which becomes cosine square. Hence, you can derive, what is it? Using the property of log, that 2 can go in front, so it's going to be 2 ln cosine x, and it's a lot easier to work with because you just have to add them through, and then divide it by 2. It's going to give you the Maclaurin series of just ln cosine x. And then the next question is, okay, I found the Maclaurin series of that, and then they're asking you to work with who? Tangent x. Can you think of any relation between the ln cosine x and the tangent x? This is why knowing all the derivative is important. You're right. If you integrate tangent x, what do you get? I get negative ln absolute value of cosine x. Okay, so if you just want to get tangent x, what should we do using the fundamental theorem of calculus? Simply differentiate. It's going to simply get you the tangent x, isn't it? Right, so of the Maclaurin series that I have of ln cosine x, I'm going to just differentiate and multiply by negative 1. It's going to give you the tangent x, okay? So as you can see, very, very nice exam problem with the composition, okay? Sure, another expansion that you should be aware is the binomial expansion. We already talked about it with the rational power, but also, it's often used for what often used with the Maclaurin series. And remember, if you have a binomial expansion, if you are just expanding not the general term, but only up to a certain degree, just simply use 1 plus x to the power of n is 1 plus nx plus n minus 1 over 2 x squared and all that. Okay, and it's not that bad because you're now going to substitute with the negative x squared. So these are the only terms that I'm interested in. So blah, blah, blah. I'm going to use that. So I've already expanded and simplified for you. So it comes out like that. Okay. Now, because after having done the Maclaurin series of this, they asked me to find the Maclaurin series of r cosine x. And is there any relation that you remember with this fancy binomial expansion with the rational power with the arc cosine x? You're absolutely right. It works with the, we found that. And in fact, if you integrate, what do you get? You're right. I simply get the arc sine x. Okay? So I'm going to just integrate both sides. I get the arc sine x. But here's the thing. You're right. Our aim is to get who? Sorry. Our aim is to get the arc cosine x. So is there any way that I can convert this arc sine x into arc cosine x? You're right. We remember there are two identities for you to memorize with the inverse trick. Was arc sine x. One of them was arc sine x plus arc cosine x equal to pi over 2. So I can substitute that. I can rearrange around. Then you can find the the Maclaurin series of arc cosine x. So another application with the Maclaurin series is that after having found some form, they ask you to differentiate or integrate and then derive the other Maclaurin series, which you should be able to do very well. Okay. Quotient, the division form is also very popular. So I want to find. We already discussed with the Maclaurin series of tangent x using the ln 1 plus sine x and ln cosine x and whatnot. But there's another method here. If you want to find the Maclaurin series of tangent, what you typically do is let this to be a0, a1x, a2x squared, a3x cubed. You can do that. And I'm trying to find the coefficient. But here's the thing. Here's a much quicker way. You do realize tangent x is an odd function. And if it's an odd function, you should be able to prove that the even terms are just or 0. Right? So the constant part, I don't care. The quadratic part, I don't care. I only care about who? Odd degree. So what I mean by that is that so the terms for the arctangent is going to be typically linear, cubic, and the quartic, degree 5. Exactly. So it's going to actually, increase the efficiency of solving the problem. And then what do? You just try to use the Maclaurin series of a sine x and cosine x on it. Right? The sine x was that, cosine x was that. It's going to be now a1x, a3x cubic, a5x5, on and on and on. And what you want to do is to rearrange that to the other side and compare with their coefficient. Okay? So it looks like this. So blah, 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 blah. I will leave it as an exercise for you. But now, because, look at this. This is the Maclaurin series of a cosine. You distribute, but the process would have been a lot quicker if you already realize x0, x2, x4 already 0. Because I want the tangent. The tangent is an odd function only having the odd degree terms, okay? Then you should be able to come up with this coefficient. Please practice. Okay, easy peasy, lemon squeezy. Oh wow! Fasten your seatbelt. Fasten your seatbelt. Maclaurin series with the differential equation. Let's get to it. Okay, sometimes you're gonna be given second order differential equation, something like that. We didn't learn how to solve it, okay? But you can attempt to solve it using the Maclaurin series. For that, it is very, very important for you to memorize this, okay? This is the typical form of a Maclaurin series. It's a power function of a function, y. And, the derivative, then you can do the term-by-term differentiation and then be able to express the first derivative and second derivative like this, okay? I want you to memorize it. It's not on the booklet, but it's the technique of solving the differential equation with I mean, it doesn't have to be second order. It can be first order, second order. But typically, this technique will be used for the second order differential equation. Then I'm going to substitute that. Let's have a look. So what I mean by that is the following. Right now, can you see well on the screen? The differential equation I'm given is the second derivative of that x squared dy over dx plus xy is equal to 0. And then initial condition was given as a 0, 0, and then dy first derivative was 1 at that point. Okay. So what you want to do is to, okay, these were the memorized form of series for the solution, first derivative and second derivative. What I'm going to do is just plug them in on the location of a second, first, and solution. So I've done that for you, okay? I've written it here already because I don't want to write all this. Okay, so I've got that, okay? So notice that I've just plugged the second derivative of the solution using the series formula, which is the direct result of term-by-term differentiation, okay? So boom, boom, boom. So x squared and x, okay? Y prime, and y double prime. And what we're going to do is to compare their coefficient. We want to compare their coefficients. So now what I've done here is working one by one. So for the first term, sorry, it was a second term, isn't it? Look at the second term. I'm multiplying by the x squared, so I'm gonna plug it in. And all the term with the polynomial here is gonna be raised by power over 2, isn't it? So I've done that. Okay, I've done that for you. Same thing for the next one. For the solution, I multiply by the x, so it's gonna be raised by 1. Okay, so I've got that. So now you have a sigma, which was raised by power of 2. But here's the thing, previously we had a x to the power of k minus 2 for the second one. But I don't like it because I just want to preserve everything by x to the power of k, x to the power of k. So notice that I've changed my index. You know what? I know it is not an easy concept, but that's the benefit of a video, isn't it? You can pause and you can write by yourself and then think. What I mean by that is for the previous example, let me show you in the previous slide. What I had was this, okay? But I don't like it because it's a k to the power of k plus 1. I want to compare with just by the x to the power of k and their coefficient. Okay, what we can do is that we can change the index, because if you expand this out, you're gonna have, 1 times a1 x squared, right? If I put at 1, it's gonna be 2 a2 x 3, and if I put 2, 3 a3 x power 4, plus on and on and on. But what I can do is to attempt to describe this by x to the power of k in the sequence. So sigma, I'm just gonna put a sigma. I want this to be x to the power of k. I'm choosing my index as an x to the power of k. So if I want this to be k, the sequence, all the subscript needs to be reduced by 1, isn't it? So if this is k, and then at the 2, sorry, I'm going to then start with what's going to be first term of x to the power of k was 2. But I want 1 and a1. For that, it's going to be, what is it then? K minus 1, ak minus 1. So we should be able to find a similar form for the sake of x to the power of k. That means you just have to change the index of a sigma. It's just a simple algebra from the sigma notation is what we're doing. And what we have done is, now I've found everything in terms of k, but notice the index of sigma changed accordingly, right? We should see that. Okay. And then I'm going to compare to the right-hand side. Look at this. The right-hand side is a 0, okay? So whatever the term that I combine here, their coefficient must be 0. Whatever x to the power of something, their coefficient must be 0, okay? So now I'm going to combine their coefficient with k plus 2 times k plus 1, ak plus 2, k minus 1, ak minus 1, ak minus 1. I combine them together. And they need to add up to be 0 because on the right hand side, whatever the expansion must be 0. Okay? But I want you to notice that it's only true for bigger than or equal to 2 because this one starts from 2. For the 0 and 1, we got to use from the initial condition, which I'm going to show you in a second. But right now, I'm more interested in this recurrence relation. Okay, let's have a look then. How can I solve the recurrence relation? This is a recurrence relation that is not in the syllabus, but we can know how to find the pattern. So this will be a typical paper 3 problem, don't you think? So, we were given the initial condition to be the following. Remember, this A0 and A1 are the terms for the Maclaurin series. He represents the constant term, and he represents the first derivative at 0, right? And then we were given the initial condition as a 0, 0, and dy over dx at x equal to 0 was 1. So, in fact, the constant term is simply 0. First derivative was simply 1. So I've got that A0, A1, which is the coefficient of the Maclaurin series. Brilliant. Okay, it's great. So I'm trying to combine more together to simplify. You can see that this is a like term, so you can combine them and then do the rearrangement, then boom, I've got that recurrence relation here. Wow. So far, so good. It is good, okay, it is good. Please fasten your seatbelt. So then what we want to do is to find the explicit form of this. Right now it is a recursive form. We don't like it. Sure, then how can we find the recursive form? We can actually try starting from the bottom now here, right? We can start it from the bottom. How are we going to do that? We have an initial condition, and then the first derivative, my friend, was simply 1 at x equal to 0. That was a given condition. So let's then try to find, who do you want to find? Who do you want to find after this? Yes, I want to find the A2. Okay, let's see what I can do with the A2. Okay, before we continue, what I want to remind you here is that if you look at the initial condition here, 0, 0, and then the first derivative was at 1, right? And I can actually use the differential equation to find who? The second derivative at that initial condition, right? So look at this. I've got the dy over dx being 1, but initial condition was 0, 0, so this 0 times 0. So in fact, I got the second derivative also at where? 0. So in fact, I know A0 is 0, A1 is 1, A2 is 0. So that is a known fact about this differential equation with the initial condition, okay? I wanted to make it clear before we continue. Okay, so I'm going forward. So the equation that we were working on was this. Okay, let's have a look. So we wanted to what? Work on the recurrence relation. Let's see. Sure, so before we do that, let me make it clear with the initial condition. It was A0 was 0, A1 is 1, A2 is 0. Okay, we saw that. So maybe we are interested in finding A3. Let's see that. So A3 is going to be who? I'm letting the k to be 1 to find A3, so it's going to be minus 1 times A0 over who? Whatever. But then I found the A0 was 0, so A3 is going to be 0. Okay. What about A4, my friend? So for the A4, k is 2, isn't it? So I'm letting the k to be 2, so it's going to give you negative 2 A1 over 3 times 4. All right, and then A1 wasn't 0, isn't it? So that's brilliant, right? That is brilliant. It's going to be negative 2 times 1 over 3 times 4. And you know what? To find the pattern for the explicit form for the recurrence relation, I am not going to combine, I'm not going to simplify that. I actually want to leave it like this, okay? I want to leave it like this. Okay, then you will see why later. So let's have a look at the A5. But here's the thing, you know what? For the A5, I'm not going to bother either. Why? Because for the A5, k needs to be 3. If you put k3, that gives you A2, which is 0. Okay, what's going to be the next term that's going to depend on the A5? A8 is also going to be 0 because it depends on A5. Okay, so in fact, anything with the remainder 2 after having divided by 3 is in fact going to be 0. We know that. Okay, that's interesting observation. Who was depending on the A0? A3 was. So now I know A0, A3, A6, anything with the remainder 0 after having divided by 3 is going to be 0. Can you think of any other? 1, 2, that's it, right? But then the one wasn't. 0 was what? A1, A3, sorry, A3 was 0, my bad. A4, so anything with the remainder 1 after having divided by 3 is going to be non-zero because their previous terms are non-zero. So I'm gonna just jump into who? I'm gonna just jump into 7. You know what I mean? So let's go with A7. So the A7, K is 5, so I'm gonna go with negative 5 times who? A4 over, I'm letting the K to be 5, so it's gonna be 6 times 7, okay? But it's a recursive, so I can use the expression for the A4 right there. That's going to be what? Negative 5 times negative 2 times 1 over 3, 4, 6, 7. Okay, looks very nasty. Sure, it's great. Now let's go with A10 to find any further pattern. So A10 would have been when K is equal to who? 8. So I'm going to go with negative 8 A7 over 9 times 10. So I have a negative 8, A7, 1 over 9 times 10, and A7 was, what was it? 10 times 1 over 3, 4, 6, 7, etc. And you know what? Now I want to find any pattern of this. I want to find any pattern with this. Okay? Sure. So what sort of pattern can you find? So let me list down the terms that we have. So we have A3, so A1 was 1, A4 is, what is it? Negative 2 over 3 times 4. A7 was positive 2 times 5 over, what is it? 3, 4, 6, 7. Okay, that's great. What was A10? It's a negative, so you can sort of see that it's alternating. So that's great. So A10 was a negative. Right, so from there, what do you want to do? 2 times 5 times 8. Okay, right, so that's sort of shows a pattern over 3, 4, 6, 7, 9, 10. Okay, all right. Let's jump into what? Finding the generalized form. So we know this is the representation of what? A3K plus 1. The one thing that I notice is that it's going to be an alternating term. So I'm going to just arbitrarily put what? Negative 1 to the power of who? K. How about that? Is it correct? Yes, it is correct. So that's an alternating term. Times, what about the numerator? It's a product of, what is it? Multiple of 3 after 2. So I'm going to go, what is it? 2, 5, 8, on and on and on, up to who? 3K minus 1. How about that? Does it make sense? Right? If I have 3 terms, it's going to be 8. So that's great. So it's a product of what? The multiple of 3 with the remainder 2. And now if I look at the denominator, that's a bit more fancy, isn't it? That is more fancy. So it's going to be 3 times 4, right? Times 6 times 7. So how would you go? I'm going to go with the 3K times 3K plus 1. Okay, how about that? Right? So that is going to give me the expression of that sequence. And in fact, I've written it down more details. Let me quickly show you. Sure, we're trying to find the pattern. So what we actually end up having was such. Okay, we actually managed to find a form like that. But as you have said, maybe it's gonna be better to find a more pattern on this, right? I want to simplify this further, and let me show you how you can simplify this further. So we managed to find a3k plus 1 like this. But here, if you look at the 3, 4, 6, 7, 9, 10, we put it like that. However, I really wish I wish it would have been factorial. What are the important numbers missing? In order for this to be factorial, you gotta be product from starting from 1 and ascending. So 1, it's already have. I don't have 2. I don't have 5. I don't have 8. So what if I arbitrarily just multiply by 2, 5, 8, and 3k minus 1? Hold on a sec. That's the one that I had on the top, isn't it? That's great. Okay, so what I like to do is actually just multiply itself again and then put that into consideration for the bottom. So here, it's going to come out as negative 1 to the power of k, 2 square, 5 square, 8 square, 3k minus 1 square over. Notice that I multiply the same thing in the bottom. Why? Because I wanted to make it as a factorial. So that becomes simply 3k plus 1 factorial. Okay, so that is what the coefficient of a 3k plus 1. Very good. Why have I found that? Because we wanted to find what? Maclaurin series general form of that second order differential equation, right? Now I found the a3k plus 1. He's going to represent the coefficient for which polynomial? X to the power of 3k plus 1 is going to be the extra term we have. If we go back to the board, so now I multiply that extra term to make it more simplified. This is going to be the solution for that second order differential equation. Notice I started with the k equal to 1, so this is going to start from what? A to the power 4. Sorry, x to the power 4. So then you gotta consider for the previous terms, the constant was 0, and then yes, we had the a1 being simply 1. So, and then anything between was all 0. It was only for the terms that was having the remainder 1. So after a1, I'm gonna go with a4, which does well with this polynomial, okay? Sure, I know. You might be thinking, what? Do I really have to do this? Well, I don't want to miss anything, okay? This is a primary example from a book called Holder. Brilliant book. I think the author used to be Cambridge Press, okay? Brilliant examples with the differential equation, including the Maclaurin series for solving the differential equation. So I want you to take a look, okay? I want you to take a look. Maybe this is a good paper 3 problems, but it is examinable. Why? Because it's in the book, and also it is in our syllabus, okay? That's pretty much it, okay? So, this is a run-through of the calculus. The whole point of this video was to remind you what sort of skills we need for attempting these problems, but details I sort of skipped because I typed it well on my PPT, so please go through the examples. And you shouldn't be satisfied just looking at these examples. Make sure you try yourself with a bunch of other past examples. But for me, other past examples are not that relevant at this moment. I think you should try to go with the mock exam papers from the books, right? He has a lot of mock exam. What else? Pearson also has it. Okay, so please try some mock exam paper from the books. I think that will be more relevant to you than going over the past paper, okay? But good luck to you. See you around.
All right, now we have gone over all the skills that we need for each topic before the main exam. Let's try to apply them, right? The beginning of the video started with going through some of the exam questions in May 2021. And now we have acquired relevant understanding from our video. We can accordingly apply them for the November paper. So what I'm going to do is to try to put myself in the shoes of a student and going to read through the questions. I'm not going to solve the problems, but I'm going to just check whether I have the relevant understanding of some skills to apply. what I think it is that the first 50% of the questions comes from your understanding, right? So but if you know it, then first half is done. The next half is the computation algebra that can only be consolidated by the number of the practice you do, right? And so for now, I'm going to just read through and then see if I have relevant skills, right? So let's have a look at number 1 and tell you what I mean. Okay, so I'm a student right now. I'm in the exam room. I just got the paper. I just want to read through the question first, maybe first 5 or 10 minutes. So I know, okay, so this one is going to be something like the fundamental theorem of calculus. It's something of the derivative. They asked me to find y in terms of x. I got to be extra careful with the initial conditions. That's all I'm going to say. I'm going to move on. I should be confident being able to solve it. Okay, it's talking about the rational function, horizontal asymptote, vertical asymptote, x-intercept, y-intercept, easy peasy, lemon squeezy, right? We should be able to check with the vertical asymptote quickly, with the x being 3 and horizontal asymptote being -2. Make sure you follow their coefficient, and that's pretty much it, okay? Then we're gonna move on. We can sketch them, no problem. And it says what? I want to find the what is it? The given that the function is inverse, it's called a self-inverse, right? So what you want to do is, okay, if I want to talk about the self-inverse, I know that I'm going to composite this and then try to find the value of a that makes it x. Okay, so now I'm aware it's going to be something with the self-inverse, and I move on because I already know what skills I'm going to do. The next part is the algebra, which I'm going to do it later with more time. Okay, property of log. Maybe I don't have a same base. No problem. I can do the change of base, especially realizing that log BA is the same as what 1 over log AB. You know what I mean? So that's all I'm gonna do. I'm gonna be aware of what skills I'm gonna apply here, and I'm just gonna move on. I'm confident being able to solve it. Okay. And for the probability problem here, a box A is chosen at random, ball is drawn, find the probability that ball is red. And for this one, I realized, okay, I'm going to go with the tree diagram first, right? And I'm sure it's going to be something with the law of total probability. Okay. And also, independent, what do we do? There are many ways of determining it. And one is a probability of A given B. If it's independent A and B, it's going to be probability A. Or you can use probability of A intersection B is going to be probability of A times probability of B. And I'm already aware this is going to be somewhat with the tree diagram, and maybe this is going to be a more comfortable method. I'm just going to read through and apply my understanding accordingly and just move on, right? I'm going to just move on to the next question and glance through what sort of questions I'm going to encounter. Okay? Very good. Sure, derivative at a point should give you the gradient of tangent and the passing point. It's good to go. Okay, G is defined as such, and then I have the hx with the composite function, no problem. And it's going to be something with the composite function. I should be able to find the f of g over 4, where g over 4 will be given here, and etc. We already know, right? And this is going to be somewhat with the chain rule because I'm dealing with the composite function. That's all I gotta say. All the details of algebra, you can do it. Okay, I will leave it to you. Very good. I just move on. Okay, now this is going to be, what is it? A long division, right? I've got a quadratic over linear, so I just try to do the division here, and this is quotient, and this is a remainder. And now what are they trying to do? Okay, now I definitely have to, if it's hence, I definitely want to use the previous information. And maybe choosing the right substitution is going to play the key role, right? And what I recognize, okay, the left-hand side pretty much looks like that, right? So what I want to do is maybe make the relevant substitution with the x with sine to theta, and then try to work with the right-hand side and make that equal to 0. And it's even better because I just have to deal with the numerator being 0 for solving an equation, right? And then that's going to be something that I'm going to check first. And the next thing is, yes, please make sure for the trigonometric equation, you really need to check on the domain because it gives you a certain number of solutions. That's all I'm going to be just writing down on the paper. Why? Because I'm confident I'll be able to solve it later, right? Because I know it is going to be something with the hence problem, so I'm using the previous information. And for the trigonometric equation, I got to be careful with the domain, and I move on, right? And I move on. Okay, it's talking about who? Two real distinct roots, talking about the number of solutions. What have we talked about in the video? You're absolutely right. I'm going to use the discriminant. So, discriminant being positive, real roots fine. Case of p equal to 4, roots of equation can be expressed blah blah. And what are we going to do? We're given roots, and I'm given some sort of a coefficient with the polynomial. Then maybe it's something with the either, if I let the roots to be x1 and x2, then maybe I can factorize it with the p being 4, so 12, or you can do the sum and product of roots. Remember that? Oops, sorry. x1 plus x2 is going to be, negative b over a, where your b is given as such and the p is given, so you can use some algebra to find the a, no problem, just like we checked from the video. Okay? Easy peasy, lemon squeezy. Alright, so differential equation here. Okay, what you want to check here is if it's possible to solve out of how many methods? 3. We have a case of a separation of variable. And what else? We also had the homogeneous, and also integrating factor. And for me, what I notice is that if I maybe rearrange that to the other side, I've got the dy over dx plus 2y over x is equal to then 2x over x squared, where this is a perfect setup for the integrating factor, right? We can choose the integrating factor 2 over x dx, and it'll be good to go, right? The rest is just the next half is just algebra, right? That I'll leave to you. But the first 50 is already finished, right? We know what method we're gonna use, right? That's what I want you to just to practice. That is great. Okay, binomial expansion, no problem. I can do I'm just going to simply use 1 plus x to the power of n. I gotta be careful whether if I have a constant being 1, I have it, then I can just use 1 plus nx plus n times n minus 1 over 2 x squared and n minus 1. Where is it go? Oh, okay, up to second degree, so I don't need to bother with that, right? So just use that accordingly. Then I can find the a and b. It's just going to be sum of two Maclaurin series, two power series, and you can combine them together. Yes, remember, we gotta be careful with the interval of convergence of the binomial expansion. Always think about any value that makes it 0 inside, right? For the second one, it's going to be between -1 and 1. And the first one is going to be between, I don't know if a is going to be positive or negative, but let's go with the absolute value of -1 over a minus less than absolute value of -1 over a. That is going to be your interval, and what you got to do is just find the intersection accordingly. Okay, that is great. Sure, without blinking an eye, I know it's something with the velocity, it's kinematics. I gotta be very careful. Maximum velocity, it's a concave down, so you can easily find it. But of course, I need to be aware whether that maximum is gonna be in the positive time. If so, then it's pretty piece of cake. And for finding the distance, right, I gotta be careful because it's talking about the area. So from at this time, okay, so I'm talking about the time of maximum. Sure, from 0 to t maximum, absolute value of t is what I'm gonna do. Make sure it's talking about the area, and yeah, it's a quadratic function. I can find it. That's it. Then total distance is going to be from 0 to 3. Make sure you graph it well and see if you can find any negative region. Then you can find the area. That's all I'm gonna be aware, right? I'm already aware of it. Okay, proof by induction with the differentiation. I know I gotta be super careful with so let's go with the result to prove. Is simply going to be what? Just differentiating once more of my induction hypothesis, right? That's all I'm gonna say. I'm already aware of what sort of a trap they're gonna do, and then now the next 50 is just algebra. Okay, right? And if I look at the second one, hence or otherwise determine the so it's pretty nice because we know for the Maclaurin series I just gotta tack on the nth derivative of a 0, n factorial x to the power n. I can use all this for the coefficient of a constant, linear, quadratic, cubic, degree 4, you name it. Okay, I can just put the n with the 0 number and then divide it by the n factorial. That's gonna give you the coefficient right away. Okay, piece of cake. And yes, you know what? If it's hence problem, I'm aware you could, okay, you could apply L'Hopital, but I don't want you to. I don't want you to because I see already that differentiation is going to be nasty. You definitely want to use the Maclaurin series that you already have done. And then what my best guess is that or whatever the Maclaurin series, it's going to cancel out with the x squared, you know what I mean? So then all the terms are going to be somewhat bigger than 2, right? The degree is going to be bigger than 2, and maybe it's going to come out like a cubic, but then you put it into the power of q, so everything is going to be a very higher degree that I can actually divide by the x to the power of 9, so it's going to be actually canceling some terms out. Therefore, you can essentially put x equal to 0 because you no longer would have x squared in the bottom. We already know what sort of tactics we're going to apply. That's the whole point of learning these techniques, because you can foresee, you can foretell the answer already, but the details is just algebra. Okay, easy peasy, lemon squeezy. Okay, complex number, higher power with the I. Maybe I gotta do the roots of unity. Verifying the roots is just plugging in and just see if it becomes I. And I want to find another root, so I gotta use the roots of unity. But for that, I need to make sure I would put a polar form or Euler form, doesn't matter. E to the power of pi over 2i. Then I can use the roots of unity formula. We're good to go, right? I should be able to visualize that on the Argand diagram, no problem. And then I can find the AC just to find the distance formula. Consider the equation of another form using the demo. Sure. All I gotta do is just plug it in and make sure that maybe you don't like having the complex number in the bottom and multiply by the conjugate. And for me, okay, the conjugate is going to be careful. It is not 1 plus e. It's going to be simply just 1 minus e to the power of negative argument, right? And then just simplifying terms, and especially I've got the negative 1 there, so maybe it's better to express what? In the Cartesian form, right? So because I believe maybe you can cancel out with 1, I don't know, who knows, okay? But then, it's going to simplify the terms quite quickly for you. And that's just to run through, I'm already confident, once I get the piece of paper here, I know most of the answer. Then I just have to work on my algebra to get the answers correctly, okay? And that's the sort of things that I wanted to embed it in you before the exam. By going through the video, you're aware, most of skills that we discussed according to the AA guideline, we are aware of it, okay? Then you can easily solve it. So I really hope that the video was a great help, sort of a last minute revision for you, and that you're gonna do well for the exam on the 6th of May, okay? Wish you all the best, and do not panic. At the end of the day, it's mathematics. You cannot really cram. You cannot do the revision at the very last minute, but take your time, sort of doing this mental practice. Can I read the paper? Can I read the exam paper and know the skills accordingly? Can I get the first 50% correct? If you can acquire that within the remaining time, I'm sure that it's going to definitely help improving your grades, okay? That's pretty much it for me today. I will see you around. Ciao.